Okay, let's unpack this. We are diving deep into a problem that, frankly, costs organizations a staggering amount of money.
A truly staggering amount.
And it affects nearly every single person who works in a large office building. I mean, it's a failure we often just accept as, the background noise of corporate life.
We really do. We just put on a sweater and get on with it.
Exactly. So I want to start, as we always do, with a stat that just sort of stops you in your tracks. Did you know that buildings, the structures we live and work in, continuously consume approximately 40% of the entire world's energy supply?
40%. It's almost unbelievable.
It really is. And you have to think about that massive energy footprint. It's not just some abstract environmental issue. It comes with a massive, massive price tag.
It absolutely does. And that price tag is hitting the balance sheet of every major corporation right now.
So our mission for this deep dive is to cut through that noise and really reveal where this money is going.
Right. And we're pulling from some really systematic research that's focused specifically on facility management.
Not just any buildings, though, right?
No, specifically for large commercial office buildings, particularly here in the U.S.
And the sources we've looked at tell a compelling, almost shocking story about how these, poor operational choices cost organizations billions every year.
Billions with a B, and at the same time, it's absolutely tanking human productivity.
Which might be the even bigger cost. This isn't theoretical. We're talking about real, measurable loss.
And that's why we're really analyzing one core question here.
What's that?
How exactly can the strategic adoption of artificial intelligence, of AI, enhance the decision-making of the facility professionals?
The people on the ground running these buildings.
The experts, yeah. How can AI help them dramatically improve energy management while, and this is the key, simultaneously satisfying occupant comfort?
Because those two goals, saving money and keeping people comfortable, they often seem to be in complete opposition to one another.
They really do.
You turn the air conditioning down to save a few bucks, and suddenly half your workforce is complaining they're too hot to think straight.
And that's the core conflict we're unpacking. Facility professionals are constantly, every single day, trying to balance minimizing those massive fluctuating energy costs with maximizing the complex and often conflicting demands of comfort for every single person in that building.
And you're saying that achieving that balance is worth billions.
Billions.
And just to be super clear for you listening, we are focusing specifically on large commercial office buildings in the U.S., those at least 100,000 square feet.
Right, which represents a massive segment of the knowledge worker economy.
So we want to know how AI provides a systematic solution to this dual crisis of cost and comfort for everyone who manages and works in these huge spaces.
It's a huge question.
Okay, let's start with the money. Let's follow the money because the numbers here are truly alarming. I mean, they're almost unbelievable until you really contextualize them.
They really are.
So we've established the context. The building sector globally uses about 40% of the world's energy supply. But what does that actually translate to in dollar signs and organizational impact right here in the United States?
Well, if we look at the hard data that's been collected and analyzed in the sources, the organizational costs are nothing short of staggering.
Give us the headline number.
Organizations in the U.S. collectively lose approximately $15 billion annually.
$15 billion.
Annually. And this is due to inadequate operation and maintenance, or O&M as they call it, of their commercial buildings.
And that figure, where does that come from?
It's based on a 2018 report that has been systemically reviewed, so it's solid. And it highlights a crisis of efficiency that, frankly, is not being adequately addressed.
$15 billion. That is not just a rounding error on a balance sheet.
Not at all.
That sounds like the kind of financial damage caused by major natural disasters or a massive corporate fine, not just, badly managed thermostats and ventilation systems.
That's the key distinction, though.
How?
We aren't talking about money lost because a catastrophic failure required buying a new multi-million-dollar chiller unit. That's a capital expense.
Okay.
We're talking about money lost due to operational inadequacy.
So just running things poorly.
Exactly. This includes things like running HVAC systems at full blast when a whole wing of the building is empty on a Friday afternoon.
Right.
Or simultaneously heating one zone while you're cooling the zone right next to it because of faulty sensor readings.
I feel like I've experienced that exact scenario.
We all have. Or paying higher peak electricity rates because systems weren't optimized to pre-cool the building in the morning. The loss stems from poor control, poor monitoring, and just inefficient processes.
So if a building is overventilating the entire space because a timer is set incorrectly, or if a damper is just stuck open somewhere in the ceiling, that inefficiency adds up hour by hour, day by day, contributing directly to this $15 billion black hole.
That's it. Precisely.
Yeah.
And the data shows this is not a static problem. It's actually getting worse.
It's accelerating.
It's an accelerating problem. You just have to consider the historical context that the sources provide. A similar study, this one conducted back in 2012, estimated the cost to commercial organizations alone was $10 billion.
Wow. Okay, so it jumped from $10 billion to $15 billion in just 6 years.
That's a 50% increase.
A 50% increase in estimated operational loss over a very short period. What does that jump tell us about the state of facility management?
Well, it underscores a fundamental truth, really. The energy costs that organizations have to bear have just continued to increase significantly.
And I'm guessing the buildings haven't gotten any simpler to manage?
Not at all. The complexity of managing these large modern buildings has also grown exponentially. You've got more sensors, more controls, more integrated systems.
And labor costs have gone up.
Labor costs have risen, and the expectation of consistent optimized performance has increased. So it demonstrates this sustained escalating issue that traditional, often manual facility management practices simply cannot keep pace with.
So it's not just a flat problem that we can kind of ignore and budget for. It's an accelerating financial drain that actually threatens an organization's survival, especially in competitive markets.
The sources are very clear on this. The problem is existential.
That's a strong word.
It is, but it's accurate. This isn't just about saving a bit of money in the short term. Improper control of buildings, when you couple that with the natural, continued increase in energy costs.
And the rising labor costs.
And the now mandatory public and regulatory emphasis on environmental impact. It all severely affects an organization's long-term sustainability.
So if a company is consistently losing, say, tens of millions of dollars just by running their own headquarters poorly,
they simply cannot sustain that drain on their resources year after year after year. It makes them uncompetitive.
And when we talk about this improper building control, let's get specific about the operational failures. What are the common culprits that contribute most heavily to this inefficiency?
They really fall into three main categories of costly outcomes.
Yeah.
First and foremost is the massive excessive energy use we've been talking about.
Right. The obvious one.
Paying for overheating or overcooling unused spaces, or unnecessarily running pumps and fans at 100% capacity when, 60% would have been perfectly fine.
Just waste. Pure waste. What's the second one?
The second outcome is the accelerated wear and tear on the building equipment itself.
Ah, I hadn't thought about that.
Yeah. When equipment runs outside its optimal parameters, or if it's constantly cycling on and off because the control system is confused.
Like it's fighting itself.
Exactly. It drastically shortens its lifespan. And this means more frequent and much more expensive replacements of these multi-million-dollar components like chillers, boilers, and air handling units.
That makes perfect sense. It's like if you redline your car engine every single day, you're going to be replacing that engine a lot sooner.
Precisely. It's the same principle, just on a much, much larger and more expensive scale.
Okay, so wasted energy and worn out equipment. What's the third outcome?
The third is a significant increase in the use of organizational resources beyond just energy and equipment. And this really comes down to labor.
The people.
The facility professionals themselves. If they are constantly in firefighting mode, reacting to alarms, chasing down comfort complaints, performing emergency repairs instead of planned preventative maintenance, they are spending organizational resources incredibly inefficiently. Their time is valuable.
So the organizational mandate then, if they want to survive and remain competitive, is crystal clear. They have to improve building control to safeguard their long-term financial health and, frankly, their environmental credibility.
That's the cost side of the equation.
But there's another side.
Yes. It's the side that's inextricably linked to the human side. Because the moment you start trying to save money by, say, reducing the HVAC load, you immediately bump up against human comfort.
And that's where the hidden, often unquantified productivity losses begin.
That's where they really start to bite.
So we've covered the corporate hemorrhaging, that $15 billion loss annually from just operational mistakes. But where does the human cost really come in? I mean, that $15 billion is the ledger side of it. Let's talk about the productivity side, which is often far more valuable to a modern organization than its utility bill.
The connection is absolutely undeniable, and the research provides a clear, evidence-based link.
What's the core argument?
It's simple, really. Uncomfortable and irritated employees are significantly less productive than employees who are comfortable in their surroundings. It's common sense, but the data backs it up.
So if you reduce those comfort-related distractions in the workplace,
You directly improve employee performance and you increase organizational output. The goal is to maximize the return on the largest investment any company makes.
which is its people, its payroll.
Exactly.
Okay, let's unpack what the sources actually define as occupant comfort. Because for most people listening, comfort is just not being too hot or too cold, but it's much broader than that, isn't it?
It's far broader. Occupant comfort is defined in the research as the total occupant experience during any indoor activity.
The total experience.
Right. And this encompasses a whole range of measurable environmental factors that directly affect an employee's concentration, their health, and their overall performance.
And if any one of those factors is out of balance.
If any one of them is off, the employee's brain is devoting precious cognitive resources to managing that physical stress rather than focusing on the organizational task at hand.
The research breaks this down into 4 critical areas. Let's start with one that often feels like inescapable background noise in a large office. Noise levels.
Noise is a profound cognitive drain. It really is.
Yeah.
Excessive noise in commercial buildings distracts occupants and visitors, and it makes it incredibly challenging to think, to communicate, to concentrate, and to perform even, rudimentary tasks that require focus.
Yeah, if you're constantly having to filter out the sound of a roaring ventilation system or, your neighbor's loud conversation.
Your cognitive capacity is already reduced before you even look at your first email of the day. You're starting at a deficit.
And the sources even raise a major health concern when it comes to noise. It's not just an annoyance.
They do. The research warns that sustained loud noises in the workplace may have long-term health effects on employees.
Like what?
Everything from stress-related illnesses to actual hearing issues. And this is why, in the context of a high-performance organization, excessive noise isn't just deemed unacceptable. It can constitute a genuine health hazard that the employer is actually responsible for mitigating.
Your ability to concentrate is directly tied to the noise floor of the building.
Directly.
That immediately hits home for anyone who has worked in, say, a poorly designed open-plan office or right next to a constantly humming piece of server equipment. It just fragments your attention.
It completely does.
Okay, what about lighting? That's something that's often overlooked, unless a bulb just burns out completely.
Inadequate lighting is also a major culprit, and it can be really subtle. It affects an occupant's vision, their psychological comfort, and ultimately their concentration.
Which then severely impacts their performance.
Right. The goal of facility operations has to be to maintain adequate and appropriate lighting, which helps keep occupants focused on their work tasks. If the light is too harsh or too dim, or it's casting weird shadows, the brain spends energy just trying to adjust the eye.
And the sources flag a very specific, kind of surprising hazard related to lighting systems that I don't think most people would ever consider a major operational failure.
Yeah, they note the hazard of instantaneous changes and unprovoked light flashes.
So not the sun going behind a cloud?
No, this isn't about natural light variation. This is about poorly controlled systems, faulty dimmers, flickering ballasts, or automated systems that trigger erratically.
Why is that so bad?
It's identified as a significant distraction and a genuine health risk for certain building occupants. It interrupts a person's visual field without any warning, and that completely breaks their concentration. Their flow state is gone.
That is a perfect example of a tiny operational flaw that causes a huge productivity drop.
A huge drop.
Okay, now for the grand champion of all complaints, and the one that probably impacts that $15 billion figure the most: thermal comfort.
Thermal comfort is, without a doubt, the most frequent, the most visceral complaint of building occupants. It is a direct and powerful distraction.
Everyone has an opinion on the temperature.
Everyone. And because of the sheer amount of energy it takes to heat and cool a huge structure, solving the thermal issue also significantly impacts the overall energy consumption and the utility cost.
So what's a goal there?
The goal is maintaining a consistent, well-balanced indoor air temperature while also ensuring you have correct air exchange and circulation.
And facility managers often fail at this, right? Which leads to that immediate, visible evidence of employee discomfort that the research calls out.
Absolutely. The research provides these clear, illustrative examples of this discomfort in the U.S. workplace. You see occupants wearing long sleeves, bulky clothing, even blankets indoors.
The infamous office sweater?
The office sweater, exactly. Or requesting and using personal space heaters, which are often an energy nightmare and a fire hazard.
Or cooling fans.
Or resorting to using cooling fans, and often during seasons when you wouldn't even expect them.
What do you mean?
Like requesting a fan indoors during the dead of winter because the room's being overheated due to a lack of proper zoning control. The system is just blasting hot air on them.
I know exactly what you mean about the fans. I once worked in an office where I had a desk fan running in January because the forced air from the perimeter system was so intense it felt like a blast furnace, even though the core of the building was actually cold.
That's the failure right there. It's the inability to correctly balance the different zones of a building.
And when occupants have to actively adjust their clothing or resort to personal devices just to achieve a baseline of comfort,
They are profoundly distracted. Being too cold or too hot severely affects employee performance because, again, the brain's primary focus shifts from processing complex information to just achieving physical homeostasis.
it's a survival instinct.
It is.
So if I'm sitting there wearing 3 sweaters, maybe running a space heater under my desk, and I'm periodically getting up to adjust a window blind because the sun glares too much, my employer is effectively paying me less to be productive because I'm so distracted by the facility's failure. It's a double whammy. You've got wasted energy and wasted salary.
That's the central insight that so many organizations miss. That loss of focus translates directly into measurable, decreased organizational output. It's a hidden cost that completely dwarfs the utility savings they might be trying to achieve by, throttling the AC.
Finally, the sources mention a few other critical environmental factors that complete the picture of occupant comfort.
Yes, these are the remaining elements that contribute to that total occupant experience we talked about, and they're critical for health.
Like what?
These include things like building cleanliness and the maintenance of aesthetics, which impact psychological well-being. But there are also crucial measurable factors like humidity, carbon dioxide levels, and odors.
CO2 levels, that's an interesting one.
Is a huge one. High CO2 levels, which are often caused by inadequate air exchange or poor filtration, lead directly to drowsiness, reduced mental clarity, and headaches.
The 2 p.m. slump might not just be lunch.
It might be the air you're breathing. And odors, whether they're chemical or organic, are immediate distractions.
So appropriately addressing all these factors ensures occupants are comfortable indoors, they're focused on their organizational tasks, and they're working in a healthy environment.
It completes that holistic picture of the indoor environment that directly drives productivity.
So we've established the enormous financial cost of poor operation and this profound impact on human capital because of discomfort.
Right.
Now we need to look critically at how these buildings are currently managed because, as you pointed out earlier, facility professionals are not working blind. They have access to data.
They do. They are absolutely drowning in data, even if they aren't using it correctly or efficiently yet. The infrastructure is there.
So what does that infrastructure look like?
Precisely. Modern, large commercial and administrative buildings are already equipped with these incredibly sophisticated measuring devices and sensors.
They're everywhere.
Everywhere. And they're part of what's called the Building Management System, or the BMS.
Okay.
And these systems collect huge quantities of real-time data. They're constantly updating information that describes equipment operational characteristics, environmental conditions like temperature, humidity, airflow rates, and the current state of the entire building.
So these sensors are the fundamental data foundation upon which everything else sits.
They are.
And the facility professionals, they rely on this information from the BMS to monitor conditions and make these crucial decisions.
They do. And these decisions can range from the really minor adjustments, like tweaking the temperature set point in a specific conference room for a meeting,
to really big system-wide changes.
Right, like altering the chilled water supply temperature for the entire HVAC plant based on the expected heat load for the day.
And these decisions, as the research notes, may not have an immediate dramatic effect on the building's structure, but they absolutely affect long-term occupant comfort.
And critically, energy conservation.
Yeah.
If they make a bad operational decision at 8 a.m., the building might feel fine until 2 p.m.
At
which point the discomfort complaints start flooding in and they're behind the curve. The professional's challenge is synthesizing this constant flood of real-time operational data into an effective, timely decision.
But when things inevitably go wrong, when that critical operational decision is missed or delayed, the current system is inherently reactive.
Completely reactive.
It waits for the human to experience a failure. So let's walk through the exact process that the sources outline for addressing discomfort, the basic customer request flowchart. The researchers call this the reactive workflow.
This workflow is the status quo for facility management everywhere, and it just highlights the latency, the delay that's inherent in the system.
So where does it start?
It all begins with the initiate requirements step.
Yeah.
The occupant submits a customer requirement, which is the formal tracked term for their complaint.
It's too hot, it's noisy, there's a light out.
Or I smell a bad odor in the east wing.
Yeah. And how do they submit this requirement? I'm guessing this is often done while they're already annoyed and distracted.
Usually, yeah. The sources outline the 3 typical methods. There's personal contact with facility staff, stopping a technician in the hall.
The classic hallway complaint.
Right.
Yeah.
Or a phone call to a dispatch center. Or increasingly, an online submittal system, usually through an intranet portal.
And regardless of the method, the complaint then moves into the next phase.
Yes, the review requirement phase, which typically goes to a central work control system or team.
And work control acts as the triage center, validating the complaint, maybe prioritizing it, and then dispatching the right people.
Yes, which leads to the execution finalization step. Work control assigns the work to a specific technician or trade for execution.
The plumber, the electrician, the HVAC tech.
Exactly. The technician performs the necessary work, adjusts the damper, fixes the light, performs a filter check, whatever it is. And importantly, the outcome of the technician's action is formally categorized.
What are the categories?
It's either deferred or delayed, which means the issue couldn't be solved immediately, or it needs a major part or a bigger fix, or it's marked complete.
And once that task is marked complete or deferred, the loop closes. The paper trail ends.
Correct. The customer is notified of the action taken. We adjusted the damper, please check in an hour, and the requirement is officially closed in the system.
And the entire process, from initiation by the occupant to the final closing by work control, is captured.
It's captured in a formal record that gets stored in their administrative systems. This is typically the Computerized Maintenance Management System, or CMMS.
Okay, so that's how one single complaint gets handled. But here is where the massive, game-changing opportunity in all this data truly emerges. This is where you can transform that annoyance into a real insight.
That's absolutely right, because every single time an occupant files one of these requirements, a complaint of discomfort, a note of a failure, it is stored digitally.
Every single one.
Every single one. And over time, thousands and tens of thousands of these requirements accumulate. This stored record captures not just the immediate action, but the entire history of occupant pain points across every single square foot of that building.
So this historical record of past discomfort, when you combine that with the building equipment's operational characteristics, all that real-time data coming from the BMS sensors, which are also being stored in these same databases like the CMMSs.
It creates a colossal untapped data source.
It really does.
It's this combined data set, the operational temperature logs, plus the history of too hot complaints in Zone 4A, that is immensely analyzable.
And it allows facility managers to shift from, as you said, firefighting.
To prevention.
To prevention.
They can analyze this data to predict and address specific situations before occupants even experience the discomfort or before the energy consumption spikes unnecessarily.
So that transition from reactive firefighting to predictive, preemptive intervention is the entire strategic goal of applying AI here.
That's it.
It's about leveraging the data they already own to stop that $15 billion leakage.
That's the whole game.
So we're talking about this transition from a reactive model where the organization just waits for a person to file a complaint to a proactive predictive model where the building actually anticipates the complaint by synthesizing all this complex data.
That's the shift.
And this is where artificial intelligence steps in as the crucial intervention.
Right. And the research we're drawing from uses a very specific, rigorous lens to analyze this shift, which I think we need to explain because it really grounds the whole methodology.
Okay, what is it?
They use the adaptive structuration theory, or AST, as the framework to analyze and interpret the decision-making of the facility professionals.
Okay, adaptive structuration theory. That sounds intensely academic. Can you give us an analogy for what AST is actually trying to capture in this context?
Yeah, of course. Think of it as a cultural and behavioral lens.
Okay.
AST studies how a new technology, in this case, AI, doesn't just get adopted, but how it actually changes the culture of the people who are using it.
So it's not just about the software.
No. It looks at how AI influences the structure of facility management decisions and how the professionals, in turn, adapt the use of the AI tool to fit their organizational needs.
It's a two-way street.
It is. Essentially, they are trying to gain an evidence-based understanding of the impact AI can have on the habits, the choices, and the interactions of these facility professionals. It ensures we analyze AI as a human-technology interaction, not just a standalone piece of software.
That makes sense. It's studying the entire system, not just the code. And to structure this complex analysis of that human-technology interface, the study relies on something called the SIMO framework. And this gives us a very clean way to frame the research question, guiding this entire deep dive. It's like a clean narrative structure for a complex idea.
Exactly. The SIMO framework stands for context, intervention, mechanism, and outcome. It's just a way to break down cause and effect systematically.
So let's break down the categories the study used because they really clearly define the parameters of the problem and the proposed solution.
Sure.
So first, the context, C. This answers the question, which individuals, relationships, or systems are currently operating under stress?
The answer is 3 critical elements that are operating in constant tension with each other.
Which are?
Occupant comfort, energy management, and the facility professional themselves. These are the elements that exist in the status quo, and they're always struggling against one another.
Then we move to the intervention. This is the change agent, the effects of what event or activity are being studied.
And that's the key technological lever we're focused on today. Artificial intelligence. AI is the disruptor that's designed to resolve the tension that we found in the context.
And this, to me, is the most critical part. The mechanism. What mechanisms explain the relationship between the intervention, the AI, and the desired outcomes? I mean, how does AI actually work inside the system to change behavior?
The focus here is highly specific. It's the decision-making of the facilities professional.
So AI is not replacing the human?
Not at all. It is serving as an enhancer, a tool. It provides immediate, synthesized, predictive data that allows the human decision-maker to make smarter, faster, and more optimal choices than they could if they were just relying on raw sensor data or reactive customer complaints.
So the mechanism is the improved quality of the human decision, which is driven by superior intelligence from the machine.
That's it. And finally, you have the desired outcome. Oh, what are the ultimate effects of the intervention?
And the goal?
The intended effects are the improvement of energy management while satisfying occupant comfort and reducing costs. And that neatly captures the entire mission.
Solving the dual crisis of cost and comfort simultaneously, and you're leveraging AI as the tool for decision enhancement. And we keep coming back to the specific focus of this systematic review. These commercial office buildings in the U.S. that are 100,000 square feet or larger. Why is it so crucial that the research targets this specific subset of real estate?
It's critical for 2 main reasons. First is just the scale.
Okay.
The U.S. Energy Information Administration defines these structures as those used for general, professional, or administrative office. And it's interesting, they note that medical offices qualify if they don't contain diagnostic equipment, so like a large clinic space.
And how much of the market is that?
These large office buildings make up 34% of the total office floor space in the United States.
A third. Over a third of the market?
Yeah, that's over a third of the market. It represents trillions of dollars in assets and energy consumption. So targeting that 1/3 has a massive potential impact on national energy savings and productivity.
It's a huge lever to pull.
It's a huge lever. But the second reason is the human factor. While office buildings only rank 8th by floor space among principal building activities overall, they contain the most shift workers.
These are knowledge workers, often sitting at desks for 8 to 10 hours a day, relying entirely on cognitive focus for their output.
That's right. And improper building operations decisions have a compounded and a disproportionately negative impact on these specific workers.
How so?
Well, a factory floor worker might be able to move or adapt to a hotspot, but a knowledge worker whose task requires deep focus is completely derailed by a headache from high CO2 levels or a distraction from thermal discomfort.
Their entire job is focus.
Right. Their comfort and productivity are central to the economy, which makes this segment the highest leverage point for improvement.
That really drives home the importance of minimizing those comfort-related distractions. So before we jump into the specific applications of the technology, let's make sure we're all clear on what AI is in this context, because it's not, the futuristic science fiction we see in movies.
No, not at all. And the source material provides a very useful, functional definition that really grounds it in reality.
What's the definition?
AI is a general term that's used to encapsulate many different uses of predictive statistical models.
Okay, so it's math.
Essentially, yeah. We're talking about machines evaluating massive quantities of data based on weighted factors and algorithms to present a functional use of that data, meaning a decision recommendation or an action.
So it's advanced pattern recognition.
That's a great way to put it. Familiar systems that fall under this AI umbrella include things like neural networks, expert systems, machine learning, or ML and deep learning, DL.
And the goal is what?
It's about creating an intelligence that can process and perceive patterns like a human, but at a massive scale, at incredible speed, and crucially, without human bias or fatigue. It is specifically designed to handle the complexity and the volume of that BMS and CMMS data that would just completely overwhelm a human analyst.
So now we get to the core of the findings, how this technology can be systematically applied to facility operations.
Right. How to transition the facility professional from being a reactive technician into a strategic manager.
You mentioned that AI enables machine to mimic human perception and cognition. How does that actually translate into solving that $15 billion annual problem and addressing the productivity loss we talked about earlier?
It translates through advanced, synthesized data analytics. AI applications have already expanded into nearly every industry, from translation to robotics, and especially in decision recommendations.
So what does that look for facility management?
For facility management, employing ML and DL frameworks offers these really sophisticated data analytics solutions for energy management and, crucially, for developing energy-efficient protocols that are tailored specifically to the analyzed building's unique operational history and its occupancy patterns.
So the AI doesn't just crunch numbers faster, it actually enhances the very process of data collection and integration itself.
Yes, to support better analytics. It effectively makes the data foundation stronger and more coherent for the human to then use.
And the researchers found evidence that AI is capable of taking the existing data streams, that massive volume of information flowing from the BMS sensors and the historical records from the CMM,
and using it for immediate, actionable insights. The results really coalesce into three major interlinked benefits that can fundamentally redefine facility operations.
Okay, let's start with the immediate benefit, the one that directly tackles the optimization problem, real-time monitoring and optimization.
This is where AI moves beyond just simple detection and into proactive prescription.
What do you mean by prescription?
AI can monitor all building operations, every sensor, every fan speed, every valve position, and provide real-time reports based on pre-processed and correlated data.
Okay, so it sees everything at once.
And crucially, these reports don't just tell the facility professional what's happening right now, like Zone 4A is 75 degrees.
What do they do instead?
They offer immediate awareness of predictive suggestions for optimal equipment settings. The AI runs thousands of hypothetical scenarios almost instantly to decide what the optimal balance point is for the building.
Optimal settings, that is the key that prevents the $15 billion loss. Can you give us an example of how this recommendation moves beyond just a simple thermostat adjustment?
Sure. So a facility professional might see a spike in temperature in Zone 4A starting around 1 p.m.
Right.
A human might instinctively just lower the air handler temperature for that zone.
Seems logical.
It does. The AI, however, knows that based on the weather forecast, the heat load from the south-facing windows, and the historical complaint data from that specific zone, lowering the chilled water supply temperature right now will actually cause the building core to overcool by 3 p.m.
Triggering a whole new set of complaints.
And wasting a ton of energy.
So what does the AI recommend instead?
Instead, the AI recommends something like this. If you adjust the air exchange rate to XCFM, cubic feet per minute, for the next 90 minutes and slightly increase the supply air temperature to 58 degrees instead of 56, you will reduce your energy cost by Z amount, while keeping the interior temperature in Zone 4A within the preset comfort range of 70 to 72 degrees.
Wow, that's the power of the optimization loop. The system is constantly balancing those two preset ranges, the cost minimization range and the occupant comfort maximization range, using these predictive models.
Exactly. It's making unbiased recommendations that a human professional who is facing a lack of bandwidth and conflicting demands simply couldn't derive in real time.
And that leads directly to the second massive benefit, which tackles the massive capital expenditure side of the problem.
Yes, anomaly detection and predictive maintenance. If you're running these massive, complex mechanical systems 24/7, things are going to break.
And that's usually where the biggest unexpected costs come from, right? Reacting to a catastrophic failure is always more expensive than fixing a small problem before it escalates.
Always. And the research confirms that AI is essential for spotting these issues proactively. It enables detailed anomaly detection within facility systems.
What does that mean in practice?
It means it provides effective and efficient notification of emergent conditions, specifically including impending equipment failure.
So it can see the future, in a way.
In a way. For example, if a large centrifugal chiller starts vibrating, the change in that vibration frequency might be so subtle that human monitoring won't notice it until the bearing is actively failing.
And by then it's too late.
The AI, on the other hand, is processing the real-time vibration sensor data against thousands of previous maintenance records for that specific model of chiller.
So it knows what to look for.
It knows, and it can flag a tiny, say, 0.5% deviation in the vibration signature as a medium risk, impending bearing failure, 2 weeks before the component actually seizes up.
That is the holy grail of facility management.
It really is.
You move from reacting to a catastrophic, expensive failure, like a chiller completely dying on the hottest day of the year, requiring a huge rush order and massive overtime,
To getting an alert on your phone that allows for a scheduled, planned, far cheaper repair during normal working hours.
That saves massive amounts of money, it reduces downtime, and it prevents that inevitable wave of discomfort complaints that happen when a major system goes offline unexpectedly.
The AI, because it's processing data from thousands of previous maintenance records and real-time operational specs, can identify patterns that are invisible to the human eye.
And crucially, before they impact human productivity.
Exactly.
Finally, we have this idea of remote and unbiased management, which completely changes the daily operational workflow for the facility professional.
It absolutely revolutionizes their work environment. The research found that exploiting AI in facility operations allows these professionals to monitor, manipulate, and retrieve required maintenance data directly from their cellular phones or other remote devices.
So they don't have to be physically tied to a centralized building management system console in some basement control room to know what's happening or to make a quick fix, especially after hours.
Correct. The automated system provides real-time awareness of current conditions and alerts technicians to potential faults based on that anomaly detection we just talked about.
And they can actually do things from their phone.
It also allows the technician to perform a certain level of manipulation remotely to verify a set point, adjust a flow rate, or even temporarily override an operational anomaly until they can get on site.
Unbiased is a crucial word there that you used earlier. Human decisions can be influenced by personal experience. Last time this happened, I just turned the boiler up. Or by the loudest occupant complaint.
The squeaky wheel.
Right, the one person who emails repeatedly.
AI recommendations are based purely on weighted factors that are designed to meet the operational parameters defined by the organization.
It's balancing cost and comfort.
Not balancing who shouted the loudest. It removes that subjective element entirely. And the research stresses the absolute necessity for organizations to pursue this technology, not as a luxury, but as a strategic requirement for achieving comprehensive energy conservation and occupant comfort goals.
It seems like the $15 billion question really boils down to whether organizations will invest strategically in making their existing data streams smarter, using AI to connect the dots between the BMS, the CMMS, and that history of human discomfort.
Or continue to pay the accelerating price for being constantly reactive.
This has been a profoundly detailed deep dive into a problem that sits quite literally over our heads every single day.
It really has.
We started with the sheer scale of the problem. Roughly 40% of global energy used by buildings, translating to billions, at least $15 billion annually in the U.S. alone, lost through poor operational management.
We then connected that failure directly to lost organizational output. We highlighted how everything from excessive noise and inadequate lighting to that most frequent complaint, thermal discomfort, just fragments employee focus and their attention span.
And we established that a comfortable employee is a focused employee, and focus is probably the most valuable organizational resource there is.
Absolutely.
And we showed that the current model is tragically reactive, relying on that customer requirement loop, which only begins after the human occupant is already uncomfortable and already irritated.
And the power of AI, what we've seen in the research, lies in its potential to synthesize the massive amounts of historical complaint data, equipment operation data, and environmental sensor data to manage operations and maintenance effectively.
And this isn't just about saving utility money.
Not at all. It's about improving the long-term health, the productivity, and the attention span of the knowledge workers who work in these massive spaces. It's about optimizing the organizational resource that is most valuable, its people.
Which leads us to the final provocative thought about the future of the modern workplace, based on the findings of this research.
The current system, as we said, relies entirely on occupants to file a complaint, a structured record of a failure after they are already uncomfortable. So if AI successfully uses all this historical data to predict discomfort and autonomously adjust building settings, preemptively adjusting the airflow, tweaking the lighting spectrum, managing noise mitigation.
Before the human even registers the need to complain.
Yes. What does that mean for the future definition of workplace comfort?
That's a great question. We've always defined comfort by the absence of noticeable problems. You're comfortable if you're not thinking about being uncomfortable.
Right.
But if the building becomes truly proactive, if it eliminates the need for the complaint entirely, what level of predictive control will we accept, or maybe even demand, from the intelligent environments we work in?
And will the facility professional's role shift entirely from just fixing things that broke to managing an intelligent system that is designed to prevent discomfort from ever occurring in the first place?
That's the next chapter in facility management, and it's one that promises to save billions while making our workplaces fundamentally and measurably better for every single employee.
Welcome to the Deep Dive, the show where we take the densest research, the most complicated white papers, and the most comprehensive stacks of sources, and distill them down to the essential, fascinating, and actionable knowledge you need.
Today, we're tailoring this deep dive specifically for you, the learner who's fascinated by how technology is, well, fundamentally restructuring the spaces we live and work in, specifically large commercial office spaces.
Right, and we're looking at a systematic review of literature that really grapples with this constant, incredibly complex trade-off.
It's a big one.
And that trade-off is our core mission today. How can artificial intelligence, AI, fundamentally enhance the decision-making of facility professionals?
And these are the people who manage everything from the air conditioning to the elevator timing.
Exactly. So how can AI help them simultaneously improve energy management and satisfy occupant comfort?
It sounds like a pure engineering problem on the surface, but it's actually a really profound organizational conflict. Well, the continuous challenge for any facility professional is satisfying dozens, sometimes hundreds of different people in a huge commercial space.
And everyone has their own idea of what's comfortable. I'm always cold.
Exactly. And this goal, the happy tenant, it often directly conflicts with the organization's relentless need to, reduce energy consumption and cut costs.
And here is the initial nugget of truth that I think elevates this from just a utility bill issue to a core business strategy problem. The research is overwhelmingly clear on this. A comfortable, clean, and welcoming indoor environment leads to vastly more productive employees than conditions that are, irritating or uncomfortable.
It's just common sense, but the data backs it up. If you save, say, $10,000 a year on your utilities, but you lose $50,000 in lost productivity because people are too cold to focus.
You've failed the mission.
Utterly. Precisely.
The facility professional is managing the subtle physics of human productivity, all within the constraints of, physics and finance. It's incredibly high-stakes management. So before we dive into the nuts and bolts of energy systems and AI algorithms, we need a framework. We need a way to understand how a massive technological change, like introducing predictive AI, actually shifts the behavior of the professionals themselves.
Right, we can't just talk about the tech in a vacuum.
So here's where we start digging. We're talking about organizational change, and for that we turn to a specific theoretical lens known as adaptive structuration theory, or AST.
Exactly. We need a theoretical bedrock, a kind of advocacy lens that can frame how facility professionals might interact with cutting-edge technology like AI to enhance their decision-making.
Because we aren't just installing a fancy new sensor here.
No, we are changing how an entire profession operates.
I know AST has some pretty deep academic roots. It goes back to the structural theory of Anthony Giddens. But why is it the right tool for facility managers? Why drag a social theory into, building operations?
That's a great question, and it gets at a potential critique of the theory itself. AST was developed by DeSanctis and Poole back in 1994. And this was a time when industrial employers were rapidly implementing information and communication technologies, the original ICT revolution. And they realized something important.
Which was?
Merely installing the technology wasn't the hard part. The hard part was how the organization used it.
So the technology itself, the structure, it imposes certain rules. But the people using it, they adapt or they ignore or they even repurpose those rules.
You've absolutely nailed it. The power of AST comes from its dual vantage points. It lets you look at the structures provided by the technology, so the AI system itself, which dictates how data is organized and analyzed.
Okay, that's one side.
And then it looks at the new structures created by the actors, the facility professionals, as they interact with that technology. This interaction between the system's rules and the human's interpretation, that's the key to understanding success or failure.
And because this study uses AST as an advocacy lens, it's essentially saying, we believe AI can improve decision-making, and AST is the tool we're going to use to map out how that social change and professional enhancement has to happen.
That's the mission statement of the framework, exactly. We're tracking their adaptation process. And to do that, AST gives us 5 elemental concepts that define this whole interaction. Let's break down the first 2, which are the fundamental inputs. Structures and boundaries.
Structures are the building blocks, right?
Yeah.
The rules and resources.
Precisely. Structures are the specific rules, resources, or capabilities offered by an advanced information technology, a system, or even the organization itself. So think about the resources allocated to a task, or the organizational hierarchy, or the task itself, like maintaining a comfortable temperature.
In our specific case, the key structures we're examining are occupant comfort, the data repository where all the historical and real-time information lives, and then the introduction of AI as the advanced information technology.
Those are the inputs the professional is working with. And structures always exist within boundaries. Yeah. Right. These are the operational or conditional limits of those elements. These boundaries bind the users and the elements to specific parameters. For instance, a boundary on the occupant comfort structure might be the maximum capacity of your heating system.
You can't raise the temperature above what the system is physically capable of producing. Simple as that.
Exactly. So, okay, structures are the raw ingredients and the AI rules. Boundaries are the physical limitations. Next up, we have systems and appropriations.
Okay.
Systems are the social interaction between the actors, our facility professionals, and the inputs they're getting from those structures. When these actors start interacting with the technology and they perform tasks over and over, they start to create their own rules or limits for the system.
So the professional reads the data, they make a decision, and then that decision informs how they interact with the system next time. That creation of new internal rules is called appropriation.
Appropriation is the human element that transforms the rigid technology. It captures how facility professionals absorb the information from the AI recommendations and the data repositories. And crucially, it captures how they create new processes, maybe a new standard operating procedure or an emergent source of structure.
And it also reflects their attitudes, like positive or negative.
Oh, absolutely. If the AI is recommending energy-saving actions that just make the professional's job harder, the professional might appropriate the system by deciding to only check the recommendations twice a day instead of hourly.
That facility professional's adaptation process is so vital because it determines if the AI investment actually succeeds. They might take the AI output and develop a new checklist, a new structure source, or maybe a new communication method with the occupants.
Which leads us to the final concept. Outcomes. The outcomes are just the resultant changes we're trying to measure. In this case, that's energy management performance and occupant comfort satisfaction.
It's a continuous loop then. If we visualize this model, you have the structures feeding into the social interaction, which involves appropriation leading to the decision process.
Right, but the flow is critical. The professional's decision process leads to a decision outcome, but that outcome then feeds back into creating a new social structure because the professional learns and refines their appropriation.
So the success of AI hinges entirely on this feedback loop.
It does. The AI gives an unbiased, repeatable recommendation, but the professional retains the agency, the ability to review, interpret, and adapt the system based on their own wisdom.
That makes perfect sense. It validates the professional's experience while introducing this data-driven efficiency. But hang on, if AST is sometimes criticized for being a bit, well, overly optimistic about organizational change, doesn't that inherently color the results of this study? Should we trust a lens that might gloss over how hard this is to implement?
That's a really critical question, and it's why the latter sections of the source material focus so heavily on the roadblocks. AST provides the ideal path. It shows how successful appropriation should work.
But it's not always ideal.
Not at all. And the researchers acknowledge that successful appropriation is hard, precisely because the facility management context is so complex and deeply entrenched in existing, often messy, infrastructure. And that complexity is where we turn next, the foundation of facility management itself.
Okay, let's establish the context. We're focusing on large commercial office buildings. We know buildings provide shelter and employment, but the sources characterize them as much more than just a functional box.
Oh, absolutely. I mean, think about the skyline of any major city. Buildings are fundamentally organizational marketing tools.
How so?
They are signature structures used to advertise a company's stature, its stability, and, increasingly, its values. Organizations routinely advertise their internal workspaces, the fitness centers, the airy atriums, the climate-controlled floors. They're all symbols designed to attract and retain high-level talent.
So the building becomes a reflection of the corporate culture. If the air quality is poor or the thermostat is always arguing with the occupants, that sends a very negative message, regardless of what the company's mission statement says.
It's a very clear signal. But managing that signal means grappling with the building life cycle. Design, construction, operations, and maintenance, or O&M, and then finally, disposal.
And this brings us to the financial figure that, frankly, it shocked me when I was reading the source material. This is where it gets really interesting and illuminates the financial gravity of the decisions we're talking about.
Yes, the operations and maintenance, the O&M stage, it is unequivocally the most expensive and resource-depleting stage of the entire life cycle.
That sounds completely counterintuitive. You'd think the construction budget is the big number.
You would.
You're telling me that after all the millions spent on land, architects, steel, and glass, the actual middle stage is the financial black hole.
Precisely, and it's because of the timescale. A building's typical lifespan ranges from 50 to 100 years, so the longevity of that O&M phase is just staggering.
So what's the number?
Researchers found that an astonishing 80% to 85% of total building costs occurred during the operations and maintenance stage of the building life cycle.
Wow. Okay, let's just pause on that 85% figure. That's essentially saying the architect is building the cake, but the facility manager is paying for every single ingredient the cake consumes, plus the staff to serve it, for the next century.
It's an amazing way to put it, and it means that a seemingly minor improvement in O&M efficiency, say, a 2% energy reduction, translates into massive long-term organizational savings.
That 2% compounds over decades.
Yeah.
It totally validates why this mission of simultaneously improving energy and comfort is so critical. The financial stakes are huge.
They necessitate constant diligence and the most efficient decision-making possible.
And the people responsible for managing that 85% burden are the facility professionals. It's not just a handyman, it's an entire sophisticated ecosystem.
Correct. The profession is made up of managers, architects, a whole host of specialized engineers, electrical, mechanical, structural, and numerous tradespeople. They are supporting everyone in the building by keeping the facility in a functional state.
And their responsibilities cover what sounds like an impossible scope.
They do. I mean, we are talking about major electrical systems, the entire HVAC system, heating, ventilation, and air conditioning, vertical and horizontal transit systems, like elevators and moving walkways, all the plumbing, the custodial staff.
And the industrial control systems.
Right. And critically, the industrial control systems known as SCADA, or Supervisory Control and Data Acquisition. SCADA is what allows them to monitor and control those complex industrial processes like massive chillers and air handlers from a central point.
Managing that scope sounds less like facilities and more like running a small, highly technical city.
That's a perfect analogy. And because of the scope, the facility professional isn't just fixing things. They are primarily an information broker and a data gatekeeper.
What do you mean by that?
Well, think about the constant flow of information required just to manage outside service providers. Before a specialized HVAC contractor can even start work, they have to be vetted, introduced to the specific system parameters, and granted the correct data access according to strict organizational protocol.
So if the professional can't manage the information, the access, the data logs, the historical records, they can't manage the building effectively.
Absolutely. Communication and information management have been identified as among the most critical areas of FM. Improving that information exchange improves both daily operations and overall building performance.
And it's the sequence of micro adjustments that have the macro impact. You mentioned the example of changing an elevator's door open time to accommodate an occupant with a disability.
And that small decision, that single modification to a system's behavior, it directly impacts that occupant's experience and comfort. Hundreds of such adjustments happen every single day in large office buildings, from minor light sensor recalibrations to tweaking airflow.
And collectively, these sequences determine overall comfort, productivity, and eventually that massive O&M cost percentage.
Right. Without technological support, the scale of this daily decision-making is simply overwhelming.
That moves us logically into the core conflict. Section 3, the balancing act between occupant comfort and energy demand. We established that comfort is a key structure in the AST framework.
And comfort depends on the total occupant experience during any indoor activity. It is multifaceted, subjective, and frustratingly variable from person to person.
What's comfortable for one person is a drafty nightmare for another.
Exactly.
So let's list the key variables and their boundaries that the facility professional has to manage.
Okay, so you have the lighting level, where the boundaries are personal preference, bright versus dim. You have cleanliness and odor, the welcoming sensation versus the unwelcome smell. Noise intensity and duration, the sound of the HVAC system, chatter from other offices, maybe construction, and most significantly, temperature and airflow, where excess heat or cold almost universally and negatively affects productivity. These are the other sources of structure in our theoretical model.
And the goal here is to stop relying purely on subjective complaints, I'm cold, and start relying on objective data.
Right. And facility professionals are using incredibly sophisticated tools to track these dynamic, subjective variables. The first one you cite is BIM building information modeling.
I thought BIM was for architects, for designing the building.
It is, traditionally, but here it's repurposed. It integrates coordinated data throughout the entire life cycle, so for the facility professional, it serves as a crucial visualization platform, allowing them to see a pipe or a duct that's causing an issue in 3D space, and it's linked directly to operational data.
But how do they get the subjective data? The sources mention something called microecological momentary assessments. That sounds intensely technical.
It is, but the function is brilliant. This involves using wearables like smartwatches worn by the occupants.
Okay, so you're tracking people's comfort in real time.
In real time. They allow for the collection of immediate, subjective feedback on an occupant's comfort preferences, a real-time rating system. This reactive feedback is then aggregated and displayed on a decision-maker's dashboard, providing a real-time, granular preference profile.
So you're moving far beyond a generic thermostat reading in the hallway.
Miles beyond. And then there's the ultimate convergence tool, the digital twin. This seems to be the highest expression of integrating all this data.
What exactly is a digital twin?
A digital twin is a sophisticated virtual replica of the physical building. It incorporates the BIM data, real-time sensor data from thousands of points, and all that subjective occupant feedback from the wearables.
And then it does something with it.
Right. And crucially, it then applies a probabilistic model, often using highly sophisticated mathematical tools like Bayesian networks, to actually predict occupant comfort.
Okay, could you simplify that? What does it mean to characterize comfort as probabilistic rather than deterministic?
It means moving away from a simple deterministic question like, is the temperature 72 degrees? Yes or no? Instead, the Bayesian network uses historical data, occupancy patterns, and previous feedback to give the professional a forecast.
So it's like a weather forecast for the office.
It is. It says, based on the outside temperature and the current occupancy level, there is an 85% probability that the people on floor 7 will start complaining about thermal discomfort within the next hour if we don't slightly reduce the airflow.
Wow. It transforms the professional from a firefighter responding to a complaint into a forecaster who prevents the fire from starting.
That's a huge shift in capability. And all this data from sensors, BIM, smartwatches, and the digital twin models, it all needs to be housed and accessed. Which brings us back to the core data repositories, the original AST structures.
The CMMS and the BMS.
Right. The two primary repositories. Think of the BMS, or Building Management System, as the central nervous system of the building. It's the computerized network that monitors and controls all the mechanical, electrical, and plumbing, the MEP systems. The chillers, the fans, the electrical switchgear. It holds the historical data on the system's operational characteristics.
And the CMMS, the Computerized Maintenance Management System, what's that?
That's the patient's medical chart. It's the historical record, the massive searchable diary of the building. It stores operational characteristics, every single maintenance record, life cycle information, and, importantly, records of customer requirements and every technician's interaction.
So those two systems, often linked, provide the essential informational structures for any data-driven decision.
They're the foundation.
So that's the comfort side. Now let's layer on the second imperative, energy management.
Since the early 2000s, this has been driven by sustainability goals. Conserving energy involves monitoring usage, identifying waste, and of course, reducing costs. Historically, there was just an insufficiency of data to fully understand consumption changes in the built sector, which made efficiency optimization really difficult.
But modern technology is bridging that gap dramatically.
Oh, absolutely. We now see AI architecture enabling energy efficiency services by interlinking and enhancing those multilingual data repositories, the CMMS and BMS, with advanced machine learning and deep learning algorithms.
So these systems are designed to crunch massive amounts of historical data and propose solutions purely focused on efficiency.
Exactly. And we also see those BIM models being extended past construction and into post-occupancy use, serving as energy management platforms.
So the 3D model that helped design the ducts now helps facility managers identify where energy is being wasted or where system efficiency is degrading.
Precisely. But here's an important point. Even with all this technology, the research still highlights a critical human factor.
The appropriation.
The appropriation. Trained staff involvement from the planning cycle all the way through O&M overwhelmingly improves the energy and environmental performance of the systems. The AI is a powerful tool, but the human interpretation is still the core agent of success.
That is a necessary caveat. The technology doesn't manage itself. And this leads us perfectly into Section 4, why leaders should care. We've established the massive cost implications, that 80% to 85% O&M burden, and the constant struggle to balance energy and comfort. So what are the organizational consequences of getting this balance wrong?
The consequences of inadequate comfort conditions are massive, even if the financial correlation to profit isn't always linear.
I found that nuance interesting. Some research found that employee retention and productivity impacts do not directly correlate with corporate profit. It's hard to draw a straight line from a 1-degree temperature change to the CEO's bonus.
It is, because profit is subject to so many other things: market forces, sales cycles, global economics. However, the internal evidence is undeniable. Maintaining adequate indoor environmental quality correlates very strongly with employee output, satisfaction, and health.
So if you renovate an existing space and improve comfort,
you see immediate improvements in work performance and employee satisfaction. It's a clear link.
So while we can't say a better HVAC system guarantees a 5% profit increase, we could say a better HVAC system guarantees better focused employees.
Precisely. And those specific comfort elements are tied directly to performance. Thermal comfort, indoor air quality, office layout, noise, and acoustics. They all significantly affect occupant productivity.
So if the air quality dips, decision-making slows. If the noise level increases, cognitive performance degrades.
You've got it. And beyond keeping existing employees productive and healthy, there is the powerful factor of attracting new talent. As we discussed earlier, the built space is a marketing tool.
It's a passive advertisement.
It is. If the space is elevated in its comfort level, it satisfies existing employees who then share those positive experiences, becoming informal recruiters. It signals that the organization actively cares for its employees' day-to-day well-being, which is crucial in a competitive labor market.
And the research also notes that it's not just the internal elements of comfort that attract potential employees, but external comforts, like the surrounding public infrastructure and amenities, also play a key role.
Right. A facility professional managing an office tower in a great neighborhood has an advantage over one managing a building in a remote, amenity-poor location.
Finally, let's just emphasize the connection between comfort, task performance, and health.
Inadequate comfort causes unintended distractions,
which leads to insufficient task performance. I mean, a distracted employee, constantly focused on being too hot or too cold, is an ineffective employee.
And that ties directly back to health. Inadequate comfort has a documented health effect on employees. Missing days at work due to sick leave, whether directly caused by building systems or exacerbated by them, has a definite, quantifiable budgetary impact on organizations.
So the decisions made by the facility professional, while not medical, absolutely contribute to the occupant's overall well-being and, consequently, the organization's financial stability.
The stakes are incredibly high.
Which brings us to Section 5, the heart of the solution: decision-making frameworks and the AI enhancement. Given the staggering number of variables facility professionals must consider: health, safety, code compliance, environmental conditions, cost, funding, and comfort, it sounds nearly impossible to rely on a single framework.
It is exceptionally difficult. And that's why researchers found that the leading factors guiding decisions are often experience and expert opinion.
Which is valuable, but not always optimal.
Right. While we value wisdom, this reliance on intuition means biases, historical context, or a lack of real-time data can creep in, potentially sacrificing energy efficiency for perceived comfort. This is the exact management gap AI is intended to fill.
So let's look at the structured frameworks they currently rely on. The first is multi-criteria decision-making, or MCDM.
MCDM is used widely across the facility lifecycle, often applied to uncertain assessments. It involves methodologies like the analytic hierarchy process or top PSIs.
What's the core idea?
The core idea is that these methodologies highlight the usefulness of impartiality and neutrality when you're addressing multiple critical challenges, like assessing numerous energy management or maintenance options that all have different pros and cons. It provides a mathematical, neutral way to weigh your options.
And then there's the facility decision-making process, or FDP, which sounds like a systematic response to occupant requests.
The FDP is a 7-step process derived from the military decision-making process, and it's designed to provide a structured, repeatable way to respond to any occupant request.
So what are the steps?
It starts with receiving and logging the request, then moves to analyzing the problem in detail. Next, they develop decision criteria and a range of options. After analyzing and comparing those options, they present the recommended course of action, get approvals, and finally, they execute the action and document the solution so they have a blueprint for next time.
That sounds quite robust already. If that's the existing system, where does AI conceptually fit into this entire ecosystem?
In the conceptual framework presented in the sources, AI is proposed as a pending addition to that decision loop. And crucially, it enhances the process before the facility professional interprets the data. It does the heavy lifting of analysis and synthesis.
Okay, let's trace that new flow as it was visualized in the research. We start with the occupant comfort variables, lighting, thermal, noise, environmental factors, which feed data into the data repository, the CMMS and BMS systems.
That's the input side. Now, instead of the professional having to query the raw data repository and hunt for patterns or anomalies, the artificial intelligence block is inserted.
So the AI sits between the raw data and the human.
It does. The AI performs unbiased, repeatable data analytics, identifying correlations and potential solutions, providing clear recommendations or ranked faults back to the professional.
So the professional retrieves and reviews those AI-enhanced comfort conditions and additional boundary information, then interprets the data and makes the facility professional decision, which impacts the total energy demand.
And this is where the AST concept of appropriation is so clearly visualized. The professional still retains agency. The model shows feedback arrows flowing from the decision point back into the AI block and the occupant comfort block.
So they can alter the boundary conditions of the AI interpretations.
Exactly. Maybe telling the AI to prioritize comfort over energy savings for a week because there are high-profile visitors in the building. Or they can develop new appropriations, creating new processes informed by the AI's output.
So the AI doesn't make the final decision. It simply cleans, organizes, and analyzes the data so the professional can make a better, more confident, and faster decision.
And the ultimate feedback loop closes when the change in total energy demand leads to an increased or decreased energy cost, which provides feedback and also impacts overall occupant comfort, potentially starting a whole new data collection loop.
The purpose is radical efficiency through unbiased data analysis.
And in limited trials in other industries, AI has proven capable of dramatically improving data analytics, simplifying the interpretation of complex, massive data sets, and guiding actionable responses.
Let's get concrete. If I'm a CFO looking to invest, why do I need an artificial neural network when I have an experienced facility manager? What are the real-world examples showing why this AI enhancement is needed now?
The complexity and just the sheer volume of data make AI indispensable. Take work requests, for example. AI can provide automated prioritization of trouble tickets.
So instead of a human sorting through them all.
Right. One study developed a system that allowed facility professionals to quickly assign and respond to critical requirements, bypassing the typical bottleneck of a manager having to read and manually categorize hundreds of incoming complaints or alerts.
So instead of a manager spending the first 2 hours of their day sifting through a spreadsheet of trouble tickets, the AI sorts and ranks them instantly by severity, system impact, and occupant history.
Exactly. That's time saved and efficiency gained. Another powerful example utilized deep learning models to identify facility equipment and actually lead technicians remotely to failing fire protection systems.
Wow.
The AI learned the subtle degradation patterns of critical systems and could determine the order in which they should receive attention, proactively maintaining conditions before the system fails or occupants even notice an issue.
That is moving from reactive maintenance, just fixing what's broken, to true predictive maintenance, stopping it from breaking in the first place.
And the research goes even further with fault ranking. Researchers found that complex algorithms, artificial neural networks, support vector networks, and decision trees were the methods of choice for predicting and ranking the severity of faults in facility operations. They created an occupant-focused digital twin framework where the technology provides immediate awareness of condition changes.
Can you explain how a neural network performs that ranking compared to a traditional rule-based system?
Sure. A traditional system might use a simple rule. If temperature is above X and humidity is above Y, generate a fault ticket labeled medium.
Okay, pretty basic.
A neural network, on the other hand, is trained on years of historical data. We're talking sensor readings, outside weather, occupant feedback logs, maintenance costs, technician reports, everything. It learns that in certain combinations, say a specific vibration pattern in chiller 3 combined with a 2-degree variance on floor 12, that event always leads to a critical, expensive failure within 72 hours.
So it can then rank that fault as critical act now, even if the immediate system parameters look only mildly off.
Exactly. It's using pattern recognition across huge, diverse data sets to predict and rank severity, providing immediate awareness to professionals before occupants notice significant changes. That leap in capability validates the investment.
It certainly does.
It does. However, that capability, as powerful as it is, runs headfirst into reality. And Section 6 brings us to the crucial part of the study, the roadblocks, the challenges to AI implementation.
Scholars and industry leaders consistently identify 3 top factors affecting implementation: cost, data quality, and data security. And these aren't minor operational hiccups. They introduce unique and substantial business and operational risks.
Let's start with data security. We are talking about connecting complex Internet of Things, or IoT technologies, to absolutely critical facility systems.
That increases the attack surface dramatically.
It does. Protecting data is the first major challenge for IoT systems, closely followed by the threat of insiders introducing unauthorized code into the network, either maliciously or accidentally.
And we have to remember what we are protecting here.
Right. We're talking uninterruptible power supplies, electrical switchgear, massive chiller plants, cooling towers. These systems cannot go down or switch to manual operation without risking major organizational disruption. Their compromise constitutes a substantial existential risk to the entire operation.
And this risk is especially amplified in facility programs, because you have to use outside tradespeople for specialized maintenance.
Precisely. These tradespeople, highly specialized as they are, often connect their own IoT devices, diagnostic tools, laptops, gauges to the building's network for temporary data collection. This simple act may compromise the integrity of the building systems, accidentally or by design, opening the door for faults in essential systems.
So it requires a whole new layer of cybersecurity protocol that FM staff may not be equipped to manage yet.
Exactly. The second major hurdle is data quality. Deep learning algorithms are notoriously sensitive. They are only as good as the information they are fed.
Garbage in, garbage out, as they say.
It's the perfect way to put it. And facility management has a long, difficult history with data standards. For many years, facility managers operated using handwritten notes, log books, or unstandardized printed forms. Transitioning from that historical reality, a messy stack of paper and tribal knowledge, to standardized, data-driven processes requires significant time, money, and organizational resources.
So the data that exists, the historical record in the CMMS, is often not clean enough to feed an AI.
Exactly. Deep learning algorithms require vast amounts of clean, standardized data for training and effective operation. Data quality is a massive concern for FM leaders. While some researchers have successfully developed algorithms to convert old 2D paper drawings into 3D information models, the initial training of AI technology still requires significant data processing time and effort to standardize all this disparate historical input.
It's a massive cleanup effort before the AI can even start analyzing.
It is. Finally, let's address cost. Leaders need to see a working cost model and a defined return on investment, the ROI, before they commit to these massive technological overhauls.
And that's the sticking point.
And that is the crux of the financial financial friction. Leaders currently lack a fully developed working cost model for comprehensive AI implementation in the FM space. This makes the total investment a significant, unquantified financial risk in a budget already burdened by that 85% O&M cost.
Why is it so hard to develop a generalized cost model for AI and FM? Surely they can approximate it.
Well, it's because AI technology is not a one-size-fits-all product. It can be implemented in systems of widely varying scopes and sizes. A small, single-tenant facility might only require a few specific AI algorithm models focused on HVAC optimization.
But a massive corporate campus is a different story.
A completely different story. It might need dozens of bespoke integrations requiring customized data pipelines to link 10 different systems. Without knowing the specific need and scope, the number of sensors, the existing data mess, the legacy systems involved, it is exceptionally challenging to develop a reliable cost-to-benefit ratio that organizational leaders require before approving major investments.
So the technology is proven to work dramatically in limited controlled scenarios, but the obstacles of security, the data cleanup effort, and the complexity of cost calculation are what slow down widespread adoption across the built environment.
It is the friction between the ideal theoretical model of efficiency and the messy, expensive reality of retrofitting and maintaining technology in 50-year-old physical infrastructure.
That wraps up our extensive dive into the complex world of AI, comfort, and energy management. We started by navigating the complexity using the adaptive structuration theory lens, which allowed us to view the technology and the human professionals' necessary adaptation process, their appropriation, simultaneously.
We established the profound financial stakes in the operations and maintenance stage, where 80% to 85% of total building costs accumulate over decades. We detailed how AI, utilizing powerful tools like digital twins and machine learning, is proposed as an unbiased, repeatable decision enhancer.
Right, improving the existing decision loops used by facility professionals, moving them from reactive firefighting to predictive forecasting.
And finally, we discussed the critical real-world challenges, the threats to data security from complex IoT integration, the demanding requirements for clean, standardized data, and the lack of a standardized cost model that organizations must mitigate to successfully transition into the age of intelligent buildings.
And that brings us to our final provocative thought for you to consider as you move forward. We know AI promises enhanced, unbiased, and instantaneous decision-making, offering clear, data-driven recommendations that optimize for both energy and comfort.
Yet the professional, drawing on decades of experience, their earned wisdom, retains the power of appropriation to adjust boundaries and override the system.
So as these AI systems become more prevalent in our daily environments, providing solutions that prioritize long-term, systemic optimization, how much weight should be placed on a facility professional's experience and intuition when the AI recommends a course of action that seems counterintuitive or even slightly uncomfortable in the short term, but is entirely proven and driven by vast amounts of data?
The balance between human wisdom and data optimization is not just the next frontier of facility management. It is, I think, the ultimate challenge of integrating human-focused technology into any organization.
Thank you for joining us for this deep dive. We hope this has equipped you with the essential knowledge to navigate the future of intelligent buildings. We'll see you next time.
Welcome back to the Deep Dive. Today, we are undertaking a very special kind of analysis. We aren't just looking at the conclusions of a research project. No, we're looking at the blueprint, the DNA of how the best conclusions are even generated.
Yeah, the how.
Exactly. We have a set of source documents that are, well, they're basically a masterclass in evidence-based decision-making. And this is all focused on a really high-stakes challenge for modern commercial real estate.
It really is.
How to effectively use artificial intelligence to balance those aggressive energy conservation goals with the non-negotiable requirement of keeping people in the building comfortable.
That's absolutely right. Our mission today is really to unpack the entire methodology of what's called a systematic review.
Okay.
And for you, learner, this is the essential stuff. You want knowledge quickly, sure, but you also want it to be thorough. And this material, it shows the extreme rigor that's required to make sure that any recommendations,
right,
be it about AI models or specific strategies, that they're trustworthy, that they're truly built on the best available evidence. We're going deep into the how and the why this research avoided bias, starting from the ground up.
Okay, let's unpack this then, because before we can even get to the AI or the, building controls, we have to start with the philosophical foundation of it all, the idea of evidence-based decisions. Because look, If a facility leader is going to sink millions of dollars into new tech, they have to know the research guiding it is sound.
Absolutely.
And that all begins with something called evidence-based management, or EBM.
EBM is it's the foundational discipline here. It provides the structure for critical thinking and management, sort of like how the scientific method guides research in a lab.
Okay, so it's a framework.
It's a framework, exactly.
Mm-hmm.
And the source leans on this definition from Behrens and Rousseau, who define EBM as making decisions through the, and I'm quoting here, conscientious, explicit, and judicious use of the best available evidence.
I think we need to slow down on those three words because they feel really deliberate. It's not just use evidence.
Not at all.
It has to be conscientious, meaning you're aware of what you're doing, the implications.
Right.
It has to be explicit, so you're transparent about your data, your process.
Mm-hmm.
And judicious, which means you have to use good judgment in how you interpret and apply it all. So if those are the ingredients, what's the so what for the person running a massive facility?
Well, what is profoundly practical, it's at its core the primary strategy for risk mitigation and resource allocation.
Okay, risk mitigation.
Think about it. When a leader, whether it's a CEO or a chief facility officer, makes a decision, it directly impacts enormous organizational resources.
People, money, buildings.
People, physical structures, systems, huge financial investments. By conscientiously seeking out and applying the best evidence, not just some evidence, you dramatically increase the likelihood of achieving your goals.
Your positive outcomes.
Your anticipated positive outcomes, exactly.
Yeah.
EBM is like the organizational guardrail designed specifically to mitigate that inherent risk that comes with any major decision.
That makes perfect sense. If you just rely on anecdote or, the way we've always done it, you're just introducing uncontrolled risk into the equation.
You really are.
But I want to challenge this a bit. The sources note that the scholarly landscape of evidence includes input from professional experience. And we're talking about facility managers with 30 years of skin in the game.
Sure.
So if EBM includes professional experience, why bother with this whole complicated systematic review? Isn't that seasoned, expert gut feeling enough for a 30-year veteran?
That is a great question. And it gets to a fundamental tension, I think, in EBM. The core belief is that neither academic study nor experience alone is sufficient.
Okay.
That professional experience, that gut feeling, it's invaluable. It's invaluable for understanding the context of a problem, the political realities of implementing a solution. But experience is inherently limited. It's limited by what that one individual has personally encountered.
Ah, I see. It's a sample size of one.
It is. So what EBM provides and what the systematic review delivers is the ability to integrate that localized personal experience with the accumulated, tested, validated, and peer-reviewed experience of hundreds of other experts from all over the world.
So it guards against your own biases?
It guards against confirmation bias, against the belief that just because something worked once in your building, it will always work everywhere. Yeah. When you combine the best available evidence from research with the professional judgment of that veteran manager.
That's where you get the most robust decision.
That's where you get a much more robust, defensible, and reliable decision. A true synergy.
So the professional provides the practical lens, and the systematic research provides that global, objective view.
Okay.
And to make this repeatable, the source details these systematic steps, the 6 A's. This sounds like the operational roadmap for that risk mitigation you mentioned.
It is. It's the cycle of continuous evidence-informed decision-making. First up is asking.
Asking.
You have to start with a precise, well-defined question. If the question is vague, like should we use AI, the evidence you gather will be just as vague. The ask has to be super specific, which we'll see with the SIMA framework later on.
Okay, so a good question is step one.
Step one. Then comes acquiring. This means gathering the evidence from diverse, multiple sources. It's not just a few quick Google searches.
Right.
It requires a structured multi-database approach, which is really where the systematic review methodology shines.
Okay, so ask, acquire. What's third?
Appraising. This is the critical gatekeeping step. You have to rigorously judge the quality and relevance of everything you acquired.
So you're filtering out the junk.
You're filtering out the junk. Is the study methodologically sound? Is the data clean? This is where low-quality, biased, or just poorly executed studies get thrown out.
Got it. And after appraising.
Aggregating. Once you have your pile of high-quality evidence, you synthesize it. You bring all that validated data together to find the overarching patterns, the trends, maybe even the conflicts in the research.
And then you use it.
Then you use it. Step 5 is applying. This is the action phase. You use those synthesized findings to actually make your decision. For a facility manager, this might mean designing a new control scheme or buying a specific software package based on the evidence.
And the loop has to close.
Yeah, the loop closes with number 6, assessing. You have to evaluate the outcome of your application. Did that AI system actually meet the energy reduction target while keeping people comfortable? The results of that assessment then feed right back into the first step. It refines your next ask.
So if I'm running, say, a $10 million AI implementation project, this EBM framework gives me an audit trail. I can justify every stage by pointing back to these 6 steps.
That's a great way to put it. It turns decision-making into an audit trail. And again, the scholarly landscape of evidence that feeds this whole thing is broad. It's peer-reviewed studies, yes, but also professional experience, observations, stakeholder input.
Right.
The fact that EBM relies on practitioner insight is what keeps it from becoming just, academic theory disconnected from the real world.
Okay, so if evidence-based management is the philosophy of why we need the best evidence, then the systematic review is the methodological solution for how to get it, with the highest possible rigor. So why is this considered the gold standard research design for EBM?
The term gold standard really comes from its explicit design to prevent bias and ensure transparency. As Go and his colleagues described it, it's a proven research method for delivery of evidence-informed decision-making.
Okay.
Think about the difference between this and, say, a standard literature review.
Yeah.
In a standard review, an author won't be highly selective. They read 20 papers and maybe only choose the 5 that best support their pre-existing argument.
Right, they're cherry picking.
They're cherry picking. A systematic review is the complete opposite. It's rigid, it's predefined, it's transparent, and it's totally repeatable.
Repeatable how?
It forces the researcher to define their search terms ahead of time, document every single database they searched, publish their criteria for including or excluding an article, and formally appraise the quality of every single one.
Ah.
So if another researcher followed your exact recipe, they should arrive at the same collection of articles. That level of transparency is what elevates it to the gold standard.
And the specific goal of the review in our source material was very focused on solving a real persistent problem in commercial buildings.
Absolutely. The problem is that complex balancing act we mentioned between 2 goals that are often in conflict. Improving energy management, which is really about cutting costs, and satisfying occupant comfort, which is about preventing complaints and maintaining productivity. The research aimed to inform leaders specifically on how AI can enhance the decision-making of facility professionals, helping them interpret the massive amounts of data coming from their building systems.
Right, because there is a gap in the literature.
A huge gap. The researcher noted that while there are lots of individual studies on specific things, like one study on machine learning for chiller optimization, another on deep learning for lighting control.
Right. Very siloed.
Very siloed. There wasn't a high-quality collective synthesis that tied all these disparate findings together into actionable guidance for leadership. So the systematic review was essential to aggregate only the highest quality studies to provide that holistic, trustworthy answer.
So let's look at the structure itself. The systematic review process, as it's broken down in the source, it's basically a 7-stage anti-bias workflow.
That is a perfect way to describe it. The whole process is designed to stop the researcher from making arbitrary choices.
So what's step 1?
Step 1 is review initiation. This starts with forming the team and, crucially, engaging stakeholders. It's the initial reality check.
To make sure you're solving a real problem.
Exactly. To make sure the problem you're studying, AI and energy versus comfort, is a real problem for the industry, not just a theoretical one.
Okay, so you confirm the need, then?
Then comes review question and methodology. This is all the strategic planning. You formulate that precise CMO question, which we'll get into, and you build your conceptual framework. This step defines the boundaries and the theoretical lens for the whole project.
Right, the rules of the game.
The rules of the game. Third is the search strategy. This is the acquiring stage we talked about. It involves running highly specific searches across multiple databases and meticulously screening every potential article using those strict eligibility criteria you just defined.
And it has to be exhaustive, not selective.
Exhaustive, not selective. Then description of study characteristics. Once you have your eligible articles, you start to operationalize the data by coding the study characteristics.
Wow.
What was studied, who was involved, where did it take place? You're building a map of the evidence.
Okay, and step 5 sounds like the most important one.
It's the crucial gate, quality and relevance assessment. Here, you apply critical quality appraisal criteria, like the TAP-UP-Assess framework we'll discuss, to determine which studies are actually trustworthy. A study might seem relevant, but if it fails the quality check, it's out.
No exceptions.
No exceptions. Then synthesis. You bring all the high-quality coded data together. Using your framework and your quality judgments, you synthesize the patterns to generate coherent findings.
And finally, you have to make it useful.
Finally, using reviews, interpretation, and communication. The findings have to be translated into clear, actionable recommendations and communicated to stakeholders in a format they can actually understand and use.
It's an accountability machine. I love that. Every step is documented. So if a leader asks, hey, why did you include this study but not that one? The answer is never because I felt like it.
Never. The answer is because it failed to meet the specified quality criteria for accuracy or whatever the reason was.
Yeah.
That transparency, that explicit documentation is the core of what evidence-based management demands. It turns the whole thing into a science.
Okay, so we've established that the systematic review is technically sound, incredibly rigorous, but the sources are also honest that this process, it faces some real-world friction, especially when it has to interface with busy executives.
There's what's called the practitioner gap, and the first major challenge is something called interpretation capacity.
Interpretation capacity, what's that?
Systematic reviews are, well, they're inherently academic. They use specialized terminology, complex stats, theoretical frameworks. The source argues these reports are often written in a way that only a few highly specialized readers can truly understand them and apply the information.
So if the chief facility officer can't immediately figure out what it means, the report just sits on a shelf.
It gets shelved, and all its practical value is lost. It's the ultimate irony. The best research is often the least accessible.
Right. And the second challenge is something every organization deals with. There's just never enough time.
Absolutely. Time constraints. A detailed, well-planned systematic review isn't a weekend project. We're talking months, often a year or more, to do all those rigorous steps correctly, especially the quality appraisal and synthesis.
And business leaders don't have that kind of time.
They often lack the luxury of waiting for the definitive answer. The source observed that this pressure for speed causes managers to, and this is a quote, stray away from these long, rigorous studies, even though they prefer to have researched recommendations.
So there's this constant agonizing tension between the need for speed and the need for precision.
A huge tension.
Which sets up a great narrative for this specific study we're looking at. They had to execute a gold standard review, but they also had to make sure the final product was practically indispensable to the facility management community. So how did they bridge that critical practitioner gap?
They systematically integrated the human element right from the start by recruiting industry professionals, subject matter experts or SMEs. And this is a methodology recommended by experts like Creswell and Creswell. And the SMEs weren't just, token participants. They were involved from the very beginning of the research design to make sure the question was relevant and the findings would actually be applicable in the real world.
So let's talk about that initiation process. Before a single database was even searched, the researcher went into the field.
Yes, deep groundwork. They attended industry conferences, spoke directly with facility managers, IT professionals. They were in webinars, reading what's called gray literature.
Yeah.
Technical reports, white papers, things that aren't peer-reviewed but reflect current industry challenges.
And that reconnaissance confirmed the problem.
It confirmed that the most pressing and complex practical challenge was in fact that balancing act of satisfying occupants while conserving energy, mostly because of the vast, complex, and dynamic variables in any commercial building.
That real-world input solidified the need, and then they formed the expert panel. We have to talk about the credentials of these three individuals because it's a really formidable cross-section of expertise.
Oh, the panel was meticulously designed for practical relevance. Expert 1, for example, had a Doctor of Business Administration.
So they get the business side.
They get the high-level decision-making context.
Yeah.
And they served as a Director of IT Operations and Chief of Engineering, Construction, and Facility Management.
Wow, okay. So one person covers business strategy, IT infrastructure for the AI, and the operational reality of the physical building.
All in one.
Yep.
That person provides the strategic and financial critique, but then you have to get into the technical weeds.
Where the rubber meets the road.
Exactly.
Yeah.
Expert 2 was a mechanical engineer, a facility operations expert, and crucially, a facility DDC expert.
DDC, that's direct digital controls.
Direct digital controls. This is the sophisticated networked system of computer microprocessors that actually operates the building's physical machinery. The pumps, the valves, the dampers.
So without a DDC expert, any AI finding is just theoretical?
It stays theoretical. DDC is essentially the building's operating system, and the AI has to integrate with that layer. And rounding out the panel was Expert 3, an electrical engineer, also a facility BDC expert, and a facility electrical and operations expert. The combination of mechanical and electrical systems, both run by DDC, meant this panel could critique the findings from the perspective of real-world installation, maintenance, and all the failure points.
So that is a triple threat panel designed to make sure the recommendations are not just accurate, but actually implementable.
Yes.
But here's what I think is the most important part, the rigor check. The researcher themselves had over 30 years of facility operations experience. How did they use this panel to monitor and control for their own potential confirmation bias?
That's a critical point. The structured method was necessary precisely because of the researcher's deep expertise. Someone with that much experience might, inadvertently favor findings that align with what they've seen in the past. The expert panel served as the formal external monitor. The process was painstaking. Personal contact, detailed packets explaining their roles and the scope, a specific questionnaire. And crucially, their feedback was used to review the initial findings that came out of the review.
So if the research said one thing, but the panel said, that's not going to work in the real world,
because of X legacy system limitation, then the researcher had to formally reconcile that conflict. This constant structured challenge ensures objectivity and stops the whole project from just validating the researcher's pre-existing knowledge.
Okay, so the foundation is EBM. The external validation is the SME panel. Now, the entire project hinges on having a single laser-focused question. And this is where SEMO logic comes in to provide that systematic framework.
SEMO logic is essential for turning a broad area of interest, like AI in buildings, into a manageable, searchable, and specific research question. It stands for context, intervention, mechanism, and outcome.
CIMO.
Right. And if you miss one of those factors, your whole search strategy can just fall apart.
So let's break down how they applied those factors to this study.
Okay, so the researcher identified the key components. The intervention is, what are we introducing? That's artificial intelligence.
Got it.
The mechanism, M, is how does it change things? It enhances the decision-making of facility professionals, specifically their data interpretation.
Okay, so AI helps people make their decisions.
Right. And then the context outcome, CO. Where does this happen and what's the result? Well, it's about improving energy management. That's the cost benefit. And the other required piece of the context is satisfying occupant comfort.
So you can see how if you changed any of those, the whole question would shift.
Completely. If the intervention was installing smart windows instead of AI, the entire search strategy changes. If the outcome was structural resilience instead of energy and comfort, everything would be different. CO mode just locks down the variables.
Which resulted in the exact research question that guided every single step. How can AI enhance the decision-making of facility professionals to improve energy management while satisfying occupant comfort?
That's the one.
So once that's locked in, the search strategy has to be equally precise.
It does. The initial phase was a massive scope review. The researcher actually reviewed the written descriptions of 95 different library databases just to select the ones that specialized in engineering, IT, and business management, the 3 pillars of the question.
95. That commitment to a holistic search shows they were trying to capture everything. But then came the critical anti-bias step, consulting the expert librarian.
And that step was non-negotiable. The researcher initially developed a narrow search string, but even that limited search returned an astonishing 8,852 articles.
Wow.
And that was from just the one search database. Imagine multiplying that across all the relevant databases. The volume is immediately overwhelming, impossible to manage effectively.
Right. If the researcher tried to tackle that alone, they'd have to introduce their own bias just to get through it all.
Absolutely. So the librarian's assistance was crucial to structure and narrow the search string into something manageable, ensuring maximum coverage with minimum noise. And the key tool was Boolean logic.
Right, the A and Ds and ORs. Let's not recite the whole dense string, but what were the strategic components?
Well, the strategy is key. To capture the whole concept of the intervention, they didn't just search for AI. They used artificial intelligence, or AI, or machine learning, or deep learning.
So it's casting a wide net.
A very wide net. And for the outcomes, they had to be just as thorough, covering both comfort and the systems that deliver it. Occupant comfort, or thermal comfort, or temperature, or heat, or cool, or air condition, or HVAC. That little asterisk is a truncation symbol, so it captures words like temperatures and heating without having to type them all out.
Smart. And then there's this key operational step, connecting the energy context with the cost or use outcome using a proximity operator, N10.
This was a brilliant strategic move. They combined terms like energy or utilit or electricit with cost terms like cost or expend or spend or use or usage or consume using that N10 operator. This tells the database to only return articles where the energy term and the cost term appear within 10 words of each other.
So it makes sure they're actually being discussed together.
Exactly. It eliminates articles that might mention energy on page 1 and cost on page 20 in a totally unrelated context. It ensures the concepts are linked, which is vital for the core research question.
That is a masterclass in query structure. So once the query is perfect, the next step is setting up the strict boundaries of the evidence base using inclusion and exclusion criteria.
Right, and these criteria define exactly what the final recommendations apply to. The inclusion criteria were tight, designed to focus on modern facilities, strictly peer-reviewed articles, commercial buildings, specifically mentioning open floor plans.
And the date constraint was critical for a tech study.
The most critical. Articles had to be published between January 1st, 2018 and December 31st, 2023. A firm 5-year window. The pace of AI development just dictates this. Any research before 2018 would likely be based on less sophisticated algorithms or concepts that are now obsolete.
So it keeps the evidence base current.
Rooted in the most current, relevant technology. And the exclusions further refine the scope.
Right, they were.
The two key exclusions were non-English language articles, and any articles focused on commercial buildings outside the continental United States.
And these limits ensure consistency.
They do. If you include global studies, you introduce massive variables. Different climate standards, building codes, energy prices, utility regulations. It would make a coherent synthesis almost impossible to trust for a U.S. facility leader. The exclusion criteria make the research highly relevant to its defined audience, even if it limits global generalizability.
Okay, so once that massive search engine work is done, you have a curated list of, I assume, hundreds of potentially relevant articles. This is where the systematic review goes from acquisition to quality control, and the process follows the Prisma flow diagram.
Which is the industry standard for transparent reporting. And the flow is meticulous. First, you have to handle the sheer volume. Articles were batch downloaded into organization software Mendeley Desktop. The very first screening step is just removing duplicates. You'd be amazed how many identical articles show up across 5 different databases.
I can imagine. So after the duplicates are gone, the human element comes back in to apply those criteria we just talked about.
Exactly. The records were then screened against the explicit inclusion and exclusion criteria. U.S. only, commercial buildings, 2018 to 2023, and so on. Finally, there's an eligibility screening where you have to read the abstract of every single remaining article for more detailed information.
And only the ones that pass all those hurdles move on.
Only those articles get retained for the deep analysis, which culminates in the ultimate test, the quality appraisal.
And this appraisal is really what separates a systematic review from any other kind of literature review. It's not enough to find an article. You have to prove it's good science. And the methodology chosen here was the tap-you-paste quality appraisal approach.
You can think of tap-you-paste as the gauntlet of rigor.
Chuckles. The gauntlet of rigor. I like that.
It's an acronym. Transparency, accessibility, purposivity, utility, propriety, accuracy, and specificity. It's a framework adapted from Long and his colleagues back in 2006, specifically designed to appraise the ethical conduct and methodological rigor of any kind of research, qualitative, quantitative, or mixed methods.
So it ensures every single included article is robust across 7 distinct dimensions. Let's dig into those because they are the gates every piece of evidence has to pass.
Okay, first is transparency. Is the knowledge generation process explicit and clear? Can you, as a reader, fully trace the author's logic from their question to their conclusion? A lack of transparency might suggest hidden methods or biases.
Makes sense.
Second, accessibility. Does the research meet the needs of those seeking the knowledge? Is the language clear? Could a facility manager actually understand it and derive practical knowledge from it? If it's too theoretical or full of jargon, it fails on utility.
Okay, what's purposivity?
Did the author actually achieve the stated aims and objectives of their original research? If a study set out to prove X and instead concluded Y without a clear explanation for the pivot, it might lack purposivity.
Got it. And utility.
Is the research appropriate for the decision-making setting? Does it provide practical, real-world answers to the problem of AI optimization in commercial buildings? If it's just a lab simulation, its utility for a manager is low.
Right. And propriety sounds like an ethics check.
It is the ethics check. Did the researchers get organizational or ethical approval, like from an IRB, an institutional review board? This is critical for any research involving human data or organizational policies.
And the last two are accuracy and specificity.
Accuracy asks, are the claims made by the authors actually based on the data they collected? Or are they making huge leaps of faith? And specificity asks, does the research apply source-specific standards relevant to its field? Does an engineering paper apply accepted engineering standards?
That is a comprehensive checklist. It covers everything from ethics to practicality. But the scoring mechanism for these 7 factors is where the rigor becomes absolutely brutal.
It is. They used a simple 1 to 3 Likert scale for each factor, but the definitions were really specific. A score of 1 meant does not meet, no mention of the item. A score of 2 meant minimally meet, it's mentioned but not really used, or it lacks detail. And a score of 3 meant exceeds. It's mentioned, it has robust detail, and it's used to drive the research.
So the highest possible score is 21, but the inclusion threshold wasn't just about a high total score, it was about uniformity.
This is the absolute core of the quality assurance. An article needed an overall score of 14 or greater to be included. So it had to average at least a 2 across all 7 factors. But here's where it gets really interesting.
Okay.
The source emphasizes this crucial secondary rule. For an article with a score above 14, no single quality factor could score below a 2.
Wow. Okay, so let's play that out. An article is brilliantly written. It has high accuracy, a 3, high utility, a 3, high specificity, a 3. It scores 3 across 6 factors, so that's 18 points, well above the 14-point threshold.
Right.
But if that article completely fails to mention ethics or IRB approval propriety and scores a 1, it's immediately eliminated.
Immediately eliminated, no questions asked. That enforces methodological uniformity. The researcher is stating very clearly, we will not include research that is critically flawed in any single aspect, even if it's brilliant in others.
That makes so much sense.
A study could have phenomenal data, an accuracy of 3, but if it lacks propriety, an ethics score of 1, its entire trustworthiness is compromised. If a researcher can't tell us how they maintained ethical standards, how can we possibly trust their data interpretation?
Right.
This level of rigorous elimination ensures the final synthesized evidence base is robust across all 7 required aspects of scientific and ethical rigor.
Okay, so once the articles have survived the gauntlet of rigor, past that strict tap-you-pay-us appraisal, the analysis phase begins. This is where you take all that raw text and turn it into something meaningful and actionable through coding.
Coding is the bridge from raw data to insight. It's defined as assigning a short phrase or a word to a portion of data. You're basically operationalizing qualitative information to answer your research question.
Hey, I mean, you have 20 high-quality articles, each thousands of words long. You can't just mash them together.
No, you have to break them down into their component ideas first. And the source outlines a really clear hierarchy for this, like a funnel. First cycle coding category, second cycle coding, thematic analysis.
Let's use an analogy. Maybe it's like trying to synthesize the world's best recipes for a specific cuisine.
That's a great analogy. So first cycle coding or descriptive coding is the foundation. You're reading the articles and assigning simple labels to passages, words, phrases. Things like HVAC optimization, predictive maintenance, user interface, or energy savings metric.
So in the recipe analogy, you're just labeling all the raw ingredients: flour, sugar, salt, egg.
Exactly.
Huh.
And this review used a blend of 2 crucial coding approaches, deductive and inductive.
Okay, what's the difference?
Deductive coding uses a pre-existing framework. Since the research was guided by that CMO model and the conceptual framework, the researcher deduced that codes related to occupant feedback, machine learning algorithms, and real-time data would probably show up.
So you're looking for things you expect to find.
Right. But they also used inductive coding. These are codes that arose organically and unexpectedly from the text itself. If the articles repeatedly discussed a concept the researcher hadn't planned for, say vendor training gaps, that concept gets labeled and tracked.
That makes sure you don't miss anything surprising.
It ensures that the findings capture not just what was expected, but also the surprising relationships that emerge naturally from the data. And to manage these thousands of labels, they use software. Right, Atlas TI. And this is essential because once you have thousands of these little first cycle codes, you need a way to organize them, search them, and see their relationships visually. The software helps you discover those deeper patterns.
Which leads to second cycle coding developing categories. This sounds like moving from the ingredient list to grouping them into types of dishes. Like these are all the ingredients for cakes, these are for breads.
That is a perfect way to put it. This is where you synthesize or combine the data into new assemblages.
Mm.
Categories act as umbrella codes that express an overarching concept.
Can you give an example?
Sure. All those descriptive first-cycle codes like HVAC optimization, predictive maintenance, and sensor calibration might all get grouped under the umbrella category of, say, AI-enhanced facility system reliability.
I see.
The researcher develops these categories by actively looking for commonalities among the codes and the underlying quotes, always through the lens of their framework. You're synthesizing granular data into these manageable, coherent concepts.
And those categories then build into the final, most abstract layer, the themes. This is what the decision makers ultimately read.
The themes are the patterned responses or meanings in data. They're the most abstract layer, providing the deeper meaning, interpretation, and integration. For instance, several of those categories might lead to a final theme like the integration of AI necessitates a shift from reactive maintenance to proactive system tuning.
So it's the big takeaway.
It's the big takeaway. These final themes, developed using the categories, the framework, and the research question, are what lead directly to the actionable recommendations for leaders. You start with tiny labels, and you end with robust, evidence-supported answers.
Okay, so we've established the rigor required to produce the findings through all that screening and coding. But there's one final critical step. How does the researcher communicate to the facility leader how much confidence they should actually place in those synthesized themes? And that's where the See or Qual framework comes in.
You can't just present the findings. You have to present the trust level. A systematic measurement of confidence is non-negotiable for transparency and trust. And CIRQUAL, which stands for Confidence in the Evidence from Reviews of Qualitative Research, is a structured, systematic framework specifically designed to evaluate and determine confidence in findings that have been synthesized from qualitative data.
So it forces the researcher to turn around and critique their own aggregated evidence base.
That's it, exactly. After months of rigorous analysis, the researcher has to assess the strength of the evidence backing their themes based on 4 primary components.
And what are those 4?
The first is methodological limitations. This looks backward at the primary studies that contributed to the finding. If a finding is supported by 15 articles, but say 10 of them only minimally met the TAPUPAS criteria for accuracy, that introduces methodological limitations, and that lowers the confidence in your synthesized finding.
Okay, so you're looking at the quality of your sources.
The quality of your sources. Second is coherence. This assesses how clear and cogent, meaning well-supported or compelling, the fit is between the data and the finding. Do all the pieces tell a consistent story?
Or are they all over the place?
Right. If 7 high-quality papers suggest AI improves comfort, but 8 other equally high-quality papers suggest the opposite, your coherence is low, and you have to address that conflict.
Third,
adequacy of data. This is a measure of the overall richness and quantity of data supporting the finding. Was the theme supported by hundreds of detailed quotes across 20 papers? That's high adequacy. Yeah. Or was it just a few brief mentions in 3 papers? That's low adequacy. Rich, dense data provides higher confidence.
And the last one is relevance.
The practical application check. To what extent does the evidence actually apply to the specific context of your research question? If a theme is mostly supported by studies done in small retail spaces, but your review is focused on large commercial office buildings in the U.S., the relevance score might drop, even if the data is accurate.
So that systematic assessment of flaws, consistency, depth, and context is incredibly comprehensive. And based on that, the findings get graded into one of 4 standardized confidence levels. This is the crucial translation layer for the executive who needs to make an investment decision.
Exactly. This standardization removes all the guesswork about reliability. A finding can be rated high confidence, meaning it's highly likely a reasonable representation of what's happening. The evidence is consistent, plentiful, relevant, and strong. A leader can confidently proceed.
Okay.
Or it could be moderate confidence. The finding is likely a reasonable representation. There might be minor documented issues, but it still holds true for the most part. A leader can proceed, but maybe with a bit of caution.
And then it drops off.
Then it drops to low confidence.
Yeah.
It's only possible that the finding is a reasonable representation. This often happens when the data is shallow or there's a lot of conflict. A leader should use extreme caution here, maybe just test this finding on a small scale.
And the bottom level.
Shallow confidence. It is unclear whether the finding reasonably represents the phenomenon. The evidence is just too weak, too conflicting, or too irrelevant to make any decision at all.
Here's where it gets really interesting. Let's say the final theme is implementing AI can reduce peak energy demand by 15%.
Okay.
If the theoretical confidence level for that finding is high, the facility leader can confidently approve a $5 million project for it. But if that exact same finding is rated low confidence because of poor coherence among the studies, that leader now have the transparency they need to pull back and demand more investigation before they commit resources.
It completely changes the conversation. It goes from do we have evidence to how much should we trust the evidence we have. This structured assessment ensures that when those huge decisions are made, the leader knows the exact basis for that decision. It closes the loop on the entire evidence-based management process by providing a rigorous measure of certainty.
Wow. We started with what looked like a dense methodology document, and we found an explicit roadmap for truly evidence-based decision-making. The sheer level of meticulous detail, I mean, from reviewing 95 databases and consulting a librarian on search strings to eliminating any article where even one of 7 quality factors scored too low, it just demonstrates the intense rigor needed to produce the best analysis on a topic this complex.
What stands out to me, above all else, is the unwavering commitment to actively avoiding bias through structure. The systematic review is rigid by design. It's the methodological antidote to, anecdotal management.
Right.
It forces the researcher to be explicit about their limitations, like the U.S.-only focus and their quality thresholds, which they validated with TAPUPASS and then assessed with CIRQUAL. This rigor is the only true guarantee a leader has when they're making high-stakes decisions that impact millions in organizational resources.
So what does this all mean for you, the learner? This deep dive shows that being truly well-informed isn't about reading the most articles on a topic. It's about understanding the complex, multi-stage process of how the best articles were identified, validated, synthesized, and finally assigned a professional confidence score. And armed with this knowledge, you can now critically evaluate the evidence that's presented to you, whether it's in a boardroom, a vendor white paper, or a technical journal.
And here's a final provocative thought to leave you with. The source noted that critical challenge that business leaders often shy away from systematic reviews because they just take too much time. They prefer faster, often less rigorously reviewed recommendations. So considering the complexity of modern operational problems, like integrating AI to balance energy and comfort, does the pressure for speed fundamentally outweigh the demonstrated value of precision? And what hidden long-term operational costs in energy waste, in tenant dissatisfaction, or system failure might that impatience carry years down the line? Something to think about as you evaluate the next major decision that's placed on your desk. Welcome back to the Deep Dive. Our mission here is pretty simple. We take complex, often really dense academic research, and we distill it down into the actionable knowledge that you need to be well-informed.
And today, we are diving into a conflict that is, I think, one of the most persistent and frustrating ones in the entire commercial real estate world.
Facility management.
Exactly. It's this zero-sum game that has really plagued facility professionals for, well, decades. On one side, you've got this constant, relentless pressure to slash operational costs.
Right. Lower the utility bills, get that energy consumption down.
And on the other side, you have the people in the building, the human element.
Yeah.
And they demand consistent thermal comfort, which means, you have to run those big HVAC systems and run them effectively all the time.
And it's always felt like a trade-off. If you lean too hard on the financial side, you get a flood of complaints about people freezing at their desks.
Yeah.
And if you lean too far towards comfort, the CFO is knocking on your door because the utility bills just went through the roof. So the big question has always been, how do you do both? How do you satisfy both of those demands at the same time?
And that is precisely where this systematic review comes in. Our mission for this deep dive is to unpack the quantified, evidence-based answer that this really comprehensive study provides.
And that answer is artificial intelligence.
It is. We're looking at exactly how AI is giving facility managers the decision support they need to finally break that zero-sum conflict.
I think it's important to point out that the core research question driving this whole thing was really focused on that managerial challenge. It's not just a tech question.
Right.
They weren't just asking, does AI work? They were asking, how can AI enhance the decision-making of facility professionals to improve energy management while satisfying occupant comfort?
It's a synthesis. It's technical capability meeting applied operational strategy.
And this review, it carries a lot of weight. And that's because the researchers took this crucial first step of validating their study with the very people who live this conflict every single day.
The industry practitioners and the subject matter experts, or SMEs?
That's such a critical point. This is not just theory that was, created in some academic bubble. By talking to practitioners first, they made sure the research was grounded, practical, and something you could actually use in the real world.
And the experts didn't just approve the study, they unanimously confirmed that the industry desperately needed this review. That endorsement right at the start is probably the strongest signal you could get of its practical value.
So to kick off our deep dive, we really need to understand the architectural rigor here. We're not just going to read a summary of the findings.
No, we're going to trace the entire path. From this chaotic information overload, they started with thousands of potential articles, all the way down to the final set of 31 high-quality validated studies.
And that journey, starting with their expert contacts and their really precise search strategy, is the true proof of how reliable these results are.
So let's unpack it.
Let's do it.
Okay, so that first step, consulting the SMEs, it's something that often gets overlooked in these kinds of reviews, but it just fundamentally elevates the quality of the findings.
It grounds everything in reality.
It does. The researchers knew they had to make sure their academic framework could actually be applied to real industry problems. They were following some, pretty standard methodological recommendations.
And they reached out to 15 experts.
15 high-level industry experts, yeah. And 3 of them accepted the commitment to participate through an EMIS questionnaire.
And these 3 expert voices, they offered some practical gold that just immediately raised the stakes of the entire review, didn't they? What were some of the most surprising or valuable contributions?
Well, the feedback really extended the scope of AI far beyond just, thermostats and utility bills. Dr. Jay Phipps, for example, he didn't just validate the premise.
He did more than that.
He actively provided a list of key areas where AI can expand facility management decision-making. He was essentially charting the course for future research. It was a confirmation that the study, as important as it is, was really only scratching the surface.
And then the input from Mr. Ibrahim Mohammed, that brought in a concept that I think is giving facility managers sleepless nights right now.
Oh, absolutely. The integration of AI and building systems means you have this massive increase in potential vulnerabilities.
You're talking about cybersecurity.
Exactly. Mohammed stressed just how critical cybersecurity is in modern building operations. And think about it, an AI system that's controlling a multi-million-dollar HVAC system is now a huge accessible digital asset.
And if that AI gets compromised?
The entire building's operations and maybe even the company's entire network is suddenly at risk.
He actually argued that cybersecurity in this context is so important it needs its own independent systematic review.
He did, and it's a brilliant insight that connects right back to our core topic. He noted AI's potential role in proactively capturing anomalies.
So AI isn't just the risk, it's also part of the solution.
That's the thing. AI is inherently good at pattern recognition. So while it's busy optimizing temperature, it can simultaneously be monitoring data flow or looking for weird energy spikes or control system inputs that suggest a digital breach or even physical tampering.
So it elevates AI from just a cost-saving tool to an absolute requirement for modern digital security in these commercial spaces.
It really does. The stakes are raised from just saving a bit of money to ensuring total system integrity and security.
So what about the third expert, Mr. Kevin Camp? What did he bring to the table?
Camp's focus was on the long-term capital strategy. He highlighted that AI could fundamentally expand the life cycle of really high-value building equipment.
We're talking about chillers, boilers, air handlers.
The big-ticket items.
Yep.
And the various monitoring systems themselves.
Now, that is a huge financial implication. If a facility manager is normally budgeting to replace a major unit every, 15 years, and AI can push that replacement cycle out to 18 or even 20 years?
The savings on capital expenditure are just enormous. AI can detect these subtle vibrations or minor temperature deviations or gradual decreases in efficiency long before a human or a standard, schedule-based maintenance system ever would.
It allows for this proactive, almost surgically precise maintenance.
Right. It minimizes system wear and tear and maximizes the useful life of that asset. So you can see the SME input didn't just validate the research, it instantly showed that AI's impact is holistic. It's financial, it's human comfort, it's security, and it's capital asset management.
Okay, so with that really strong vision in place, it needed to be translated into a precise, targeted body of evidence. And this leads us to the the meticulous process of designing the perfect search string.
This is where you really see the rigor that's required for a high-level synthesis like this. And the first attempt, a very narrow string just searching for occupant comfort, artificial intelligence, and facility management, was a complete disaster.
A disaster.
It returned 8,852 articles from one search alone.
Wow.
Yeah, that volume immediately tells you there's a crisis of relevance.
That sounds less like a search and more like trying to drink from a fire hose. I imagine the UMGC librarian needed a strong cup of coffee after seeing that number.
I'm sure they did. The volume just proved that using general terminology was, well, useless. They had to be surgical.
Okay, so what was the first step to getting more precise?
The first necessary step was expanding the terms for AI itself. The technology is just evolving so fast that only searching for AI or artificial intelligence would leave these massive gaps in the results.
So they needed a whole basket of terms to make sure they got comprehensive coverage.
Exactly. They searched for things like artificial intelligence or AI or deep learning or machine learning. This captured the foundational concepts like machine learning, which is often the real backbone of this kind of optimization, but it also got the more advanced methodologies like deep learning.
And then next, they actually refined the focus by removing the term facility management, which seems a little counterintuitive.
It does, but that phrase was just far too broad. It was probably triggering results from management consulting or project management or even academic management theory that had nothing to do with the physical structure of a building.
So they swapped it for something more concrete.
They did. They replaced it with office building, which clearly delineated the physical environment they were interested in. Commercial, occupied structures.
And this is where the rigor really starts to teach us a lesson about information retrieval. The advanced coding, using things like truncation and proximity.
This is the real aha moment for any learner who's trying to do serious research. Truncation, using the asterisk, is just a super efficient way to capture all the variations of a root word.
So, for example, using utilit would get you utility and utilities.
Right. It prevents the researcher from having to type out every single plural, singular, or adjectival form. It's a simple trick, but it's powerful.
But the real elegance, I think, was in the proximity code, Ensteck. This helps define the contextual relationship between two different concepts.
It's the difference between finding an article that happens to mention energy on page 1 and cost on page 10 versus finding an article that discusses energy consumption cost in the very same sentence.
And they used N10.
Yes, N10. They were ensuring that any energy or utility terms were found within 10 words of cost or expense, spend, or consumption terms.
So they weren't just looking for general articles about energy and cost. They were surgically searching for research that defined the financial outcome of that energy use.
And that hits the core conflict of the review directly. The precision was necessary because the goal of the review wasn't just about making the building more efficient. It was about proving the financial benefit of maintaining occupant comfort.
And this all resulted in a pretty complex four-part final search structure.
It was a layered instrument, really. Layer 1 was that broad basket of AI terms we talked about. Layer 2 was the comfort terms, things like occupant comfort or thermal comfort, temperature, heat, cool, HVAC.
A lot of variations there.
A lot. Layer 3 was the combined energy and utility terms, but they had to be linked to the cost and consumption terms using that N10 proximity code.
And the final layer.
Layer 4 was the building-focused terms, so building, commercial, office with the truncation. And the rule was only articles that contain elements from all 4 of those layers would pass the initial filter.
That is just a masterclass in ensuring relevance before the real screening even begins.
And once that structure was perfect, they had to choose the battlegrounds. Which of the 95 available databases would give them the most comprehensive yet still relevant results?
And they intentionally chose just 3, right? Each designed to cover a distinct angle: business, general science, and technical application.
Exactly. The first, A by Inform, was absolutely crucial for capturing the business and the managerial angle. It indexes articles, reports, case studies, all related to business management going back to 1923.
And it was important because it wasn't part of their main search tool.
That was a key strategic reason for its inclusion. It contains information about the financial and administrative application of technology, which is exactly what a facility manager needs.
The second one, OneSearch, was the main aggregator, the big, wide net.
Correct. It pulled from 43 different component databases. That was to ensure broad initial coverage across the arts, sciences, business, and technology. You have to acknowledge that AI research often crosses these multidisciplinary boundaries.
And the third one, Scopy use, was chosen specifically because it covers the more technical scientific journals.
Right. That's where you're going to find the core engineering and thermodynamic research that's related to building science and even behavioral science, which ties into occupant comfort. The selection of just these three databases provided a really intentional cross-disciplinary foundation for the whole deep dive.
And beyond just the search string, they also applied some essential constraints or limiters to make sure the findings were current and practical.
Yes, and the most critical constraint was the publication date. They limited it to 2018-2023.
Which makes total sense, given how quickly AI algorithms and facility management tech are progressing.
Yeah.
Anything older than 5 years might be technically obsolete.
For sure. They also limited the language to English, which is pretty standard.
But they made the unusual choice to disable the full text limiter.
Yeah.
Why did they do that?
This really demonstrates a commitment to rigor over convenience. Disabling that limiter meant they captured all potentially relevant articles, even if the university didn't have immediate digital access to them.
So they were willing to do the extra work.
They were. They proactively identified 9 such articles and worked with the librarian to request the full text. They were prioritizing the completeness of the evidence base above all else.
So after all of that effort, what was the initial raw result count?
It came to 2,012 articles. Abedinform contributed 46, Scopios gave them 18, and the big aggregator, OneSearch, provided the bulk at 1,948.
And here's a subtle but really important point for anyone who's trying to replicate this level of research. Even with all that careful planning, the databases didn't cooperate perfectly.
It's a great little anecdote about the reality of doing systematic review work. The syntax was different for each one. OneSearch required N10 for proximity, but Abedinform demanded N10.
And Scopius was the most idiosyncratic.
By far. It demanded that all the limiters, like the publication year and language, had to be typed directly into the search string itself. This meant the researchers had to customize their precision tool for each platform just to make sure the same quality standard was applied everywhere.
Okay, so once they had those 2012 records, the real filtering began, the Prisma flow, reducing that massive data set down through eligibility screening.
The first step is always removing duplicates. That dropped the total down to 971 unique records, and then began the very detailed abstract review based on specific exclusion criteria.
The first cut eliminated 226 articles because they were focused on non-commercial office buildings.
Correct. They wanted to maintain the focus on commercial office applications, not residential or educational or hospital facility management. Another 282 articles were eliminated for just not being related to the topic after they reviewed the abstract.
But the single biggest hurdle, the major narrative point in their whole process, was what they called the geographic bottleneck.
This was the real shocker. 420 articles, that's almost half of the remaining records, were eliminated solely because the studies focused on buildings outside the United States.
And this was an unanticipated limitation that really impacted the scope of the final review.
It really did, and we should dwell on this because it's important not just as a technical step, but as a pointer to missed opportunities.
What do you mean by that?
Well, the researchers themselves noted that this U.S.-centric focus eliminated some highly relevant global studies. Studies that potentially offered much more diverse and advanced use cases for AI implementation.
So there's good research out there that didn't make it in.
Yes. They specifically mentioned a researcher, Hosamo, who published 2 highly relevant studies in 2023 that were rejected purely based on location. So the implication is clear for you, the facility manager listening. While this review provides high-quality U.S.-based evidence, some of the most cutting-edge, globally developed AI solutions might not be reflected here.
So future studies really need to incorporate a global view.
Absolutely.
That geographic filter brought the number of remaining articles down to a much more manageable 42, which were ready for the final quality appraisal. And this is where they applied that sophisticated quality scoring system called TAPUPACE.
TAPUPACE. It's an acronym that stands for Transparency, Accessibility, Purposivity, Utility, Propriety, Accuracy, and Specificity. It's basically a tool to assign a quantitative quality score to research papers.
So it allows the researchers to judge their confidence in the results.
Precisely. They used a Likert scale, 1 to 3, for each of those 7 elements. A perfect paper scored a 21, and that was designated as high quality.
And the thresholds were pretty clear.
Very clear. High quality was a perfect 21, medium high was 17 to 20, and medium quality was 14 to 16. This kind of objective measure allowed them to filter out studies that might have been on topic but were just methodologically weak.
And there was an interesting little challenge they ran into during the TAPIGO scoring related to the propriety category.
Yeah, this is a perfect example of methodological transparency in action. The propriety category assesses whether the researchers got organizational approval for their research.
Which would be hard to confirm.
Very. Because so many of these articles described experiments, it was often difficult to know for sure if they got formal permission. So, to maintain consistency and fairness, they adjusted the scoring. They ensured no article got a score lower than 2 for propriety, and if approval was explicitly stated, it got a 3.
So they weren't unfairly punishing good studies that just failed to mention a standard procedure.
Exactly. It was a smart adaptation.
And this rigorous quality control led to the final cut.
10 articles were eliminated in this final round. 2 were actually other systematic reviews, which are valuable and were included in the references, but not in the primary synthesis itself.
Okay.
8 were found to be outside the scope once the full text was reviewed. And critically, 1 article was eliminated solely because it scored an 8 on the TAPU-PAS scale, just too low to be considered reliable evidence.
And the final outcome.
A highly vetted, high-quality final set of 31 studies ready for synthesis. And that journey, from almost 9,000 articles down to 31, is the single best proof of the reliability of the findings we're about to discuss.
All right. Now that we have absolute confidence in the studies themselves, let's take a quick look at what this evidence base actually represents. It sounds like an exceptionally strong foundation.
It really is. The quality distribution is impressive. 77% of all the included articles were rated as medium high or high quality.
77%. That's a heavy skew toward the top.
Very heavy. To break it down a bit more, 9 articles, so about 30%, achieved that perfect score of 21. 13 were medium high quality, which is 43%, and 8 were medium quality, or 27%.
So nearly 3/4 of all the evidence is in that top tier. Can you give us a flavor of some of those perfect scores?
Absolutely. The high-quality studies that hit that perfect 21 included papers by folks like Zhang, Xiao, Niu, and Zi Wang. These are really the definitive works that demonstrate the highest level of methodological rigor. They provide the most dependable results.
And even the lowest accepted scores were still respectable.
They were. Papers like Jihu and Yu and Khalil still achieved a score of 14, which is solid.
So that gives us a lot of confidence in the what. Next, let's look at the how. What kind of research methods were being used? Was this all just theoretical modeling, or were people actually out there running tests in buildings?
The diversity of the methods really confirmed that this is an exciting field of ongoing discovery, but the dominance of applied research was crystal clear.
Okay.
Experiment quantitative methods made up the largest segment by far. That accounted for 17 of the articles, or 55%.
That's significant. More than half of the evidence comes from studies that were actively testing hypotheses, running control groups, and collecting hard numerical data on things like energy consumption, thermal stability, occupant behavior.
Precisely. This is applied science. They weren't just modeling in a computer. They were measuring real-world outcomes. The other methods included mixed method studies, which blend quantitative data with qualitative insights, and observation quantitative studies. The mix of methods really confirms that the field is moving rapidly from theory into practical application and measurement.
And since we established that AI is evolving so quickly, the chronology of these articles is key to making sure everything is timely. What did that distribution look like across the 5-year window, from 2018 to 2023?
The distribution was really steady, which indicates a consistent level of interest. There were 6 articles in 2018 and 6 in 2019, then a slight dip to 3 in 2020, back up to 5 in 2021, and 4 in 2022.
But the highest volume was right at the end of the review period.
Yes. 2023 contributed 7 articles, the most of any year, and that signals that the research, the implementation, and the publication around AI and facility management are all accelerating. It just reinforces that this deep dive is focused on a rapidly expanding field.
Finally, where was this research getting published? Did it all come from one sort of niche corner of the academic world?
No, and this is another really good proof of generalizability. The 31 articles were spread across 19 different peer-reviewed journals.
So that diverse spread means the findings aren't biased towards a single methodology or, a single editorial viewpoint.
Exactly. No, there were some natural concentrations, of course. Given the twin focus on comfort and energy savings, The journals applied energy and buildings had the highest concentration. They each contributed 4 articles.
Which makes perfect sense.
It does. A concentration in those highly specialized energy-focused journals is exactly what you'd expect to see.
Okay, so we've established the rigor, the quality, and the diversity of the evidence base. Now we can finally move into the results. How did the researchers turn this mountain of high-quality data into actionable intelligence for facility managers?
This is where the magic really happens. The methodology of insight, or what's called coding. The goal was to synthesize the raw findings of 31 distinct studies into a few coherent themes. And to do that, the researchers used a software called ATLS-TIE to organize and analyze the discussion, findings, conclusion, and limitation sections of every single paper.
And they used both deductive and inductive coding. Let's try and simplify that for the learner.
Sure. Deductive coding is theory-driven. They went into the papers with established frameworks already in mind. In this case, the CMO model and adaptive structuration theory, or AST. They were looking for specific elements related to context, intervention, mechanism, and outcome.
So they were looking for the answers that their theory predicted they would find.
Right. But inductive coding, that's the surprise element.
Okay.
Inductive coding is data-driven. It's about capturing the insights that emerge organically from the text. Things the researchers hadn't specifically predicted, but were clearly persistent issues in the literature. Things like training problems or limited data or the fact that occupancy was such a critical variable.
And the ultimate goal was to show how these technical systems connect directly to real management outcomes. They used the concepts from that adaptive structuration theory, AST, to map the whole relationship.
That's it. But before we get to the outcomes, we have to look at the tools themselves. What were the specific AI structures, the technical interventions that were repeatedly cited in these papers?
This is the real nuts and bolts.
It is. This list is an operational snapshot of the state of the art. These were the first cycle codes they identified under the structures concept of AST, and they included the expected foundational systems like the artificial neural network and general machine learning. But what's truly fascinating are the advanced algorithms that kept showing up.
Okay, let's pull some of those out and try to explain them in a practical building context, because just listing acronyms isn't very helpful. Let's start with the deep reinforcement learning algorithms.
Yeah.
Double deep Q network, deep Q network, and asynchronous advantage actor critic, or A3C. What are these things actually doing in a building?
Okay, so you should think of these as control systems that are designed for real-time optimization. It's like having a highly skilled, constantly learning HVAC engineer on staff 200/7.
As opposed to a standard system.
The standard system just maintains a set point, say 72 degrees. If it gets warmer, the system turns on. If it gets colder, it turns off. It's a very simple feedback loop.
Very reactive.
Extremely. But A3C, the asynchronous advantage actor critic, is fundamentally different. It uses reinforcement learning, which means it learns through trial and error. Or, maybe more accurately, through reward and punishment. The reward is maintaining comfort and minimizing energy use. It doesn't just react, it learns the optimal policy over time.
So for example, on a Friday afternoon, knowing that maybe 80% of the occupants are going to leave at 4:30, the A3C algorithm might start gradually pre-cooling the building at 2 p.m. using less intensive methods. It anticipates the afternoon sun, and it avoids a massive energy-intensive temperature swing later on.
Precisely that. It learns these complex, long-term operational strategies to stabilize the thermal conditions while ensuring the energy usage curve is as low and as flat as possible. It is dynamic predictive control that moves far beyond the simple controllers of the past.
Then we have the inclusion of ChatGPT and the transformer model. That's incredible.
Yeah.
How are large language models applicable to facility management?
We're seeing this shift toward decision support through natural language. Facility managers deal with these huge volumes of unstructured data. Tenant complaint logs, maintenance manuals, historical repair notes, operational procedure.
A mountain of text.
Right. And ChatGPT, or similar transformer models, can be used as a smart interface to that mountain. A facility manager can literally query the system and ask, why did Chiller 3 fail last Tuesday? And how did that correlate with the external temperature and the power consumption spike? And the AI synthesizes the answer from thousands of pages of documents and live data streams.
So it's not controlling the building itself, not yet, but it's making the manager drastically smarter and faster.
It democratizes complex data analysis. It turns these mountains of operational reports into plain language decision support, which ties directly back to the core research question about enhancing decision-making.
We also saw algorithms that were dedicated to visual analysis, like the You Only Look Once algorithm, or YOLO.
YOLO is famous in computer vision for its real-time object detection. In a facility context, this means leveraging things like security cameras or other specialized sensors, not just for security, but for occupancy monitoring.
So it's counting people.
It allows the AI to accurately count how many people are in a specific zone, which is critical for highly granular HVAC control. If YOLO detects 5 people in a conference room that's designed for 20, the AI can immediately and safely reduce the airflow and the heating or cooling load for that one room.
And save energy without impacting comfort.
Exactly. It's a huge leap from relying on simple motion sensors. A motion sensor just knows if someone is there. YOLO knows how many people are there, where they are, and even if they are moving. It provides highly accurate input for those optimization algorithms like A3C.
And finally, the concept of the digital twin was frequently cited.
The digital twin is perhaps the most profound tool on that list. It's a virtual, high-fidelity replica of the physical building, and it's continuously updated with real-time data from all the sensors and systems.
So it lets the facility manager run simulations to do what-if scenarios without impacting the live building or its occupants.
Right. A manager could test, what happens if I reduce the supply air temperature by 3 degrees on the 10th floor? What is the predicted energy saving, and what is the maximum predicted drop in thermal comfort over the next 2 hours?
And the digital twin provides the answer.
It provides a safe, low-cost environment to model the impact of operational changes. It allows the AI to optimize in the virtual world before it ever commits to a change in the physical world. It provides just unparalleled decision support.
So this detailed view of the structures really shows us that AI isn't a single technology. It's a whole toolkit of advanced systems. The researchers then use that AST framework to map these tools to the real-world operational variables. Let's look at the systems first, the infrastructure the AI actually operates on.
Right. The systems are the digital and physical canvases for the AI. These included the foundational infrastructure, the building management system, or BMS, which controls the HVAC and lighting.
The brains of the building.
Pretty much. Then there's the computerized maintenance management system, the CMMS, which handles work orders and asset tracking. And then simpler things like data storage systems and the lighting systems themselves. The AI needs integrated access to all of these operational pillars to be effective.
Okay, next, let's look at the operational reality, the boundaries and constraints that limit AI deployment. This is crucial for the learner. It shows where the real-world challenges lie.
These constraints really define the boundaries of the problem. They included technical environmental factors like managing CO2 levels and noise. You can't sacrifice air quality or generate too much fan noise in the pursuit of efficiency.
But the most significant constraints were all related to data.
They were. The inductive codes highlighted 2 key data challenges: the need for large data sets and, at the same time, limited data.
Which sounds completely contradictory.
It's the paradox of modern AI. These powerful deep learning algorithms like A3C and the Double Deep Q network, they require massive amounts of historical data to train effectively. That's the need for large data sets.
But in the real world.
In many real-world facility contexts, data collection is piecemeal, it's siloed in different systems, or it's just poorly cataloged. That's the limited data constraint.
So the most powerful tools are being bottlenecked by the quality of the data that facility managers already have on hand.
It is the ultimate barrier to entry. If you don't have several years of high-resolution labeled data that links occupant activity, external weather, and system response, the AI simply cannot train itself optimally.
And they also noted data security as a major constraint.
A huge one. Facility managers are and should be hesitant to expose their operational systems to external cloud services or potential vulnerabilities if that data isn't perfectly secured.
Okay, moving on to the appropriation and operations variables. These are the levers that the manager or the AI is directly pulling or measuring.
These practical variables, which were also inductively derived from the research, are the main inputs for the optimization models. Things like occupancy, which is leveraged by tools like YOLO.
Right, the people counting.
Energy usage, which is the primary metric for savings. And thermal conditions, the primary metric for comfort. These are the 3 elements that the AI is constantly monitoring and adjusting to achieve its goals.
And finally, that brings us to the ultimate decision and outcome codes, what the facility manager is actually trying to achieve.
The desired outcomes were pretty straightforward: savings, reduced energy consumption, and enhanced occupant comfort. But the researchers also captured the nuances of management support.
How so?
Well, they found that AI provides decision support, helping the manager choose the best course of action. And there was an interesting inductive code, increase manpower, which suggests that AI doesn't necessarily replace staff.
It makes them more effective.
Right. It makes the existing staff more effective and capable of handling a larger volume of operational complexity. And conversely, they also captured the risks, financial loss, and increased cost, confirming that a poor implementation or faulty data can actually lead to worse outcomes.
So this whole systematic process led to the final distillation. The two synthesized themes that summarize the total findings of all 31 articles. These are the core takeaways for the learner.
The findings were guided by that concept of decision support and enhanced operations. And they really confirm that AI delivers measurable, consistent success across the board.
Let's break down theme 1. Energy management and occupant comfort monitoring is improved by artificial intelligence.
This is the dual mandate success story. It means that AI provides superior tracking, diagnosis, and management of both the financial variable, which is energy, and the human variable, which is comfort, at the same time. The research shows that AI moves way beyond basic scheduling and simple setback strategies.
So how does this manifest practically for a facility manager on the ground?
Well, take fault detection, for example. An AI can use neural networks to monitor thousands of data points across the BMS. It can detect these subtle, non-obvious issues, like a damper that's slightly sticking or a fan that's running at 90% when it should only be at 70%.
Things a human would never notice.
Right. And these little things lead to energy waste and comfort drift. The AI monitors this, it flags it, and it provides the manager with a specific evidence-based recommendation for action. That is far superior to a human trying to manually analyze hundreds of trend logs. And it leads to demonstrable energy savings because small issues are caught immediately, before they become large energy drains.
It really shifts management from being reactive, waiting for a complaint or a total failure, to being predictive.
Absolutely. And that improvement in monitoring is directly linked to the use of tools like digital twins and advanced machine learning models. They allow the manager to visualize the performance gap between their ideal theoretical model and the actual building performance, which lets them quantify the financial impact of even minor operational inefficiencies.
Okay, now let's look at theme 2, which focuses purely on the human element. Occupant comfort is stabilized and improved with artificial intelligence.
This theme really addresses that historical trade-off. The evidence shows AI doesn't just cut costs. It provides a better, more comfortable environment. And this stabilization comes primarily from its predictive capabilities and that granular control based on real-time data from tools like YOLO for occupancy detection.
So if the system knows, based on historical patterns, that occupants on the west side of the building always arrive a bit late, or that the south-facing corner starts heating up at 11 a.m., regardless of the exterior temperature, it can proactively adjust.
That is the key to stabilization. Traditional systems just react too slowly. By the time a thermostat registers a high enough temperature to trigger a cooling cycle, the occupant is already feeling discomfort.
Already complaining.
Exactly. But these reinforcement learning algorithms like A3C, they learn the thermal inertia of the building, how long it takes for a temperature change to propagate through the structure. They can predict the discomfort several minutes or even an hour in advance and initiate these subtle preemptive adjustments.
And the result for the occupant is that they don't feel those dramatic swings. They just feel a consistent, steady thermal stability.
And that leads directly to better productivity and fewer complaints. You're achieving the human goal without sacrificing the financial goal. The ability of AI to model individual thermal zones and factor in local conditions, solar gain, internal heat load from equipment, human presence. It allows for this zone-by-zone optimization that just wasn't possible with older, centralized control systems. This is the measurable improvement that all 31 studies confirmed.
So if we look back at those AST structures, the connection is so clear. Highly granular, real-time measurement from things like YOLO and digital twins
Right.
feeds into these complex learning algorithms like A3C and Deep Q networks, which in turn execute predictive control that leads to improved comfort and reduced consumption. The zero-sum game is broken.
And this is all built on the bedrock of that 77% high-quality evidence base we reviewed. So the confidence level in these outcomes is exceptionally high.
That's a great summary. So let's wrap this all up. When we look back at the incredible scope of this deep dive, We started with this overwhelming potential data set of 8,852 articles.
Just a staggering number.
And through this hyper-specific search architecture and a relentless quality appraisal using tools like TAPU pairs, we arrived at a highly confident synthesis of just 31 studies.
The core knowledge is clear. These AI structures, from foundational machine learning all the way up to the cutting-edge application of digital twins, YOLO, and A3C reinforcement learning algorithms, they are measurably and definitively breaking that old conflict between high energy consumption and occupant discomfort.
The AI is driving superior decision support by improving both monitoring and stabilization.
And for you, the learner, this knowledge is a shortcut. You now know not just that AI works, but which specific algorithms are being leveraged, which systems they integrate with, like the BMS and CMMS, and, most critically, the real-world constraints, data quality, and data security that you have to overcome for a successful implementation.
As we wrap up, we need to return to one of the study's own acknowledged limitations, which I think points us toward the future of facility management. The researchers relied very heavily on peer-reviewed articles.
Right, which is standard practice for a systematic review.
It is, but it also necessarily excluded literature from the concrete uses of artificial intelligence in facility management that often exists in proprietary systems or gray literature or internal industry reports.
Scientific journals tell us what research is proving under controlled conditions.
But the industry often moves faster than academia. And this raises an important, I think, a provocative question for you to mull over.
Okay.
If the published science already confirms the utility of deep reinforcement learning, digital twins, and these visual occupancy algorithms, what revolutionary, efficient, and cost-saving applications are facility professionals already quietly running in the real world that haven't yet passed the peer review process? What secrets of optimization are already being implemented off the grid, right above your head?
The facility manager who gains that knowledge first, whether it's from published research or from industry intelligence, holds a powerful competitive advantage.
An excellent thought to end on. Thank you for joining us for this deep dive.
We look forward to synthesizing the next stack of sources for you.
We'll see you next time.
Welcome back to the Deep Dive, the show where we take that intimidating stack of research, the one you know is crucial, but just haven't had the time to synthesize, and turn it into immediate, actionable, and frankly, fascinating knowledge.
That's right. And today we are strapping in for a ride through the unseen infrastructure that literally keeps the modern world humming: facility management.
I'm glad you put it that way, because we really are diving deep into the hidden mechanics of these huge operations.
We are. We're talking about the systems that handle everything from, security protocols to maybe sure the elevators work. And I think most importantly for our deep dive today, the massive mechanical systems that deliver air and comfort.
And why this is so crucial for you, our learner, is because maintaining that comfort inside any large building, commercial or institutional, is, well, it's one of the single most expensive line items on the operating budget.
Without question, incredibly expensive.
We're really talking about a decades-old conflict that facility professionals fight every single day. It's this push and pull between a building's operational energy budget and a person's, their thermal happiness.
Yeah, it's the classic, seemingly unwinnable battle. You've got the finance team demanding lower energy costs on one side.
And on the other, you have the thermostat warrior, who is constantly freezing or overheating. We've all been that person.
And this is exactly the conflict zone that artificial intelligence is now entering. Our entire deep dive today is based on a really rigorous systematic review of 31 scholarly articles.
And these aren't just blog posts.
No, not at all. These were peer-reviewed experimental studies, and they were all focused on one central, really powerful research question. How can artificial intelligence enhance the decision-making of facility professionals to improve energy management while satisfying occupant comfort?
So our mission today is crystal clear. We're going to unpack the 4 core findings that emerged from this review, which I think collectively show exactly how AI is poised to revolutionize building operations.
Or at least how it could revolutionize them.
Exactly. Because we also need to hit the brakes hard in that final section and look at the surprising, very practical, and very real barriers that are preventing this revolution from fully, deploying across the United States.
And the entire intellectual focus of this research, and this is what gives us great confidence in the findings, is on making the right decision with the best possible analysis.
It's not just about the tech itself.
Not at all. We aren't just looking at algorithms as clever bits of code. We're looking at how this technology transforms the entire decision-making structure within an organization. We're going to look at the tools, the conceptual frameworks, and like you said, the surprising challenges.
And if we're going to talk about energy cost and comfort, which is the nexus of this whole problem, we have to introduce the main target of this entire discussion, right? The HVAC system.
Absolutely. The heating, ventilation, and air conditioning system is the primary target here. Because in most commercial buildings, it's the single largest contributor to energy consumption.
By a lot, right.
Oh, a huge amount, often accounting for 40 to 60% of total energy use. But at the same time, it's the only mechanism you have for delivering thermal comfort.
So that's the interception.
It's the whole game. The research overwhelmingly confirms that this intersection, maximum energy use tied to maximum human expectation, is where the most complex, the most expensive, and the most frequent decisions are made. It's the problem that, if solved, unlocks billions in potential savings and productivity gains.
Okay, let's unpack this and start with the sheer weight of the evidence, which brings us to finding number one. And this finding, it immediately tells you where the research money and the academic focus is being spent, at least in the U.S.
Finding one is the fundamental statement of fact derived directly from the analyzed data, it says. In the United States, research focuses on thermal comfort and occupancy through heating, ventilation, and air conditioning HVAC controls.
That's a critical piece of data because the sheer volume of research focused on just this one area is, well, it's staggering. What were the numbers on that?
This one finding was supported by 22 of the 31 articles reviewed.
22 out of 31.
Yeah, that's a very strong 71% of the total evidence base. And this tells us two things. First, that U.S. researchers and experimenters are heavily prioritizing energy management.
Right.
And second, that they're specifically focusing on using AI to analyze and optimize data that comes exclusively from HVAC operations. It's the core problem set for them.
So what does that intense focus really suggest about the U.S. market? Is it just that we have bigger buildings, or is there some specific regulatory or economic driver pushing this HVAC-centric research?
It's likely a combination of things. The U.S. has a vast and, frankly, aging inventory of commercial real estate.
That makes sense.
And our climate diversity necessitates heavy, complex HVAC use. You need intense cooling in Florida and, and intense heating in Minnesota.
Of course.
And then economically, because HVAC is such a dominant cost center, any marginal improvement you can make yields massive financial returns. So if you're going to experiment with complex AI, the ROI is clearest when you apply it to the 50% energy drain, not, say, the lighting, which might only be 10%.
So if the AI is focused so intensely on HVAC, it's not just about turning the AC up or down, is it? We're talking about achieving thermal comfort, which sounds like a much more complicated dynamic soup of variables that the AI has to constantly manage.
Oh, it's extremely complex. The AI has to manage a multivariate problem set all at the same time to achieve what's defined as true thermal comfort.
And how do they define that?
It's the condition of mind that expresses satisfaction with the thermal environment. And the factors contributing to that feeling include humidity, air temperature, airspeed, and radiant temperature.
So it's not just the number on the thermostat.
Not even close.
Yeah.
If the AI only focuses on air temperature, you end up with a building that feels, too cold and dry because of low humidity, or too stuffy with poor air movement. Or maybe one side of the room feels fine while the other, next to a large sunny window, is radiating heat.
Right, so the AI has to manage all four of those things at once to keep people happy.
Holistically, yes,
Yeah.
to keep the occupant satisfied.
Okay, so here's where this deep dive gets into some truly innovative solutions. The literature isn't just saying use AI to adjust the AC. It details some, almost futuristic approaches to comfort. Let's spend some time on those nuggets, starting with something called biosensing and reinforcement learning.
Yes, this is one of the most innovative and occupant-centric approaches found in the review. There was a specific study that moved control away from fixed sensors on the wall and toward the individual person.
So it's sensing the person, not the room.
Exactly. They use biosensing technology combined with a highly sophisticated reinforcement learning approach, specifically what's called a double deep Q network algorithm.
A double deep Q network. Okay, that sounds less like facility management and more like advanced robotics control. Can you break down what reinforcement learning is even doing here?
Certainly. So reinforcement learning, or RL, involves training an AI agent to achieve a goal by rewarding desirable actions and punishing undesirable ones.
Like training a dog.
It's a great analogy. The agent, which is the algorithm, learns through trial and error within a defined environment. In this study, the goal was maximizing occupant thermal satisfaction while minimizing energy consumption.
And the double deep Q network part, what's that?
That's the mechanism that makes the decision robust. The AI monitored and regulated the HVAC response based not just on the usual room conditions, but on the occupant's biological responses.
Wow. So data collected via biosensors, measuring things like skin temperature or heart rate?
Precisely. Things that act as proxies for comfort. The RL agent then chose actions like adjusting damper positions or changing airflow rates that maximize the perceived reward, which was thermal satisfaction, and minimize the penalty, which was high energy use.
So it's literally fine-tuning the climate control based on what a person is biologically feeling. It moves way beyond just subjective feedback.
That is the ultimate resolution to the thermostat warrior conflict, right? The AI removes the need for human input because it's tracking the actual biological state of the human.
Incredible.
But the next finding also tackles this issue of knowing who is in the room and what they prefer, but without being intrusive. That's the non-intrusive occupancy ID piece.
And how did they manage to identify specific people without using something like, say, facial recognition?
Well, one study described a system using a non-intrusive ultrasonic-based doorway. This system creates a profile based on unique physical characteristics, things like height and gait, without relying on any camera imagery.
And how well did it work?
It achieved an impressive 95% accuracy in differentiating between individuals. And it then used a clustering machine learning algorithm to group these identified occupants.
And why is identifying a specific person rather than just knowing someone is here so valuable to a facility manager?
It allows for true personalization based on pre-registered data on that specific occupant's preferences. Maybe they're known to prefer a higher temperature, or they're allergic to certain air quality conditions.
I see.
The algorithm could adjust the indoor air quality, the ventilation rate, or the temperature set point the moment they enter their zone. It's personalized environmental control delivered autonomously, which is a major enhancement to productivity.
Now, if biosensing and personalized ID are about optimizing the environment for the person, there was this other concept, space match, that seems to be about optimizing the person for the environment. Tell us about that, because that struck me as really clever.
The proposed space match framework is a fascinating pivot because it completely changes the AI's objective function. Instead of the algorithm reacting to discomfort by increasing energy use, blasting the AC or turning up the heat,
Right.
the occupant responds to a series of questions about their current thermal state through an app. The algorithm then analyzes the existing conditions of all available spaces in the building. It directs that occupant to an already suitable space in the building that satisfies their comfort requirements.
So instead of spending energy to cool down a hot room for one person, the AI just suggests an unoccupied, slightly cooler room down the hall.
That's it.
So the algorithm is basically telling the perpetually cold person, hey, don't force the building to change. Just adjust your location to a space that's already operating optimally for your needs. That's brilliant. You're leveraging the existing features of the building to solve the comfort problem without any extra energy expenditure.
Exactly. It saves the finance team money while satisfying the thermostat warrior. It's a decision support tool that manages the human element, not just the mechanical system.
But we have to introduce the contradiction that was found in the literature here, right, to kind of ground this in reality.
We do. There was a critical caveat.
What was the limit?
One study noted that while machine learning can certainly improve the responsiveness of buildings and help make better operational decisions, just throwing an algorithm at the problem isn't enough to solve comfort completely.
What else is needed?
They reported that more responsive and innovative ventilation systems and hardware upgrades are still needed to truly maintain consistent thermal comfort, enhance occupant health, and drastically reduce energy use.
So the data analysis is only as good as the system it controls.
Precisely. If the physical components, the dampers, the variable air volume boxes, the pumps, are slow or outdated, even the smartest AI is limited in its ability to execute an optimal decision.
That contradiction is a perfect segue. It forces us to ask, how confident can we really be in these findings? And the confidence comes from the extreme rigor that went into synthesizing these 31 original articles. This wasn't just a quick search. This was a complex academic methodology.
That's absolutely right. The confidence level for these findings was assessed as moderate, which is a strong result, given that many of the studies were complex experiments on non-standard existing building systems. And I think it's worth delving into the methodology briefly because it underscores the trust we can place in the 4 core findings we're sharing today.
So walk us through that academic process. How do you turn 31 different experimental articles into the 5 core categories that structure the final analysis?
Well, it began with what researchers call coding cycles. The first cycle involved listing common deductive codes. These are codes derived from existing theory. So for this study, they expected to see codes like humidity, temperature, and communication bridge.
Things they knew would be there.
Right. But as the researchers read, they also conducted an inductive analysis.
And inductive codes are the unexpected things, the factors or limitations they noticed that didn't fit the initial theory.
Precisely. They were capturing conditional limits or emerging themes they noticed during the deep reading. Things like require large data sets, limited data, and demand control. They started with 46 codes in total, capturing every distinct concept or observation.
46 distinct concepts from just 31 articles. That shows how granular this research really was.
It does. And that level of detail is what necessitated the data cleansing step. The 46 initial codes were reduced down to 37 by merging similar codes and eliminating unused ones.
Can you give an example of that?
Sure. The researchers realized that codes related to cooling system performance and control system performance were really measuring the same underlying concept of system effectiveness, so they merged them. That step is vital to ensure the final analysis tracks distinct, meaningful ideas.
And then came the second cycle, where they moved from those 37 specific codes to broader conceptual categories.
This is where they applied what's called the umbrella code method. They grouped the 37 remaining codes based on overarching conceptual themes. So to give you a powerful example, codes like financial loss, training problems, limited data, and increased cost.
All the bad stuff.
Right. They were all grouped into the umbrella category of challenges. These are all barriers that a facility professional would face when trying to implement a new system.
So instead of having 4 separate findings about problems, you get one comprehensive finding about the overarching challenges.
Exactly. They initially identified 9 categories, but then realized that some of them overlapped conceptually. For instance, management tools and decision support reflected the exact same concept, helping the professional make informed choices.
So they merged those two.
Correct. 9 categories were merged down into 5 final categories to create a clean, non-redundant framework. And these 5 overarching themes are what organize the final data synthesis. Challenges, decision support, enhanced communication, enhanced operations, and predict conditions. These categories are the bedrock of our entire deep dive.
Now that we understand the methodology, we need to introduce the philosophical lens, the theoretical anchor that holds everything together. That's the adaptive structuration theory, or AST. For those of us who don't read facility management theory, why is this framework so critical?
The AST is absolutely central. It provides the lens to view how new, sophisticated technologies like AI and the Internet of Things impact existing organizational decision-making structures. It forces us to look past the technology itself and focus on the interaction.
What kind of interaction?
Specifically, it focuses on 2 things: the structures provided by the technology and the new structures created by human actors, the facility professionals, as they interact with that technology.
So it formalizes this interplay between the machine and the person, showing how a new tool changes the way decisions are made, not just what decisions are made. Let's spend some time on this because it's the conceptual heart of the research. What are the key components of the AST model as they applied it here?
We can break it down into 3 areas. First, you have what are called the structural features. This is the static environment. It includes the AI algorithms themselves, the Internet of Things devices collecting the data, and crucially, the group's internal system.
And that group's internal system, that's the vital human element.
It is. It means the cultural or historical assumptions the facility professional brings to the job. For example, if a facility manager had 30 years of experience fixing a certain chiller manually, their internal structure might involve a deeply held suspicion that an AI algorithm can predict the failure better than their trained ear can.
So that existing cultural structure is a force that technology has to contend with.
It's a foundational barrier.
Yeah.
Then the second component is the system, or the actor.
The person.
That's the facility professional themselves. They engage in social interaction using the existing legacy systems, the CMMS, the BMS, the HVAC controls. This interaction, the human using the machine, is what leads to the decision process. Is the actor making a predictive adjustment based on the AI dashboard, or are they waiting for a system failure to generate a work order?
And finally, the outcome?
The outcome is twofold. There's the direct result, the decision outcome itself, a verifiable improvement in energy consumption or occupant comfort. But most importantly, there's the resulting new social structure.
What would that look like in the real world?
It might manifest as the facility professional's customized real-time dashboard in the BMS, or a newly adopted predictive maintenance protocol. The AST shows us that AI doesn't just produce data. It transforms that raw data into a new, actionable structure that fundamentally changes how the human actor behaves.
So if the facility manager starts making investment decisions based on AI predictions rather than just annual budget cycles, the AI has successfully transformed the organizational structure, completing that adaptive process.
Precisely. That's the ultimate metric of success in this field.
That structure is vital to understand because it really frames the rest of our findings. Now that we understand the focus, which was finding one on HVAC, and the rigorous method behind the synthesis, let's shift to the operational benefits. How is AI actually helping facility managers transform their workflow in practice? This starts with finding two, AI as the ultimate decision support tool.
Finding two states. AI provides data analysis and predictions to improve decision-making. This was strongly supported by 58% of the reviewed articles.
And the so what here is that AI isn't replacing the facility professional, nor is it just automatically adjusting the temperature. It's making the human in the loop smarter, faster, and more predictive in these high-stakes, high-cost decisions.
It gives them a real-time data interpretation and an awareness that they simply couldn't achieve by manually reviewing logs. This enables deeply informed decisions regarding large capital investments, like when to replace an aging chiller, for instance, or prioritizing system repairs and making subtle data-backed adjustments to long-term system operations.
So you move from being reactive.
You move definitively from reactive maintenance fixing things only after they break to true predictive decision-making.
What are some specific quantifiable examples of this predictive power that you found in the literature?
One key area is predicting comfort and energy consumption at the same time. Researchers deployed machine learning algorithms like K-nearest neighbor, that's KNN, and support vector regression, or SVR, to analyze streams of sensor output data.
And what were they measuring?
Things like occupants' activity levels, behaviors, and other characteristics.
So why those two algorithms specifically?
Well, the KNN algorithm is useful for classification. It can classify a state as comfortable or uncomfortable based on the data points surrounding it. And SVR, being a regression tool, is excellent for predicting continuous numerical values, like the exact energy consumption 12 hours from now. By using both, the algorithms could predict both the subjective outcome, which is occupant comfort, and the resulting objective cost, building energy consumption.
So the facility professional can literally see, okay, if I slightly adjust the airspeed in this zone to improve comfort from 80% satisfaction to 90%, the model predicts an associated 7% increase in energy consumption. It just removes the guesswork from that cost-comfort negotiation.
Exactly. They get a clear cost analysis for achieving marginal comfort gains. Another crucial application is overcoming internal heat gains. These are the dynamic heat loads generated by servers, lights, people, solar radiation.
Things that are notoriously difficult to model manually and can just sabotage your energy efficiency efforts.
Right, and studies demonstrated the use of specialized neural networks called long short-term memory networks, LSTMs, to predict and overcome these heat gains.
And what makes LSTM so good for that?
LSTMs are fantastic at handling sequential data, which is crucial here, because the heat generated by a piece of equipment, or the sun's angle, is a sequence of events over time. The LSTM predicts the trajectory of the heat gain, allowing the system to preemptively condition the space.
So it avoids those reactive cooling spikes?
Precisely. LSTMs are great at recognizing those time series patterns. They can learn, for instance, that every Tuesday afternoon after the finance meeting, Zone 4 always spikes in temperature, allowing for a proactive adjustment before the human even feels the difference.
That's a whole nother level. And perhaps the most financially impactful application addresses grid management, which is load shifting during peak demand. That's a crucial business decision.
A high-stakes decision, too. Peak electric grid demand periods mean exponentially higher energy rates.
So what did the research show there?
It specifically mentioned the use of generalized additive models to inform decision-makers about which non-essential building systems should be momentarily turned off or shifted during these high-cost peak intervals.
So the AI predicts the peak and suggests the least disruptive strategy.
Right. Maybe it's pausing non-critical ventilation for 30 minutes or pre-cooling the building so systems can run lighter during that peak window.
And we have measurable bottom line results for this, don't we? What was the financial proof?
We do. There was a notable 2-year building experiment where a proprietary machine algorithm integrating about 21,000 points of continuous building data into a thermal model informed decision makers on opportunities to strategically ramp systems up and down.
And the savings?
During that experiment, the facility managers, using the AI's recommendations, saved between 2% and 6% per year in whole building energy costs.
Let's put that 6% in context. For a large commercial office tower spending, let's say $1.5 million a year on energy, a 6% savings is $90,000 annually. That single figure justifies the entire investment in the decision support system.
It absolutely does. And this efficiency gain ties directly back to that adaptive structuration theory we talked about. The BMS and CMMS systems are the structural features storing the data. The AI algorithm acts on this data, transforming it into emergent sources of structure, the savings predictions.
And the facility professional then accesses that new structure to make the informed decision, completing the loop.
Completing the loop and generating massive tangible benefits.
Okay, moving on to finding 3, we look at how AI enhances the continuous moment-to-moment monitoring and operational efficiency of the mechanical systems themselves.
Finding 3 states. AI improves energy management and occupant comfort monitoring. This was supported by 38% of the articles reviewed.
So this is less about the big investment decisions of finding 2 and more about the ongoing minute-by-minute system optimization.
That's correct. It's about leveraging AI to create next-generation system control that is constantly predicting and reacting to variables in a highly nuanced way. It's trying to move the system from a static set-point operation to a dynamic predictive operation.
Can you give us an example of how AI makes these control decisions fundamentally better than a standard building automation system?
Sure. Researchers developed a physics-based state space model to predict temperature and relative humidity in a multi-story building. A physics-based model uses the immutable laws of thermodynamics.
Right, how heat moves and so on.
To predict outcomes. But they combined this with a robust model predictive control system. And crucially, they also used k-means clustering, a machine learning technique, to handle the uncertainty of external weather conditions.
Why is k-means clustering necessary when you already have a physics model?
Because external weather is the greatest source of uncertainty. K-mean clustering is an unsupervised learning method that groups similar data points together. In this case, it was used to cluster days with similar non-standard weather patterns, like unexpected cold fronts or sudden humidity spikes.
So it finds patterns in the weather itself.
Exactly. This allowed the AI to identify which historical operational decisions worked best for that specific clustered weather type and optimize the control decisions for temperature and humidity.
So they're using both the raw, immutable laws of physics and complex machine learning to predict the outcome of outside weather uncertainty on the inside environment. That integration is a massive leap beyond standard control.
It is. And it led to significant reductions in energy consumption by avoiding over or under conditioning the building based on inaccurate weather predictions.
Now let's talk about that unexpected AI tool. We mentioned it earlier, but was ChatGPT seriously used in some of this high-level mechanical research?
Yes, the source material explicitly mentions successful experimentation with ChatGPT in facility operations. Specifically, researchers used it for monitoring chilled water flow. The LLM was trained to determine the optimal chilled water supply temperature and provide monitoring metrics and summary reports directly to facility professionals.
That is fascinating. So the public thinks of ChatGPT for drafting emails, but here it's acting as a real-time text-based translator for complex mechanical sensor data. What's the benefit over just a standard dashboard?
The benefit is likely in its ability to synthesize complex multi-sensor data into easily digestible language, providing context and implications rather than just raw numbers. It essentially explains why the chilled water temperature is optimal or not. It becomes a conversational decision support tool.
And we also saw the use of the transformer model architecture, the foundation of LLMs in forecasting, correct?
Absolutely. Predictive control methodology was employed using the foundational transformer model architecture for 60-minute forecasting. This reduced energy consumption and improved comfort by informing decision makers on necessary adjustments to make first thing in the morning.
So if the model predicts a severe heat spike at 9 a.m., the facility professional arriving at 7 a.m. knows to adjust the ramp-up schedule strategically.
Exactly. Pre-cooling the space gently rather than reactively hammering the system later. They rely entirely on the prediction data supplied by the model. This capability for strategic analytics is key to efficiency.
Findings 2 and 3 highlight how AI helps the professional manage the systems and the budget. Finding 4 brings the focus back squarely onto the individual occupant, validating the comfort side of our core conflict.
Finding 4 states, the use of AI stabilizes and improves occupant comfort. This, like finding 3, was supported by 48% of the reviewed articles.
And when we talk about stabilization, we're talking about maintaining satisfactory indoor air quality, which is critical not just for comfort, but for health and productivity.
Right, and we can return to that ChatGPT example for a comparison. Researchers successfully maintained satisfactory indoor air quality and carbon dioxide levels by employing the ChatGPT model to control HVAC units. It was used as a reactive measure, trained to continuously provide the most significant reward, in this case, good IAQ.
But I remember a critical comparison here. The AI tool that the public is most familiar with, ChatGPT, was actually outperformed by another algorithm in the same experiment.
Yes, and that's an extremely important nuance for you to take away. No single algorithm is universal. In the same controlled experiment, the researchers also employed a deep Q network, which is a specialized reinforcement learning technology.
And the results?
The Deep Q network actually yielded better results for both indoor air quality stabilization and energy consumption than ChatGPT did.
Why do you think that is? Why would a purpose-built control algorithm outperform a general large language model?
Well, LLMs like ChatGPT are primarily trained for sequence generation and probability matching on massive text data sets. While they can interpret data streams, as we saw, they aren't inherently optimized for dynamic physical control loops where timing and precision are paramount.
It's just not what they're built for.
Not really. The Deep Q network, being purpose-built reinforcement learning, excels at learning the complex, nonlinear dynamics of a physical system. How a change in damper position 10 minutes ago impacts CO2 levels now. It learns the mechanics of the HVAC system much more intimately.
So it reinforces the need to test specialized AI tools for specialized jobs.
That's the key takeaway. And beyond just controlling the climate, efficiency also hinges on knowing who is in the building. That means occupancy rate is a crucial variable for effective stabilization.
Right, it's the foundation. If you know a floor is empty, you don't need to be conditioning the air there.
And researchers employed a high-performance technique for object detection called the You Only Look Once algorithm, or YOLO.
YOLO. That's a high-speed object detection framework you usually hear about in applications like self-driving cars. How accurate was it in the occupancy context?
They determined occupancy with a respectable accuracy of 83%. However, they also identified a clear, real-world limitation.
What's that?
The accuracy of detection is significantly complicated when occupants operate and move close to one another, or if there's visual occlusion.
That makes perfect sense. AI can count clearly separated individuals, but when people cluster up for a meeting, the detection gets fuzzy, potentially leading to inaccurate counts and unnecessary conditioning. It's a hardware placement challenge as much as an algorithm one.
Correct. But looking towards the future of dynamic comfort, researchers are pushing beyond fixed sensors and occupancy counts entirely. One fascinating experiment used wearable wristbands to measure occupants' physiological data like heart rate, skin temperature, and body movement, alongside the indoor environmental data.
So now the input is coming directly from the human body, not just the wall sensor. That's true personalization.
Exactly. Employing transfer learning-based models, the authors could predict and forecast occupants' thermal comfort dynamically, learning individual patterns. Their explicit goal for future research was to use this personal physiological data to achieve comfort that is truly dynamic and personalized.
It's the final step in resolving the thermostat warrior conflict.
It is. Customizing the environment based on the specific physical needs of the person in it.
That brings us to Section 4. We've used the general term AI a lot, but the literature shows that AI in this space is a highly diverse toolbox. We need to move beyond that general term and showcase the specific algorithms researchers are actually deploying.
It's absolutely a spectrum of tools, and each one is suited for a specific task or decision type. Facility professionals interested in this need to understand that the choice of algorithm depends entirely on the context. Are you predicting a sequence of events, classifying an outcome, or controlling a system in real time?
So let's run through the high-impact algorithms that were highlighted in the research and their specific purposes.
Certainly. We spent a good deal of time on reinforcement learning, RL, specifically the A3C and Deep Q network variations. Their purpose is high-level, continuous system control managing thermodynamics, optimizing energy efficiency, and controlling indoor air quality.
Then we have the workhorse of statistical machine learning, Artificial neural networks, ANN.
ANNs are used broadly across the board because of their ability to model complex nonlinear relationships. They're applied for general HVAC operations, long-term prediction of energy loads, and general comfort improvements. They're highly adaptable.
And what about that chat tool again, ChatGPT?
Its specific application noted in the research was HVAC control and monitoring CO2 levels, acting as a real-time data interpretation agent, helping to translate complex system status into human-readable insights.
And one of the most intriguing high-level tools designed specifically for decision support is the digital twin concept.
The digital twin is absolutely crucial for strategic decision support. Its purpose is to provide a comprehensive, physics-accurate digital representation of the entire building.
The whole building.
The whole building, all its facility systems, occupancy models, energy dynamics, everything.
And what's the practical benefit of that for the facility manager?
It allows them to make changes to operational parameters, for example, changing a pump speed or adjusting a ventilation schedule virtually, and see the long-term effects on energy or comfort before ever implementing those changes in the real world. It mitigates risk and allows for rapid testing of hypothetical improvements.
That drastically improves the decision-making process by reducing uncertainty and capital waste. We also saw some classic ML tools involved in the research.
Yes, the standard regression and classification algorithms remain vital. Support vector machine, SVM, and random forest algorithms were specifically used for total energy consumption analysis, thermal comfort assessment, and prediction. They often serve as baselines against which newer, deeper learning models are compared.
Now that we have the full toolkit, let's zoom back out and show the listener how all these parts, the tools, the systems, the people integrate into the revised conceptual framework that the research developed. This is that adaptive structuration theory model brought to life.
This revised model, based on the synthesis of the 31 articles, is a sophisticated closed-loop system showing the flow of data and the structure of the decision process. It starts with the structural features on the left.
That's the occupant comfort input measured by the IoT sensors.
Right. Those sensors measure all the critical elements we discussed: lighting, thermal comfort, noise level, environmental factors. That raw data then flows into the data repository, which is the CMMS, and the BMS, the existing system infrastructure.
And this is the key update. The AI technology is located within that repository.
Exactly. The artificial intelligence technology sits as the interpreter. It takes the IoT data, feedback from past maintenance actions stored in the CMMS, and real-time energy management information and processes it using the algorithms we've discussed, the LSTMs, the DeepQ networks, the YOLO detectors.
And the result of that interpretation is then sent to the actor, the facility professional.
Correct. The facility professional receives the AI interpretations as real-time data inputs on specialized dashboards, prescriptive recommendations, or alerts, and makes a decision. This is the moment where the human structure interacts with the technological structure.
And what's critical here, which the model emphasizes, is the closed-loop feedback.
Precisely. The facility professional decision moderates feedback back into the entire system. Back to the BMS for control adjustments, back to the IoT devices to maybe recalibrate a sensor, and crucially back to the AI technology itself, allowing it to continuously learn and refine its model based on the human outcome.
And that decision then directly influences the total energy demand and ultimately the energy cost, completing the full cycle of the system.
It's a dynamic learning environment.
It's a beautifully structured system designed to replace guesswork with predictive, informed, and responsive control, elevating the facility manager from a reactive technician to a predictive strategist. Okay, we've spent so much time describing the incredible potential, the advanced algorithms, the measurable benefits, saving $90,000 a year, solving the thermostat warrior conflict with biosensors. Now we arrive at the segment that grounds this research in the harsh reality of implementation. This was, perhaps, the most unanticipated discovery of the systematic review.
This is the critical grounding fact that you really need to understand. Despite the 31 articles reviewed being original, high-level research detailing the technology's measurable benefits, and many studies being conducted as successful experiments on existing operational building systems, the researchers found a major disconnect.
Which was?
None of the articles indicated that the technology studied was in actual operational use in a U.S. facility for occupant comfort analysis at the time of the study.
Wait, say that again?
The technology was proven but not deployed.
Wow. So all this deep research, all those successful 2-year experiments, but zero confirmed real-world, day-to-day deployment in the United States for this specific application at the time of the research. That shows an immense, yawning gap between R&D and actual commercial implementation.
It suggests that while the facility management industry in the United States is actively conducting cutting-edge experiments, they recognize the potential. They are, as an industry, extremely slow to transition to using this artificial intelligence operationally.
So the theoretical adoption is high, but the practical adoption is currently near zero.
That's a good way to put it. And the slow transition contracts sharply with the sheer scale of the research interest. You mentioned earlier the timeline was explosive.
It was.
The source material noted that 2012 articles were initially downloaded for the review. Of those, 689 related directly to occupant comfort variables. But what's most striking is the timeline. 582 of those comfort-related articles were published just between 2018 and 2023.
That is an enormous academic and industry push in just 5 years to understand and solve this personal, complex, and expensive problem. The interest and the experimental proof of concept are clearly there, but the operational deployment isn't following the research yet.
Exactly. So if the benefits are so clear, like achieving 6% energy savings, what are the specific barriers causing this disconnect? Why is the U.S. industry, which stands to save tens of thousands annually per building, hesitant to cross that chasm from experiment to operation?
We have to revisit the challenges category that emerged during those rigorous coding cycles.
The primary hindrance lies in the foundational requirements of AI itself. AI implementation is heavily hindered by the requirement for large data sets and the corresponding need for extensive, often expensive, large sensor networks to feed that data.
Right. Facility managers often work with legacy buildings that lack the granular sensor coverage needed to train or run these sophisticated models effectively.
And you can't just throw new sensors in everywhere without massive upfront cost. And then there's the flip side. When they try to gather data, they face issues of limited data because of organizational silos or data security concerns. It's a catch-22.
It is. A deep queue network needs continuous, clean data streams over years to achieve optimal control. If that data is sparse or dirty or intermittent, the complex algorithm is basically useless.
Beyond the data and hardware, what about the human element? The training issues must be significant when you're introducing this kind of complexity into a field built on mechanical intuition.
The practical, non-technical barriers remain significant. The research highlighted the associated barrier of undetermined costs for deploying these systems at scale, which makes securing executive approval difficult, and the inevitable need for increased manpower and specialized training problems for the existing workforce.
Let's focus on that training problem for a second. The challenge isn't just knowing how to read the AI dashboard. It's training a technician who is used to wrenching valves and replacing parts based on 20 years of gut feeling and intuition to trust a predictive algorithm over their own experience.
That requires a fundamental shift in that group's internal system as defined by the AST.
That is the core barrier. It's a crisis of trust and a skills gap. If the AI suggests turning off a massive pump based on a prediction of future energy prices, the technician needs the training and confidence to override their internal cultural structure, which might say, run the pump manually to be safe, and trust the new structure provided by the AI dashboard.
And that requires massive organizational investment and training.
It does. So what does this all mean for you, the learner, in real terms?
It means this is not a mature market. It's a field that is rapidly accelerating right now.
The research is prolific, the technical proofs of concept are clear, but the transition to operational use in the U.S. is just beginning. Understanding these underlying principles, the different algorithms, the conceptual frameworks like AST, the proven benefits, puts you ahead of the curve as this transition accelerates from theory to mandatory practice.
The people who understand why the deep queue network beat ChatGPT are the ones who are going to lead this transformation.
Exactly.
So let's bring this deep dive full circle. We started with that central expensive conflict, balancing energy cost and thermal happiness, primarily managed by the HVAC system, and we discovered the 4 core findings that explain AI's transformative role.
Finding 1 confirmed the U.S. research focus is overwhelmingly on thermal comfort and occupancy via HVAC controls, the most energy-intensive system. Finding 2 showed AI acts as a sophisticated decision support system, providing real-time data analysis and quantifiable predictions for major strategic decisions.
Finding 3 demonstrated AI's ability to enhance monitoring and efficiency, giving us next-generation control systems that can integrate physics-based models with advanced clustering algorithms. And finding 4 show that AI stabilizes and improves occupant comfort using specialized tools from deep Q networks to occupancy detection via the YOLO algorithm, moving steadily toward dynamic, personalized comfort.
We also map this entire process through the crucial lens of the adaptive structuration theory. The technology, the AI, the IoT sensors forms the structural features. The facility professional interacts with these features, generating new social structures, the real-time predictive dashboard, which allows them to move past historical assumptions and make better decisions.
But the punchline, the grounding reality check, is that despite all this compelling, positive experimental data, we're currently seeing a significant delay in operational implementation across U.S. facilities. And that's due to systemic issues like overwhelming data requirements, ambiguous deployment costs, and the need for a massive overhaul in workforce training and organizational trust.
The ultimate goal for the industry is to move past those existing cultural assumptions, that group's internal system that resists change, and embrace the new social structures created by these AI dashboards. This is the necessary path to ensuring better energy outcomes and better comfort outcomes, achieving both sides of the conflict, not one or the other.
That is a phenomenal amount of information synthesized from a stack of complex technical papers. Before we sign off, the source material had one suggestion for future research, which leads perfectly to our final provocative thought for you, the listener.
The source material explicitly mentioned that future research should expand beyond the United States to assess the use and adoption of AI in other countries. So, if U.S. researchers, as Finding One shows, are focusing so heavily on the specific, expensive challenge of thermal comfort in HVAC, what entirely different variables or problems might AI be solving in facilities globally right now?
That's a great question.
I mean, perhaps in regions where energy costs are radically higher or lower, or where infrastructure is fundamentally different, they might be prioritizing entirely different solutions, like water conservation or security optimization. What unique cultural or economic assumptions, what different structural features might be driving entirely different adoption rates and experimental focuses overseas?
It suggests that the U.S. may only be solving one small, albeit expensive, part of the global smart building puzzle, something to mull over as you adjust your own environment this evening. Thank you for diving deep with us. We'll see you next time. Welcome back to The Deep Dive, the only place where we turn massive stacks of specialized research into actionable, unforgettable knowledge.
Glad to be here.
Today, we are tackling a monster of a problem. I mean, it's one that lurks within the walls of, well, nearly every commercial building out there.
It's that delicate, and I mean really financially perilous balancing act that facility managers have to perform every single day.
Yeah, you've got skyrocketing energy costs on one side, and on the other, the absolute necessity of keeping the people inside the building comfortable and, productive.
And we are not talking about small discrepancies here. The inability to strike that perfect balance, I mean, relying on these outdated, inefficient systems and then just failing to satisfy occupants, it's a silent budget killer.
It really is, and you're right to point to the data, because the most shocking number from this research, the one we have to start with, is this. Organizations in the United States alone are losing a staggering $15 billion annually, all because of poorly operated facilities.
$15 billion. It's a number that's almost hard to wrap your head around, but it's real.
It should be a wake-up call for every CEO and CFO listening. So where does that $15 billion go? It's not just one line item, right?
Not at all. It's a combination of things. First, you've got excessive energy consumption because these systems are just constantly overcompensating for poor design or, bad management.
Just running full tilt all the time.
All the time. Then there are the high labor costs. Think about the facility staff who are just constantly in reactive mode, running from one too hot or too cold complaint to the next.
And I guess the most insidious cost, the one that's harder to track, is productivity.
That's it, is the reduced productivity and maybe even increased turnover from people who are just too uncomfortable to focus on their actual jobs. It's the cost of dissatisfaction.
And our mission today is to cut through all that noise and show you exactly how to tackle that $15 billion problem head on.
Right. We're taking a systematic deep dive into the findings of a comprehensive academic review, which analyzed 31 different peer-reviewed articles. Our goal is to synthesize precisely how one powerful, evolving tool, artificial intelligence, can fundamentally change the game for facility professionals.
Okay, so let's define our terms, because AI is a buzzword that gets thrown around a lot. For this to work, we have to know what we mean by AI in this very specific context.
That is absolutely vital. In the context of this review, AI isn't some science fiction concept of a thinking machine.
Right.
It is operationally defined by what it does. And what it does is act as a system of predictive statistical models.
Okay, so it's math. It's advanced math.
It's very advanced math.
Mhm.
And this broad definition covers a whole array of technologies you might encounter. Things like neural networks, which sort of mimic the human brain to process data. Robotics, which apply the models to physical tasks.
And then the ones we hear about more often, like machine learning.
Exactly. Machine learning and deep learning are under that umbrella. It's all about using weighted factors to evaluate data for a functional, predictable use.
So we're talking about these highly sophisticated systems that can look at massive amounts of unstructured building data and use it to predict outcomes and then suggest or even execute system adjustments. It's about using information for prediction, not just, logging it.
That's the core of it. And so the central objective, the main question the systematic review wanted to answer was super focused. It was, how can AI enhance the decision-making of facility professionals to improve energy management while satisfying occupant comfort?
The two sides of that balancing act we mentioned.
The two sides of the coin. And the most critical takeaway, the thread that's going to run through everything we discussed today, is that these findings show a clear path for facility operations to move from that universally recognized reactive mode.
Which is waiting for the complaint call.
Waiting for the call. Waiting for the energy bill spike. Waiting for the system to fail. It's about moving from that to a truly proactive mode, where you are predicting and preventing problems before they ever even impact the occupant or, just as importantly, the budget.
That transition alone is a complete paradigm shift for anyone managing a large portfolio of buildings. So let's jump in. Where did the researchers start? What was the first big finding?
Well, it was a fascinating and, as they noted, an unanticipated one. It really sets the stage by showing just how inefficient the current state of comfort monitoring really is.
Okay, so the study's first key finding shines a spotlight on a core limitation in building science today. What is it?
It's that in the United States, the research, and by extension of the common industry practice, still heavily centers on measuring thermal comfort and occupancy only through the lens of basic HVAC control.
So everything is viewed through the heating and air conditioning system.
Exactly. This reliance is what the source calls the building standard approach, and it points to this huge systemic inefficiency in how we manage commercial office buildings.
The status quo is inefficient by design, then.
It is, because the sensing mechanism that most facilities rely on is centered around measuring the return air.
Okay, explain what that means for someone who isn't an HVAC tech.
Sure. So you have air being blown into a room,
Oh.
right? The return air is the air that's being pulled back into the system to be reconditioned. And the sensor that measures its temperature is usually located somewhere in the ceiling, maybe 50 or even 100 feet away from where you're actually sitting.
I see the problem immediately. So you're measuring the air temperature way up there, not down here where the actual person is.
Precisely. Relying solely on the temperature of the air returning to the handler just cannot accurately represent the comfort level across an entire, often very complex office environment.
Right. The system might think everything's perfect at 72 degrees, but if I'm sitting next to a huge, unshaded window in the afternoon sun, I'm roasting. The system has no idea.
It has no idea you're baking, or that the person under the supply vent is freezing. This is why facility management so often overlooks this complex interplay of all the environmental variables that truly contribute to a person's feeling of comfort. It's never just one number on a thermostat.
So let's detail those variables, because if you're a facility manager listening, this is basically the new checklist for what you should be measuring.
Absolutely. So you have the obvious ones, like the actual air temperature and that return air temperature we just mentioned.
Mm-hmm.
But then you have humidity, which dramatically changes how temperature feels.
100%. 80 degrees dry is very different from 80 degrees humid.
Very different. Then there's airspeed. Is there a draft? There's radiant temperature, which is the heat coming off surfaces, that hot wall from the sun, or a cold window pane in winter.
Okay, that's a big one that I think most people don't consider.
It's huge.
Yeah.
And finally, things like the damper settings in the ductwork, which control how much air is flowing into specific zones.
So when you're not directly monitoring this whole suite of variables where people actually are, you're flying blind.
You are flying blind, and you are guaranteed to contribute to occupant dissatisfaction. It's a fundamentally inefficient and therefore very costly way to operate a building. It's like trying to solve a puzzle with half the pieces missing.
So if that return air standard is the problem, what's the alternative? How do you get the sensor closer to the person without, taping a thermometer to everyone's forehead?
Well, the alternative is already being rigorously tested in the scientific literature. It's the integration of AI and IoT sensors for what the researchers call biosensing of occupant comfort.
Biosensing. Okay, break that down. It sounds a little sci-fi.
It does, but it's actually pretty straightforward. It's
Yeah.
just a term for using a distributed network of specialized low-cost sensors to measure multiple data points at once. So instead of one thermometer in the ceiling, you might have sensors integrated into light fixtures, or desks, or wall panels.
So it's not just measuring the air temperature. It's measuring the radiant heat from my laptop, the humidity right at my desk, the airspeed from the vent above me, all at the same time.
All at the same time. That's the promise. Instead of waiting for a sensor 50 feet away to report on old news, this network gives you direct, localized indicators of comfort factors.
And the study showed this actually works.
They do. Studies cited in the review show successful tests where AI algorithms, fed by this really nuanced biosensing data, communicate directly with the HVAC systems. They sense and predict these factors, not just temperature, to control the environment in a microzone. It gives them a direct impact on occupants in near real time.
It's the difference between a blunt instrument and a surgical tool.
That's a perfect way to put it. And the core implication of this first finding is that many of these highly effective cross-functional AI algorithms are just being underexploited in the US.
So the technology's there, we're just not using it.
For the most part, yeah. There's this massive, untapped opportunity for building operations to move toward biosensing and get that direct line of sight into occupant comfort that we're all missing.
Okay, but implementation is never that simple. If it's so effective, what are the challenges? Where did the literature say these systems struggle?
The literature flagged two main environmental challenges, where the AI can sometimes struggle to optimize comfort without, ironically, using too much energy. The first is in excessively populated settings.
Like a big lecture hall or a crowded open-plan office.
Exactly. Think of a big corporate training room. The challenge is, well, it's too many signals. When people gather that close together, the sheer density of human activity, their combined body heat, their movement, their different metabolic rates, it all just muddles the data.
So the AI gets overwhelmed.
It gets overwhelmed. It can't cleanly isolate individual occupants to figure out an accurate, localized comfort metric for everyone. The signal just gets lost in the noise of too many people.
Okay, so that's one problem. What's the second?
The second is fast-moving environments. So think of fitness centers, sports complexes, or even big shopping malls where people are moving around rapidly and constantly.
Right, they're not just sitting at a desk.
Not at all. And in these settings, the AI sometimes tries to respond to every little bit of movement, like a sudden burst of heat from people exercising. But in trying to stabilize a constantly destabilized environment, the system can overcompensate and actually end up increasing energy costs. It's too reactive.
It's too quick on the trigger, wasting energy on a situation that might only be temporary. So how do we get around these problems? Is the tech just not ready for those spaces?
Well, the consensus in the sources suggests this isn't a permanent flaw, but more of a refinement issue. They recommend intensive training technology, basically, using machine learning to teach the AI about these specific environments.
So you feed it historical data.
You feed it historical movement patterns, you establish density thresholds, you teach the AI to be a little more patient, essentially. With enough training, it can learn to provide the necessary analysis and control, even in these really challenging settings. It's just an investment in making the AI smarter.
That's a fascinating look at where we are and where we could be. So we know the current state is inefficient. We know biosensing is the path forward. Let's pivot now to the core of the study, how AI specifically enhances decision-making for facility managers. Okay, so the review systematically identified 3 concrete ways that AI answers that central research question. It covers data, energy, and comfort. Let's tackle them one by one, starting with the foundation, which is finding 2 on data analysis and prediction.
To really understand the power of AI here, you first have to appreciate the sheer volume of data that facility management generates. I mean, it's an enormous, overwhelming quantity of unstructured data.
And what do you mean by unstructured?
It just means it wasn't collected or tagged in a way that lets it easily talk to other systems. It's just raw data flowing constantly into 2 main systems in an organization.
Let's break down where this data lives, because I think the fact that it's in 2 separate places is the human hurdle the AI needs to clear.
Absolutely. The first major data silo is a BMS, or building management system. This is the operational side. It's where all the real-time data from your IoT sensors, smart meters, HVAC controllers, security devices, all that stuff gets collected and stored. It tells you what's happening right now.
And the second silo is the historical record.
That's the CMMS, or computerized maintenance management system. This stores all the historical data about maintenance, preventative maintenance schedules, corrective actions, parts used, and critically, the history of every single service call a person has ever made.
Okay, so when you put those two massive data silos together, the real-time operational data and the long-term maintenance history, it becomes crystal clear why solving a recurring problem is such a huge time sink for people.
It is the definition of the human hurdle. I mean, imagine a determined facility tech trying to figure out why a specific zone on the third floor is always complaining about drafts.
Right.
They have to manually comb through years of service calls in the CMMS, then try to cross-reference those dates with operational data in the BMS from those same days, looking for a correlation. It takes hours, days, sometimes even weeks of screening, sorting, and evaluating.
And all while the people in that office are still complaining.
Exactly. It just exacerbates the negative feelings around an already urgent complaint. It's like looking for a needle in two different haystacks at the same time.
And this is where the AI solution becomes, well, not just nice to have, but essential.
The advantage is speed and synthesis. AI algorithms can do that massive analysis almost in real time. They can access and make functional use of all that vast unstructured data across both the BMS and the CMMS simultaneously. It can spot patterns a human might never see in their entire career.
And the output of that analysis is what translates directly into saving resources. People, time, and money. What are the key predictive outputs that the study highlighted?
The predictions are where the real value is. The AI can predict thermal comfort levels in specific microzones. It can predict occupant activity and overall occupancy in large areas based on historical use.
So it knows the big conference room will be full at 10 a.m. on Tuesdays.
Exactly. It can also predict detailed energy usage patterns, often pinpointing the exact piece of equipment that's about to cause a spike. And, crucially, it can predict the ability to turn off inessential equipment without compromising service, which is huge for efficiency during off hours.
Let's get into the mechanics a little. The research provides a conceptual data flow diagram. We see these raw inputs, occupant characteristics, occupancy, weather feeding into specific AI models. Let's slow down and explain what these models actually do.
Agreed. Let's demystify them. First up, you have something called random forest. Now, instead of thinking of one single complex equation, think of it like a big committee of different experts. Each expert, or decision tree, analyzes the data separately. One might look only at weather, another at historical complaints, another at humidity. Then they all vote on the best prediction. Say, will Zone 4 be too hot tomorrow at 2 p.m.? Random forest takes the consensus of all those votes, which gives you an extremely reliable, robust prediction.
So it's strength in numbers. It reduces the chance of one bad prediction throwing everything off.
Exactly. Then you have CNN, or convolutional neural network. These are famous for things like image recognition, but in a facility, they're fantastic for recognizing spatial and temporal patterns.
How does that work in a building?
Well, if you have a massive grid of IoT sensors providing a sort of digital heat map of your building, the CNN is uniquely suited to spot the spatial pattern. It can say, aha, this is where the hot spot always starts, or this is the pattern of energy use that always comes before a major system failure. It processes the data grid to understand the location and intensity of a problem.
So that's how it finds and helps eliminate those notorious hot and cold spots.
That's a key tool for it. And finally, you have KNN, or K-nearest neighbors.
Okay.
KNN is a classification model that's all about similarity. So imagine a new situation arises, a specific combination of outside temperature, occupancy, and CO2 levels. KNN looks through your massive database and finds the K closest, most similar historical days.
And it assumes today will be like those days.
Pretty much. If the 5 most similar days in the past all resulted in an air handling unit failure, the KNN model predicts a high probability of failure today. It makes predictions based on historical precedent.
And these sophisticated models, they don't just exist in a vacuum. The diagram shows them fully integrated.
No, they're fully integrated.
Right.
They interact directly with the BMS, that central hub of the building's operational data. That interaction then directly influences the HVAC controls, which is the physical action point where the system actually starts adjusting dampers and fans and chillers.
So the data flows from prediction to action automatically.
Right. And you might even have a more advanced transformer model layered on top, which is excellent at processing data over long periods of time, making those really complex long-term predictions about system maintenance and optimal set points, this whole integrated dynamic data flow. That is the definition of data-driven decision-making, and that builds directly into finding 3, which is all about how this improves operational processes and, critically, energy management.
Yeah, the philosophical shift.
It's a huge philosophical shift. We move from systems reacting to a complaint or an energy spike to systems automatically responding to needs that are predicted before they even happen.
It's the difference between driving a car using only the rearview mirror versus having a GPS that sees traffic 10 miles ahead.
That's a perfect analogy. And when AI is fully implemented, the level of full automation capabilities is truly next generation. The technology can predict future occupancy patterns, not just who's here now, but when meetings are scheduled to end, when a big delivery is due, and based on that, it can exercise systems.
What do you mean by exercise systems?
It means starting, idling, or adjusting system settings proactively to precisely match that predicted occupancy and the environmental needs. So it's not just on or off. It's a constant, subtle adjustment.
I can just imagine the energy savings from managing that peak load.
It's massive. And it's not just anticipation, it's smarter run cycles. In existing non-AI energy programs, technicians are monitoring things on a static, reactive basis. They might check readings once a week or look at the utility bill at the end of the month.
At which point, the damage is already done. The money's already spent.
The money is spent. And because it's impossible for a human to scan all the factors across hundreds of pieces of equipment at once, these localized energy spikes or equipment drift often go completely unnoticed until the bill arrives, or worse, until the equipment fails.
So the AI is like having a technician watching every single piece of equipment 24/7.
24/7. It provides real-time monitoring of output systems across the entire building. The state of the chillers, the fans, the variable air volume boxes, all simultaneously. So if a specific fan coil unit on the 10th floor starts drawing excessive energy, the AI knows immediately.
It doesn't wait for a complaint.
It doesn't wait. It knows instantly, which allows for proactive intervention. The AI can adjust the parameters, run a diagnostic, or alert a technician before the problem becomes a failure or a huge financial drain. This reduces the need for that constant manual human intervention, freeing up your technicians for higher-level work, all while drastically improving energy conservation.
Okay, so that covers data and energy. Let's shift now to the final piece of the puzzle, which is finding 4, stabilizing and improving occupant comfort. This is about the human experience inside the building.
Right. And stabilizing comfort is inherently tied to monitoring occupancy, the whole spectrum of indoor air quality, IAQ factors, and those local environmental conditions using the sensor networks we talked about.
And the core value AI delivers here is eliminating inconsistencies. We're talking about those infamous hot and cold spots.
Exactly. Those areas that never seem to be comfortable no matter how many times a tech adjusts the local thermostat. They're often caused by unique variables, solar heat gain, poor insulation, that a standard BMS just can't account for globally.
But the AI can see those local factors.
It can see them and works relentlessly to eliminate those inconsistencies. And what's more, it's not starting from scratch. The algorithms can be trained by evaluating years of historical records, the complaint data, the weather data, the BMS settings, to stabilize the environment, to provide historically comfortable conditions. It learns what works best for that specific building and those specific occupants over time.
Let's talk about occupancy sensing, because that's a technology most people have seen, but AI completely upgrades it.
It does. Traditional occupancy sensors are purely reactive. The lights turn on after you walk into the room. The system is always playing catch-up, trying to condition a space that's already uncomfortable. The AI approach, cited in the literature, moves this firmly into the realm of true prediction. By integrating scheduling data, historical patterns, even weather forecasts, AI allows for advanced predictions, so spaces can be pre-cooled or preconditioned before anyone even arrives.
Pre-cooling is such a brilliant application. It's managing energy demand. The system anticipates the need and runs optimally before the peak load hits.
Exactly. It ramps up the chiller at 6 a.m. instead of slamming it on at 8:30 when everyone walks in. This saves energy, it reduces wear and tear, and reduces complaints because the environment is perfect the moment you open the door.
So it's a stable, consistent environment. And what about that next layer, indoor air quality?
So right now, technicians monitor IAQ variables like CO2, humidity, and fan speed through the BMS. But the research suggests that an advanced AI could synthesize all of those conditions into a single, comprehensive, actionable report.
The source even references ChatGPT as a conceptual example of this. Now, that sounds a little strange. Is the AI going to write me a poem about my office's CO2 levels?
No, not poetry, but synthesis. Think of it less like a chatbot and more like a powerful model designed to synthesize massive amounts of complex data into simple, actionable summaries.
Okay, so give me an example.
Instead of a tech having to pull up 15 different graphs and logs to figure out why the air feels stale, the AI synthesizes all the inputs and generates a one-page report instantly. It would say something like, humidity is high, the outdoor air damper is only 30% open because of the morning cold snap, and the filter on AHU4 was due for a change 3 weeks ago. Recommendation: increase the damper opening and generate a filter replacement work order.
Wow. That completely flips the technician's role. They stop being a data detective and start being a strategic decision maker.
Precisely. The AI doesn't replace the technician, it elevates them. And this kind of advanced output, by ensuring equipment is always operating within its optimal parameters, would not only improve occupant comfort, but would also significantly extend the life of that very expensive facility equipment.
It really sounds like a win-win-win. Happier people, longer-lasting equipment, and huge energy savings. So now that we understand the benefits, let's get practical. What are the concrete steps managers can take to actually adopt this?
The systematic review came up with 4 major recommendations for managers and practitioners, and they're all centered on making that strategic shift to data-backed, proactive decision-making. It's really more about leadership and culture change than just buying new gadgets.
Okay, so what's recommendation number 1?
It's fundamental. You have to initiate a strategic, top-down goal focused on measuring and considering all elements of occupant and thermal comfort, not just the number on the thermostat.
So it's a mandate to focus on the whole environmental picture, all 6 of those variables we listed earlier.
All 6 of them. Humidity, airspeed, radiant temp, all of it.
That's the long-term goal. But what about facilities that can't afford a full AI rollout tomorrow? The research also suggests some immediate practical steps you can take today, right?
Absolutely. These are low-cost, high-return process updates you can do concurrently with the strategic planning. The first step is work control training. You have to train your clerks, your frontline staff, or update your online portals to get maximum detail from customers when they make a complaint.
So instead of just a ticket that says Office 305 is hot, you need more diagnostic info up front.
Way more. The intake system should guide the customer to provide richer data. Is this a new problem? Is it constant or only in the afternoon? Is the sun shining on the window? Is your desk next to a vent? Maximizing that detail at the very beginning is crucial.
And what about the technicians who actually go out on the job?
Step 2 is rigorous technician training. Techs have to be trained to look at the total environment, not just go in and take the air temperature. They need to check diffuser locations. Are they blowing cold air right on someone? They need to review the sensor readings, the set points. They need to solve the discomfort problem, not just the temperature problem.
And once the work order is closed, how do you know if the human problem was actually solved?
That's step 3, mandatory customer follow-up. After any work is done, someone has to follow up with the customer to make sure conditions actually improved. It's the only way to know if your action worked. It's a feedback loop that makes your whole process smarter.
And finally, quality control on the data you're collecting.
Yes, step 4 is implementing quality control by reviewing technician annotations. You need to ensure they are capturing maximum detail. This includes things like exterior environmental conditions. Was it overcast? Was the sun intense? Were there weird smells? Capturing all that environmental noise dramatically increases the quality of the data that will eventually feed your AI models.
It's so tempting to focus just on the tech, but recommendation 2 forces us to look inward. It says successful adoption relies on understanding the deep-seated historical and cultural assumptions within your organization.
If you ignore the people who actually run the buildings,
Yeah.
you are guaranteeing that your technology initiative will fail. It's the #1 cause. Let's start with historical assumptions. Facility professionals who have been on the job for decades have incredible value. They have this deep, intuitive understanding of their systems. When leaders bring in new, data-driven tech, they have to respect that experience. They need to show how the AI augments their experience, not replaces it.
So it's about showing them a tool that makes their intuition measurable and provable.
Exactly. You have to show them that the data validates, or sometimes even improves upon, their lifetime of expertise.
And what about the cultural side of things?
Cultural assumptions are huge. Individual culture brings a variety of perspectives, from deep skepticism to outright fear. Leaders can bridge that gap by directly linking the benefits of data-driven decisions to the actual outcome. If the AI prevents 5 chiller failures in a year, you show the technicians the data proving it.
You make it real for them.
You make it real, allowing them to interact with the technology, to test it, It makes it feel less like a top-down mandate and more like a powerful tool that's there to help them.
Okay, so beyond those internal human barriers, what's the single biggest challenge that the literature identified for any data-backed program?
It's the one everyone talks about, data security. As soon as you start collecting all this detailed building data, real-time energy use, occupant metrics, the risk profile of your building spikes dramatically. This data is sensitive.
So addressing this upfront is non-negotiable. What do you need to have in place before you even plug in the first sensor?
You need a robust set of protocols. This includes layered security, encryption-based data storage, strong network security to prevent unauthorized access, and strict controlled access management, so only authorized people can see the data.
And to get that right, you need a specific team.
You absolutely do. The organization should create a well-defined data initiation team.
Who's on that team? It sounds like more than just the IT guy.
It's a multidisciplinary skill set. The team has to have an information technology expert who understands the network architecture, a cybersecurity and data security expert who is focused purely on threats, a facility management expert who understands the critical nature of the operational data, and an AI consultant who knows the specific security needs of the algorithms being used. That team builds the necessary trust and security for the whole system to work safely.
That makes a ton of sense. So let's move to the last two recommendations, which are about getting started.
Right. And the third recommendation is maybe the most actionable and encouraging one for facilities with tight budgets. Start somewhere. You don't need to overhaul your entire building overnight to prove AI's value.
Just pick one problem.
Pick one problem. Identify your most grueling, mission-impacting challenge. The one that causes the most complaints, costs the most in labor, the one everyone dreads, and use AI specifically to solve that one challenge first.
Okay, give us some real-world examples of this. This is where it gets really interesting for someone who needs to convince their boss to even try this.
We have two fantastic examples from the airport industry that perfectly illustrate this start small philosophy. Take Pittsburgh International Airport, PIT.
Yeah.
They didn't start with comfort. They started with trash.
Trash.
They partnered with a company called Clean Robotics to test a solution called TrashBot.
So it sorts garbage. That seems a long way from optimizing an HVAC system.
It is, but the underlying challenge identifying materials and patterns is a classic AI problem. The TrashBot was an AI and robotic solution focused purely on managing the waste stream, accurately separating garbage from recyclables. And the result was spectacular. It achieved 96% accuracy.
Wow. Okay, that's a tangible, measurable result from a very focused AI project.
It is. And similarly, Seattle-Tacoma International Airport worked with a company called Intuitive AI to create a system called Oscar for waste sorting, and they also got very high accuracy rates. These projects had nothing to do with temperature, but they demonstrate a crucial point about change management.
Which is that a small, visible win builds confidence for bigger projects.
Precisely. These low-cost, high-visibility wins fundamentally change the organization's outlook on AI's potential. Once a manager sees 96% accuracy in recycling, they start thinking, if it can solve our waste stream so efficiently, what else can it solve? It's the proof of concept that paves the way for the bigger stuff.
And that opens the door for recommendation 4, which is about scaling that confidence. It says facility managers must interact with data science experts and strive to become data mature.
Data maturity is just the organization's readiness to actually use complex analysis. And the first practical step is to recommend hiring a consultant to perform a data maturity analysis for the department.
And this analysis is based on a specific framework.
Yeah, the study suggests using the Analytics Maturity Quotient framework. It's based on 5 key factors.
What are they?
They are: data quality, is your information reliable? Data-driven leadership, does management actually use data? People with analytic skills, can your staff interpret the outputs? A reliable data-driven decision-making process. And an agile infrastructure that can adapt to new tech.
And that analysis tells you where you are on the maturity scale.
It does. It tells you which analytical stage you're in. And it's important to say these stages aren't strictly sequential. You have to invest in all of them over time. There are 3 stages.
What's the first and most common stage?
That's the descriptive stage. This is where you use historical data to understand the past. You're looking at last quarter's utility bills, cross-referencing them with complaints, and visualizing where the issues were. Descriptive analysis tells you what happened.
The third floor was always hot on sunny Tuesdays in July.
Exactly. Then you move to the game changer, the predictive stage. Here, you use that historical data plus sophisticated AI models to predict future effects. You're running scenarios. If it's 95 degrees outside and we have 80% occupancy, Our chiller efficiency will drop by 15%. It tells you what might happen.
The chiller is likely to strain tomorrow afternoon.
Right. And the final and most advanced stage is the prescriptive stage. This synthesizes everything. It doesn't just predict the chiller strain. It automatically adjusts the air handling set points and pre-cools the building at 4 a.m. to prevent the strain from ever happening. It tells you what you should do, and often it just does it automatically.
Getting that initial maturity analysis from an expert seems crucial to even know where to begin.
It's the roadmap for your entire strategy.
Okay, but beyond hiring a consultant, are there lower-cost, introductory ways for staff to start engaging with AI and begin this journey?
Absolutely. A highly recommended low-cost strategy is to seek out and attend AI-focused conferences and seminars. It's about building internal champions for the technology.
What are the concrete benefits of sending a few people to a conference?
The benefits are huge for the investment. The sunk cost is low. They get a great evaluative return because they see what other similar facilities are doing. And it's fantastic for networking. It just demystifies the technology.
But the sources also pointed out some challenges with relying only on that approach, right?
They do. First, you need patience. Learning is slow. More importantly, just attending a seminar has limited impact if it's not followed up with internal technology training and a real commitment from leadership to actually implement the new knowledge. It has to feed into that larger strategic plan we just outlined.
That connects it all together perfectly. We've covered the problem, the solution, the technology, and the required managerial shift. This has been a true deep dive. #tag outro. So, to sum this all up, this deep dive has really confirmed the central transformative contribution of AI to facility management. It's about moving from operating by these static standard settings and constantly reacting to complaints
to having the capability, through things like biosensing and predictive modeling, to anticipate and proactively address concerns before they even become noticeable.
And the economic and human benefits really can't be overstated.
Not at all. By maintaining a comfortable, consistent, predictable indoor environment, you increase employee focus, you slash energy costs, and ultimately you increase both production and returns. The data strongly supports the idea that occupant satisfaction is employee satisfaction.
It's the smart, strategic way to operate a building in the 21st century and finally put a dent in that $15 billion problem.
Exactly. And while this review focused heavily on comfort and efficiency, the future research implications are equally critical for anyone thinking about implementation. As you, our listener, begin to mull this over, there are two major areas that need immediate investigation for organizations to feel secure moving forward.
Okay, so what's the provocative thought to leave us with? What should we be thinking about next?
First, cybersecurity. We talked to subject matter experts about the security vulnerabilities you create by collecting all this detailed building and occupant data. AI is a powerful tool, but it also creates a massive digital footprint.
So future research needs to focus on defense.
Yes. How can we leverage AI not just as a controller, but as a guardian? How can AI algorithms monitor and enhance protection against cyber threats, especially those targeting equipment performance or data leaks? We need to use AI to secure the very data it collects.
That's flipping the script-making AI part of the defensive strategy.
Precisely. And the second area is the cost basis. Given that no standard AI algorithm fits every organization, they all have to be customized and trained. We need future research to develop a detailed, standardized cost cases across the entire life cycle of these algorithms.
It's not just the purchase price.
Not at all. The life cycle includes development, testing, initial training, ongoing operation, refinement, and eventual disposal.
Yeah.
And crucially, it also has to account for the cost of training your staff to actually use and understand the output from the AI. Understand that full financial picture is the final piece of the puzzle for true sustainable adoption.
Welcome to the Deep Dive, the place where we take complex source material and turn it into actionable, memorable, and surprising knowledge. Today, we are peering into a world that is absolutely essential to modern life, yet remains almost entirely invisible. That is, until something goes catastrophically wrong. We're talking about facility management, or FM.
It's a perfect way to put it. It's the essential infrastructure that underpins everything. Every massive office tower, every sprawling factory, every high-tech hospital.
And definitely every major government building.
Oh, absolutely. Facility management is like the silent conductor ensuring the whole orchestra actually runs.
You're talking about the power, the temperature, the safety.
The very air you breathe. It's that fundamental.
Exactly. And today, we aren't just looking at, generalized industry trends. We are diving into some highly specialized source material, This is feedback from subject matter experts, SMEs, who were rigorously reviewing a DBA doctoral study.
Right, and a Doctor of Business Administration study has a very specific goal.
It does, and this one is focused on the exact intersection where FM meets the future: artificial intelligence. So our mission today is to extract the essential, high-level strategic insights on how AI adoption is actually going to disrupt how these massive multi-million square foot complexes are run.
And, maybe more importantly, what the real thorny bottlenecks are going to be for senior leadership, because that's what this is all about.
It is. Now, what's fascinating here, and what gives this source material, I think, incredible weight, is the pedigree of the researcher, Anthony Scaife.
Yeah. This is not some theoretical research completely divorced from practice. This is a practitioner scholar writing a roadmap for his own industry.
So who is he?
Okay, so he is currently the U.S. Intelligence Community Chief of Facilities for the Office of the Director for National Intelligence.
Wow.
Yeah. He's managing the IC's overall facility management program.
That's heavy. When you talk about the U.S. intelligence community, you're talking about facilities that demand not just operational excellence, but
absolute non-negotiable security and redundancy.
Right. He's dealing with some of the most complex, high-security, and mission-critical facilities on the entire planet. The stakes just couldn't be higher.
I mean, you said it perfectly. This is facility management, where a minor HVAC failure isn't just uncomfortable.
No, it's a national security issue.
Precisely.
Yeah.
And his background before this, he led the Defense Intelligence Agency's Global Facility Management Department, so providing facility services worldwide.
Okay.
And to top it all off, his foundational background is as a retired Air Force veteran, specifically a biomedical equipment technician. He supported U.S. hospitals all over the globe.
Okay, let's unpack that comprehensive background for a minute, because that's a really interesting combination. That lineage suggests a very unique worldview. You've got high security, globally dispersed operations.
Right.
Combined with the acute criticality of hospital support. So when someone with that kind of global, high-stakes operational experience decides to pursue a Doctor of Business Administration, they aren't looking for textbook answers.
No, not at all. They're looking for evidence-based, scalable solutions that can stand up to C-suite scrutiny and, mission-critical failure scenarios.
Which ties directly into the whole point of a DBA program, doesn't it?
It's the entire objective. The program aims to graduate scholar practitioners, people who can use evidence-based data from extensive literature to formulate.
To make decisions at the CEO or senior management level.
Exactly. They emphasize what are called systematic reviews, or SRs, of existing literature. It's a methodology they actually borrowed from the medical profession.
Why? To create a more objective, evidence-based approach to business practice.
That's the idea. So the goal isn't necessarily to go out and conduct brand new primary research in a lab somewhere. It's to synthesize massive amounts of existing data, quantitative, qualitative, all of it, objectively.
In order to do what? Formulate new policies, justify huge capital investments.
Drive innovation and strategic planning. Yeah. They are essentially building an unimpeachable case for action based on existing evidence and expert consensus.
So the researcher needs to be able to take all this complex information, synthesize these arguments, and use it to justify a multi-million or maybe even a multi-billion-dollar decision to their leadership.
That's right. And in this specific case, the ultimate decision is this. Should our massive multi-billion-dollar industry invest in AI for facility management? And if we do, how in the world do we justify the cost and manage the risk?
That's the question. And that brings us squarely to the scale of the financial argument, which brings us to the core financial argument. Why should every decision maker, even those outside of facility management, care about this deep dive?
Well, it really comes down to the sheer magnitude of the money involved. SME2, a gentleman named Mr. Mohammed, immediately grounds this whole conversation in financials.
What does he say?
He says, right up front, that the study addresses a crucial aspect of optimizing the $15 billion facility management industry in the United States alone.
$15 billion.
Yeah.
Dollars.
Yep. This isn't theoretical. This is a massive operational expenditure line item on balance sheets across the country.
That number, it shouldn't just grab the attention of a CFO. It should grab the attention of the entire capital markets. We're talking about huge annual amounts of capital tied up in operation, maintenance, energy.
And often the inefficient use of physical spaces, which is a huge hidden cost.
So even optimizing that $15 billion figure by a small percentage, say 5%, that translates into hundreds of millions of dollars in savings nationwide.
It's huge. And the cost savings are only one part of the problem statement. The core problem, as it's synthesized from the researchers' approach, is actually pretty clear. FM has to address these common operation and maintenance factors that tie organizational decisions directly to occupant comfort and well-being.
So it's not just about saving cash. It's about keeping the conditions optimal for human performance. Whether you're, I don't know, working on a trading floor or performing surgery in a hospital.
Exactly. Which brings us to the intervention they're testing. It's really strategic. The hypothesis is that infusing AI can help facility management improve operations and lower operating costs.
Okay, that's the money part.
While simultaneously maintaining positive occupancy, safety, and comfort.
So it's the trifecta. They're trying to achieve the impossible. Make the building cheaper to run, safer to inhabit, and happier for the people inside.
That's the holy grail. And this is where the originality of the study becomes really important. This isn't a topic that's been done to death.
That's new ground.
Very new. What's fascinating is the consensus among the SMEs about how novel this study is. Dr. Phipps, who is SME 1, notes that the study is highly original because AI is, and I'm quoting here, only now being considered for these key roles. It's the frontier application.
That timing is so crucial. We've had AI in software and cloud computing for years, but integrating it into the physical, gritty world of concrete, steel, HVAC pipes. That's a whole different challenge.
It's a completely different endeavor.
Yeah.
And Mr. Camp, SME 3, he confirms this market stage. He notes that while AI products are being produced for FM,
They're not being used yet.
they're just not being utilized by many, is how he puts it. Facility managers who are often, incredibly risk averse because failure is so expensive.
Right, a failure could be catastrophic.
Exactly. So they're waiting. They're waiting for that definitive evidence space to justify the immense investment they know they're going to need to make.
That makes perfect sense. Building infrastructure moves so slowly. You don't overhaul a multi-million-dollar chiller or a massive air handler every year just because a new software update came out.
The lifespan of this equipment is measured in decades.
So this study is trying to create that unimpeachable evidence base before the massive capital expenditures begin. It's providing the justification for building, or maybe more importantly, retrofitting smart facilities.
They're connecting 5 crucial strategic dots: facility operating costs, energy expenses, occupancy, safety, comfort, and then the integration of AI into the decision-making processes.
So if they can prove that AI provides a demonstrable return on investment in all 3 of those areas, financial savings, better safety metrics, measurable human comfort,
It justifies the immense capital and operational investment required to transition from traditional FM to intelligent FM.
which means we need to get very specific about the operational reality. We need to know exactly what this AI is doing inside one of these massive buildings.
Okay, so let's talk about the practical application. Dr. Phipps, SME 1, provided this really comprehensive roadmap of 8 specific areas where AI can enhance building performance. This isn't just theory anymore. This is the operational playbook for how facilities are going to be run a decade from now.
And this list is highly instructional. It breaks down the monolithic concept of AI into 8 concrete measurable functions within what's called a building management system, or BMS.
These aren't just vague concepts.
Not at all. These are distinct lines of code making real-time, financially relevant decisions.
Let's start with the low-hanging fruit, the one
Alright.
that immediately impacts that $15 billion figure, and arguably the first application most people think of. Application 1, energy efficiency.
Okay, so in this application, AI becomes the ultimate energy auditor. It is constantly analyzing historical data, how the building behaved last summer, how the occupants used power, and it combines that with what's happening right now.
Exactly. It combines it with real-time consumption patterns and external data, like weather forecasts or even dynamic utility prices. It then uses machine learning to predict future usage needs, basically hour by hour.
So what's the strategic gain here? I mean, we're all used to smart thermostats in our homes, but in a 500,000 square foot commercial building, what is AI doing that a traditional scheduler can't?
So the key impact is the hyper-optimization of the HVAC systems, heating, ventilation, and air conditioning.
That's the biggest energy hog.
It's typically the biggest, yeah. Often consuming 40 to 60% of a commercial building's total energy. AI moves you from static scheduling, like running the system the same way every Tuesday, to dynamic, proactive climate modeling.
So instead of just reacting.
Right. If a traditional system reacts by blasting cold air when the temperature crosses a certain threshold, the AI predicts that threshold crossing is going to happen.
Okay, give me an example. So instead of reacting to an interior temperature increase because the afternoon sun is hitting the west face of the building,
The AI knows. based on the sun's angle, the external temperature, and maybe even the predicted human occupancy increase in the cafeteria at noon. It knows the west side of the building is going to need cooling starting at 11:30 a.m.
Not at noon when it's already hot.
Precisely. It begins to modulate the system using minimal energy, maximizing efficiency, rather than waiting and having to blast energy later on.
That small shift, moving from reactive consumption to predictive preconditioning, that must drastically reduce peak energy demand charges, which I know are incredibly costly.
They're very costly. And it also promotes verifiable sustainability metrics, which are becoming more and more important for corporate reporting.
That proactive approach, it leads perfectly into the second function, application 2, predictive maintenance. This feels like it shifts the entire philosophy of FM, which for decades has been stuck in either reactive mode.
It broke. Fix it.
Or that kind of arbitrary, time-based preventative mode.
Replace it every 2 years, whether it needs it or not.
Yeah.
Exactly. Predictive maintenance is the major cost saver in the operational budget, no question. AI algorithms analyze a constant stream of high-fidelity data from specialized sensors.
And this is where we get specific, right? It's not just a simple temperature sensor.
No. We're talking about acoustic sensors that are literally listening for bearing degradation in a motor. Thermal imaging that's spotting hotspots on electrical components before they fail. Accelerometers that are measuring vibration levels on pumps and motors.
That's fascinating. So the AI is not just looking at a pump's operating hours, it's listening to its health. How does that translate into massive financial savings over time?
Well, the key impact is that it predicts when maintenance is needed. So instead of replacing a bearing on a massive chiller every 2 years based on some generic manufacturer guideline,
Right.
the AI knows, based on the acoustic signature and the operational load of this specific chiller in this specific building, that a microfracture is developing, and that component will probably fail in 3 months and 12 days.
Well,
So the FM team can schedule the replacement precisely when it's needed, during an off-peak hour, before the component fails catastrophically and shuts down the entire building.
that's brilliant. So it eliminates expensive, unplanned emergency downtime. It extends the equipment lifespan significantly, which ties into that longevity factor we'll talk about later. And it reduces the cost of labor by scheduling work efficiently.
All of the above. Now, moving on, the third application is crucial, especially when you consider the researcher's background. Application 3, security and surveillance.
So we're talking about AI-powered systems moving beyond just passively recording video.
Correct. This means the system uses advanced computer vision and machine learning models that have been trained on millions of data points to understand what is normal versus what is abnormal behavior.
So the key impact is real-time detection of potential threats.
That's it. The system isn't just recording video, it's actively analyzing crowd flow, it's identifying unauthorized access attempts, it's flagging what's called tailgating at secure entrances.
Where someone follows an authorized person through a door.
Exactly. Or it's spotting unusual activities, like a vehicle parked too close to a restricted zone for too long.
That must drastically reduce the cognitive load on human security personnel. They are no longer just staring at a wall of monitors hoping to spot an anomaly.
No, the AI flags the specific camera and the specific event that requires human intervention. It enhances safety and speeds up incident response far beyond what any purely human operation could ever achieve.
Okay, so then we shift gears a bit to maximizing the value of the real estate itself with application 4, occupancy management.
And this one hits the commercial property market hard, doesn't it?
It has to, especially now.
Absolutely. So AI analyzes occupancy patterns, often using sensor data, passive infrared data, or even aggregated, anonymized Wi-Fi device pings.
To understand precisely how and when space is being used.
Down to the individual desk or conference room. The key impact here is optimizing space utilization.
You hear stories all the time about companies paying millions in rent for entire floors that sit 50% empty. All because they haven't optimized their hybrid work schedule or they realize their meeting rooms are all the wrong size.
Precisely. If a company finds out through this granular AI data that, say, 40% of their floor plan is vacant 80% of the time, that data provides the evidence base to consolidate space, reduce the real estate footprint, sublease, or reconfigure layouts for massive cost savings.
It turns expensive square footage into efficient cubic footage.
That's a great way to put it. Then we move to application 5, smart lighting. This one seems simpler, but when you aggregate it across millions of square feet, it's a huge operational save.
It's got to be the easiest return on investment to prove.
It is. AI controls lighting based on a dynamic combination of occupancy sensors, the amount of natural light currently flooding through the windows, and the time of day.
So the strategic gain is dual purpose. You're saving energy by making sure unused areas are dimmed or off, which is a huge win.
And at the same time, you're creating a more comfortable and productive environment.
I assume that goes beyond just on and off, right? Does the AI modulate things like color temperature?
It absolutely does. The AI can adjust the intensity and the color temperature of the lighting to support human circadian rhythms.
So what, like using cooler, brighter light in the mid-morning for alertness?
Yes, and then gradually shifting to warmer, softer light in the late afternoon to support occupant well-being. It moves lighting from just being a utility to being a personalized productivity tool.
Okay, now, when you start putting all these specialized AIs together, the energy AI, the maintenance AI, the lighting AI, you get to application 6, building automation.
This is the integration layer, and it's where the synergy really happens. AI-driven systems integrate all these various components, lighting, HVAC, security, access control, so they work together seamlessly instead of just operating in their own isolated silos.
That means the system can think holistically, correct? So
Yeah.
for example, if the security system detects an intrusion, that's application 3. The automation AI could simultaneously turn on all the lights in that zone application 5 and maybe modulate the HVAC system to create localized air pressure changes.
Exactly, or just focus all resources on that zone. The result is a more cohesive and fundamentally a more efficient overall building management system. The interaction of these systems is often where the biggest operational gains are found.
How so?
Well, if Occupancy Management Application 4 shows an entire floor is empty, the automation AI can trigger a deep sleep mode across all the other systems on that floor. It can dim the lights, reduce the ventilation, raise the temperature set points, all simultaneously, maximizing efficiency across the board.
This kind of integration must require a serious amount of processing power and, more importantly, really high-quality data. Which brings us to application 7, data analytics. That becomes the engine room.
It's the brain behind the whole operation. The AI processes and analyzes the massive, often chaotic volumes of raw data generated by all the other systems. I mean, the sheer volume of data produced by a modern large-scale commercial building is far too complex for human analysis alone.
So it's not just summarizing reports, it's spotting patterns that are functionally invisible to human facility managers.
That's the key impact. It's providing sophisticated predictive insights. It's identifying subtle trends and generating performance metrics that truly inform the building manager's strategic decision-making.
Like what?
It might identify areas of chronic, subtle inefficiency, like a specific air handler that's consistently underperforming by just 2% across multiple metrics. That adds up to huge losses annually, but it's something human scanning dashboards might never spot.
So it turns data into evidence-based justification for capital upgrades.
Yes, it's not just running the building. It's providing the C-suite with the data and the justification to run the building better next quarter, next year, and across their entire portfolio.
And finally, that brings us to the most human-centric application, application 8, tenant experience.
And if you, the listener, work in a building, this is what you really care about. AI can personalize environmental conditions in ways that static systems just can't.
Give me an example of what true personalization looks like in a modern building.
Well, the key impact is moving beyond a single static temperature setting for an entire floor. AI can track and anticipate individual or group preferences. Imagine an executive who always prefers her office at 68 degrees, while the finance team next door prefers 72.
Right.
The AI, coupled with the occupancy and automation systems, can dynamically adjust localized temperature and airflow only to those specific zones. It moves the environment from a static, one-size-fits-all setting to a responsive, personalized, and adaptive one.
And that reduces occupant complaints, increases comfort, and theoretically boosts productivity, which is a crucial, though sometimes hard to measure, ROI.
It is.
That 8-point toolkit really makes the case clear. The DBA student is investigating how to integrate these capabilities to hit those high-level strategic goals. But before we get to the financial debate, we need to make sure the foundation of the research itself is sound.
Absolutely. Before we jump into the SME feedback on the practical value, we need to dedicate some time to Section 3. Structural soundness. For a DBA study that's intended to influence CEO-level decisions and justify massive financial outlays, the structure and scope have to be unimpeachable. They have to be highly credible.
So the SMEs were checking the fundamental integrity of the research design itself.
That's right. And the researcher, SCAFE, clearly understood the need for realistic limitations, which SME2, Mr. Mohammed, validated. You can't boil the ocean, right?
Right. So what was that critical definition of scope?
The overarching focus was the intervention of AI into facility management decision-making. That's broad. But crucially, the target facilities were narrowed down significantly to provide some research manageability. He focused on commercial buildings in the United States with 100,000 square feet facilities or larger.
That specificity is essential, and that's a strategic choice. Why 100,000 square feet or larger?
It creates a manageable universe where the costs are high enough to justify the intervention. You can't study every facility from a tiny retail shop to the massive complexes the researcher manages in his day job. By targeting 100,000 square feet and up, he is focusing on the segment of the market where facility operating costs are highest.
And where the potential for millions of dollars in optimization and impact is greatest.
Exactly. This focus provides the specific context needed for generalization, but only within that high-value segment of the industry.
That segmentation makes the financial argument immediately more credible. Now, let's talk about the conceptual coherence. The researchers used the SIMO framework. That's context, intervention, mechanism, outcome. This is specific business administration methodology.
And SIMO is paramount in management research because it forces precision. Mr. Mohammed highlighted that the SIMO framework specifically enhances the coherence and validates the intricate connections between the key factors, cost, comfort, and the AI intervention.
Because in high-stakes management research, you can't just rely on correlation. You have to map out causation.
You have to.
I understand context, large commercial buildings, and intervention AI decision support. But how does SIMO force the definition of mechanism and outcome in a way that satisfies a senior leader?
It provides the internal logic you need to support a complex capital expenditure argument. You have to define. In what context are we operating? What is the specific intervention we're deploying? What is the mechanism, so the specific way the intervention works? For example, predictive maintenance using acoustic sensors or energy optimization via load forecasting.
And finally, what is the measurable outcome?
Right. What's the measurable outcome? A 15% lower operating cost, a 10% reduction in downtime, a 20% improvement in occupant comfort scores. The framework validates that every single step is linked.
So if the DBA student is successful, the study not only says AI works, but it details the exact path of how AI works, which is exactly what a CEO needs to know before they sign a budget request.
And the SME feedback confirmed the study successfully achieved this. It articulated the correlations among facility operating costs, energy expenses, occupancy safety, comfort, and the integration of AI.
Okay, what about the literature review?
There was a consensus that the materials reviewed, covering facility energy, operating cost, facility management, and AI, provide sufficient direction. SME2 noted the literature review sets an excellent baseline for an in-depth investigation and is relevant because it incorporates recent AI studies, which is critical in such a rapidly moving field.
But there's a tension here, isn't there? I think Dr. Fix pointed out one challenge. He had trouble finding sufficient literature specific enough to AI and building management systems to complete the systematic review.
That's the classic challenge of studying a nascent field. It's a catch-22. The study is original because the applications are new and data is sparse, but that very newness means the rich evidence base you need for a systematic review is still pretty thin.
So it forces the researcher to synthesize from disparate sources, which requires a lot of skill.
It does. But overall, the structural feedback was overwhelmingly positive. It reinforced that the approach was logical, well-defined, and consistent with the high standards of complex management research.
Okay, the structure is sound, the problem is defined, and the financial stakes are massive. Let's move to the synthesis. What did the experts think was the most valuable, and what are the major implementation barriers? Now we move to the expert synthesis. This is where we compare the rapid-fire insights from all three SMEs to get a balanced view of the study's strengths and the serious roadblocks ahead. Let's start with the overall practical value and strengths. Why is this study going to be immediately useful?
The primary strength, and we keep coming back to this, is scalability. It's tied back to that huge financial number. SME2 highlights the study's high potential for a scalable solution impacting the $15 billion industry.
The problem definition and the solution set are massive.
They are, which means the results, if they're positive, will be highly valuable to any major property management group, corporate real estate holder, or government entity.
So it's a study written for the people who control the capital.
Exactly. And there's a real-world leadership argument here, which was identified by SME3, Mr. Camp. He notes that the study is highly applicable to the real world because it helps facility management specialists to, and I'm quoting, better depict the effort of implementing AI to their leaders.
That's a critical translation point. The FM team understands the technical need for a new sensor network, but the CEO only understands financial benefits and risk.
Right, and FM specialists often struggle to translate complex technical requirements in data science into a budget line item and a strategic benefit for the CEO.
So this study provides the evidence-based argument they need for that pitch. It's complete with a robust SIMO framework backing it all up.
And Dr. Phipps rounded out the strengths by noting that the results can serve as a strong foundation for further research, specifically regarding AI's contribution to occupant comfort and energy savings. It's building the scaffold for the next generation of building design and operation.
And let's double back to a concept we briefly touched on during our predictive maintenance discussion, the longevity factor. This is a massive hidden financial benefit.
It truly is, and SME3 introduced this directly, underscoring its importance. You have to think, traditional capital expenditures for massive equipment like chillers, boilers, or air handling units. They're based on depreciation schedules of maybe 15 to 20 years.
Right.
AI should be able to increase the life cycle of that equipment significantly.
How exactly does that happen?
By maintaining proper and efficient cycles and using that granular predictive maintenance we talked about. If you run a piece of equipment optimally, you never let it overheat, you never let vibration go unchecked, you ensure components are replaced just before failure, you dramatically reduce the strain and wear.
So instead of a 20-year lifespan,
AI might conservatively stretch that to 25 or even 30 years. That's reducing the capital replacement cost for the organization by 20–30%, which is immense when you're dealing with multi-million-dollar machinery. This extends the financial ROI years into the future and completely transforms capital planning.
Okay, so the study is strong, the context is clear, and the potential reward is huge, shaving billions off operational costs and extending capital cycles. But where are the pitfalls? This is where the deep dive needs to get critical. Let's discuss the key weaknesses and challenges.
We have three major hurdles identified by the SMEs, and they hit different facets of the research: scope, data, and risk.
Let's start with the scope risk. This was raised by SME1, Dr. Phipps. He warned the study might be too broad, suggesting that limiting the context to a specific type of building would be better.
Right, like hotels or factories or office buildings or airports, to improve generalizability within that specific vertical.
That's the classic academic challenge, isn't it? Achieving specificity versus generalizability.
It is. If you study every type of large commercial building, from a data center to a high-rise office, your recommendations might be too generalized to implement anywhere optimally. A factory floor has wildly different occupancy patterns and temperature requirements than an airport terminal.
And the cost-benefit analysis for implementing AI might look completely different for a hospital, where safety and air quality are paramount regardless of cost.
Versus a standard office building where cost optimization is the primary driver.
Right.
So the recommendation is to specialize the context to strengthen the depth of the findings. It's a common refinement for a DBA project. However, the next weakness is perhaps the most fundamental operational constraint facing the entire industry right now: data limitations. This was pointed out by SME3.
And this is where the theory hits the concrete reality of existing infrastructure.
Mr. Camp highlighted a major hurdle: the limited number of sensors in place in existing buildings for AI to make fully informed decisions. This is the cold reality of retrofitting. We can talk about sophisticated AI and machine learning models all we want, but AI runs on data.
And if there's no data?
If the existing commercial building infrastructure wasn't built with thousands of networked acoustic, thermal, and occupancy sensors, the AI is effectively blind, or at least it's operating with only 10% of the necessary inputs.
That is the single most restrictive constraint on AI adoption in FM. It's like having a brilliant AI engine that requires jet fuel, but your building is only plumbed for molasses.
Precisely. This lack of real-world, high-fidelity implementation data creates inevitable study limitations. And more importantly, it creates an enormous, costly barrier to entry for building owners.
So the study can prove that AI could work.
But the foundational infrastructure, the ubiquitous, high-density sensor network, it just isn't there in most existing facilities. The transition involves not just installing software, but ripping out old systems and installing new networked sensors everywhere, which is a prohibitively expensive and time-consuming capital project.
So, if the study's conclusions are largely driven by what's possible with perfect data, but 90% of the $15 billion market can't currently provide that data, is the study truly relevant for the next 5 years? Or is it purely theoretical for new construction? That's the critical friction point.
That is the essential question the researcher has to address in the implementation phase. The ROI for the AI is clear, but the ROI for the sensor retrofit is far less clear and much harder to justify to a landlord or property manager.
And then we get to the highest level risk, identified by SME2, Mr. Mohammed, and this is particularly relevant given the researcher's career in high-security environments, the cybersecurity blind spot.
Yes, he noted the conspicuous lack of focus on the impact of cybersecurity of the systems required to retrieve the necessary sensor data to build the AI database. This flips the entire conversation from optimization to existential risk.
Let's delve into this. If we network every sensor, every HVAC unit, every fire suppression system, and every access control mechanism across a massive building, and then we funnel all that vital operational data into a central AI brain, what exactly have we created?
We've created an enormous, centralized, and highly attractive target. The strategic gain in efficiency is directly proportional to the increased cybersecurity vulnerability. A cyber attack on a smart building is not just a data breach, it's potential physical control over the infrastructure.
You're talking about a malicious actor potentially controlling HVAC systems to cause overheating, disabling security protocols.
Manipulating fire suppression systems or even using the building automation system to cause widespread, highly localized power failures.
And critically, we have to remember the researcher's background. In the intelligence community, you don't optimize energy only to expose critical national assets to a network intrusion.
Of course not. The operational network that handles all this sensor data, it's often referred to as the operational technology or OT network. It has to be secured to the same standard as the information technology, the IT network, if not higher. Mr. Mohammed clearly understands that the system required to retrieve the sensor data must be secured before the AI can be trusted to run mission-critical facilities.
The optimization gain is worthless if the risk is existential. This critical feedback suggests the study has to immediately pivot to incorporate robust cybersecurity measures and risk mitigation into its strategic recommendations. You can't talk about a $15 billion industry revolution without addressing the inevitable cyber war that will be fought on its digital infrastructure.
The implication is clear. The facility management industry needs to stop treating cyber risk as an IT problem and start treating it as an FM or physical security problem.
Yeah.
The AI is only as safe as the network layer it sits on.
That sets a very serious tone for the future. But the SME feedback didn't just stop at identifying weaknesses. It provided a clear roadmap for the next investigation steps. It identified the key players who will solve these problems. The SMEs essentially provided the researcher with the next strategic objective. SME2, Mr. Mohammed, suggested the crucial next step. He said to investigate the global industry leaders in building automation, the companies he calls the smarts and the integrator of facilities. Why? Because they are the database backbone required for AI capability.
This is a really profound insight. If this technological revolution is going to happen, it won't be driven by independent facility managers or even the building owners themselves. It will be driven by the few massive industrial technology companies that control the underlying operating systems and protocols for these buildings.
He explicitly listed the companies likely to make the major shift, and these are the names you need to know: Siemens, Honeywell, Tritium, Johnson Controls, Schneider Electric, and KMC.
These are the heavyweights. They're the ones that design, install, and manage the complex systems that read the sensors, aggregate the data, manage the proprietary communication protocols, and provide the data lake necessary for the AI to train and operate.
So if the DBA study proves the need for AI,
the implementation hinges on these few global tech leaders integrating that AI capability seamlessly and securely into their established automation platforms.
That reveals a significant level of centralization in the smart building future. If you want smart buildings, you pretty much have to buy into the ecosystem of one of these global giants. That has serious implications for vendor lock-in and long-term costs.
Yeah, it absolutely does. And to clarify the immense practicality of AI decision-making, Mr. Mohammed provided an excellent, highly specific example. He called it the air filter example. It perfectly illustrates the shift from reactive to intelligent FM.
Okay, let's break down the traditional method versus the AI method for something as mundane yet vital as changing an air filter.
So in traditional facility management, air filters are changed on a scheduled maintenance cycle, say every 3 months or every 1,000 operational hours, regardless of actual usage, air quality, or building density. It's a time-based, often wasteful method.
It's maintenance by calendar, not by condition.
Exactly. With AI, that all changes. The AI uses multiple data inputs: the pressure differential across the filter, which indicates how clogged it is, real-time air quality sensors in the occupied space, and the occupancy rates, so how many people were actually using the building. Instead of a fixed schedule, the AI suggests decision-making on the filter change frequency based on actual need.
Give me a scenario where the AI saves money.
Easy. If a commercial building is only half occupied because of hybrid work schedules and the air quality sensors remain high, the AI might rationally extend the filter's operational life cycle to 4 or 5 months. That saves significant materials and labor costs over a year across an entire portfolio of buildings.
And a scenario where the AI saves the building from a costly failure or a complaint.
If there's heavy construction happening nearby, causing particulate matter sensors to spike, or if a major event causes unexpected peak occupancy, the AI might detect that the filter's pressure differential is accelerating faster than predicted. It will then trigger an early filter change, proactively maintaining occupant comfort and critically protecting the multi-million-dollar HVAC equipment downstream from undue strain or contamination.
That's the perfect illustration. It's shifting from time-based maintenance to condition-based, intelligent maintenance. It's smarter, cheaper, and better for the occupants. This entire synthesis confirms that the researcher is on the right track, providing the foundational argument needed, but must immediately factor in that existing sensor gap, the difficulty of getting the data, and the looming cybersecurity risk, the existential threat of networking that data as they move forward. So, if we summarize the journey we just took, we started with the massive financial potential. We're talking about optimizing the $15 billion U.S. facility management industry and aiming for that trifecta of cheaper, safer, and happier buildings.
And we broke down the operational reality into that 8-point AI toolkit, covering everything from predictive maintenance, which can extend the lifespan of capital equipment by years,
to enhancing occupant experience through personalized climate control.
We confirmed the study's structural soundness, how it focuses on large commercial U.S. buildings and uses that robust SIMO framework. That ensures the results are structured to influence senior management decisions by clearly linking cause, mechanism, and measurable outcome.
But the experts also gave clear, unavoidable warnings. The implementation is fraught with 2 major constraints. First, the scope needs careful management to remain useful, and second, real-world AI is currently constrained by the limited number of sensors in existing buildings, which makes the transition costly and complex.
And critically, the future success of this optimization hinges entirely on solving the cybersecurity risks posed by connecting these vital physical systems to an AI database, a threat that goes beyond data breach and enters the realm of physical sabotage.
And finally, we established that the power structure of the future of smart buildings is concentrated among just a few key global players: Siemens, Honeywell, Johnson Controls, the ones who provide the necessary technological database backbone for this revolution to even occur.
So what does this all mean for you, the listener, who is either a decision maker or just someone profoundly curious about the next wave of industrial technology? We've seen that the next level of efficiency and cost savings in our physical built world hinges entirely on the volume and quality of sensor data.
And that data, along with the integration capabilities necessary to process it into actionable decisions, seems to be centralized. It's under the control of just a few global technology leaders, the companies that manufacture the building management systems.
This raises an important final question for you to consider as these technologies mature and become standard. Is the ultimate optimization, safety, and comfort of our most critical infrastructure, hospitals, massive data centers, government facilities, corporate headquarters, become dependent on AI running on proprietary software platforms provided by a handful of global corporations? What does that concentration of operational control mean for the future resilience and competitive security of the $15 billion facility management industry?
When the efficiency of the physical world becomes entirely digital, the battleground shifts completely to the cyber domain. The greatest risk to a modern building may soon not be a pipe burst or a fire, but a network intrusion engineered thousands of miles away. That's a deep dive for another day. Thank you for joining us.
Always a pleasure. Welcome back to the Deep Dive. Today we're tackling a challenge that I think we all face. You know, being too hot, being too cold.
And wasting a ton of energy in the process.
A massive amount of energy, yeah. We received this really fascinating stack of research that's focused entirely on how artificial intelligence and machine learning are, well, they're not just tweaking the thermostat.
No, not at all.
They're fundamentally transforming how we manage facilities, especially the heating, ventilation, and air conditioning, the HVAC systems, in these big commercial buildings.
This is a really deep look into the practical side of this. I mean, we are seeing a fundamental shift here.
A shift from what to what?
From these, static schedule-based controls, the kind that just turn on at 9 and off at 5.
Right, the old school timers.
Exactly. To these incredibly dynamic, highly personalized systems. For decades, building management was, you could say, all about brute force engineering. Now it's completely about prediction and intelligent adaptation.
Absolutely. And I think the core mission of this deep dive, and really the focus of all the research we looked at, is trying to see how science can balance two goals that seem to conflict.
They really do.
On one side, you've got this relentless pressure for maximum energy efficiency, saving money.
Of course.
And on the other, you need to provide superior, personalized comfort. And this is a big one now, vital indoor air quality, or IAQ.
And historically, you had to trade one for the other. Facility managers were always making that compromise.
But the promise of AI is that maybe that compromise is becoming obsolete.
That's the goal. And we're going to unpack the methods that are being used right now. I mean, we'll look at everything from using these huge language models like ChatGPT to manage skyscraper simulation.
All the way to using ultrasonic sensors to literally, identify people based on how big they are.
Right. So our goal is to find out what really works, where the huge cost savings are, and maybe why the human element, the simple fact that my comfortable is you too cold, is still the trickiest variable for any algorithm to get right.
And this data, it's largely from recent pretty rigorous studies in the U.S. They're all focused on how AI improved these high-stakes decisions around energy, occupancy, and comfort.
And I think what's important for you listening is the confidence level here. The evidence base is already reaching what's called a moderate assessment.
Which means we're not talking about some sci-fi pipe dream.
Exactly. We're talking about established techniques that are being tested and proven right now.
Okay, so let's get into it. Let's unpack this, maybe starting with the money and the physics.
Sounds good.
If you're running a commercial building, you're used to HVAC control being, a fixed schedule.
Right.
Glorified timer.
Right.
But we are so far past that now. This first part is all about that move from the basic rule-based stuff like if it's 75 degrees, turn on the AC.
To deep learning models that are all about maximizing cost savings through prediction and proactive optimization.
What's the big change there? Why is being proactive so much better?
Well, the change is that deep learning lets the system stop being reactive and start being, truly proactive.
Like a chess master.
That's a great way to put it. It doesn't just react to the temperature right now. It predicts the future thermal load.
So it's looking ahead at the weather forecast, how many people it expects.
Exactly. Historical patterns, all of it. And then it strategizes. It might pre-cool the building an hour before a heat wave hits.
So it avoids those huge, expensive spikes in energy when everyone arrives and the computers turn on?
Precisely. It smooths out the demand and prevents that temperature overshoot.
So let's start with what might be the most remarkable study in our stack, just because of the scale of it.
Yeah, this one was fascinating.
They applied a generalist AI model, something like ChatGPT, and they coupled it with a specialized deep Q network, a DQN, to run a simulation.
And this wasn't some small office.
No, this was a massive 12-story office complex. We're talking 46,320 square meters.
What's so interesting is the comparison they set up. They basically had a bake-off.
Between the generalist AI and the specialist.
Right. The large language model versus the purpose-built deep learning model, the DQN. And the mission for both was huge.
Minimize total energy use for the whole building.
The whole building, air handling units, chillers, the cooling tower, pumps, everything. But they had one very important constraint.
Which was the air quality.
Exactly. A critical indoor air quality requirement.
And what was that requirement specifically?
The CO2 concentrations inside had to stay below 1,000 parts per million.
Which is so important. It means the system can't just cheat by turning off the fresh air vents to save a buck.
It has to balance health and efficiency. It's a real-world test.
So the results, how did they do compared to just, the normal way of running the building?
They were phenomenal. The ChatGPT integration, just using a language model for control, it managed to lower the total energy use by 16.8%.
16.8%. That is a massive annual saving for a building that size.
It's huge. But the custom-built, specialized AI, the Deep Q network, did even better.
How much better?
The DQN lowered the energy use by a staggering 24.1%.
Wow. A quarter.
Yeah.
A quarter of the building's entire energy consumption just vanished, just through smarter control.
Yeah.
That's staggering.
It is, and it tells us something really critical right away.
What's that?
That while these big general language models like ChatGPT can be surprisingly good out of the box, because they can parse complex rules, a specialized reinforcement learning model that's built just to understand the physics of an HVAC system is going to win in the long run. It achieves superior optimization.
And they both kept the CO2 levels safe.
Both of them, which proves that you don't have to sacrifice healthy air to get these huge energy savings.
That's 24% saving from the DQN. I mean, that's a potential billion-dollar game changer for commercial real estate.
It is. But the financial part goes even deeper than just cutting kilowatt hours. It's also about when you use the power.
Which brings us to the money side of things.
Right. The strategic financial angle. We looked at another study, this one by Jiang and others in 2021, and they focused their DeepQ network not just on energy, but specifically on cost reduction.
So they were looking at things like time of use pricing from the utility companies.
Exactly. Time of use pricing and those really painful demand charges.
Okay, for anyone listening who isn't a facility manager, can you just quickly explain what a demand charge is? Why is it so bad?
Sure. A demand charge is basically a penalty from the utility. They look at your highest single spike of power demand during the month.
Usually in like a 15-minute window, right?
That's right. So if all your big chillers kick on at once in the middle of a hot afternoon, that one spike can set a high rate for your entire month's bill.
Even if your total energy use for the rest of the month is low.
Even then. And AI is brilliant at shaving down those peaks.
So how did this customized DQN do against those variable costs?
It did much, much better than the old rule-based system. When you included the demand charges in the math, the DQN saved close to 6% of the total energy cost.
6%, okay.
And if you took the demand charges out and just focused on the shifting price of energy during the day, it saved closer to 8% of the total cost.
That's a really key distinction. It means whether the utility is penalizing you for spikes or just charging more at 3 p.m., the AI can handle it.
Precisely. It shows how powerful AI is at minimizing those costs. It can strategically shift the load, maybe pre-cooling the building a bit before the prices jump, to make sure it's using the least amount of power when that power is most expensive.
So the building becomes like an active player on the energy grid.
An intelligent participant, exactly.
Okay, but when you're talking about letting an AI manage millions of dollars of equipment, you have to talk about reliability.
Paramount. Absolutely.
This isn't just saving money. You need stable operation. What happens if the AI learns some weird pattern that doesn't actually follow the laws of thermodynamics?
And that is the Achilles heel of a purely data-driven model.
How so?
The problem with a model that only learns from past data is that it can, what's called overfit to that data. It gets brittle.
So it works great until something new happens, like a crazy heat wave it's never seen before.
Exactly. Or worse, it could try to make a decision that's physically impossible because it's outside of its training data. For trust and stability, you have to ground these AIs in physical reality.
And this is where we saw this other model come in, the physically consistent deep learning, or PCDL model.
Right.
How is that different from a standard deep learning model?
So think of it this way. A standard model learns by looking at thousands of examples of what happened. The PCDL model is different. It has the fundamental equations of heat transfer and mass balance.
The laws of physics.
The laws of physics, yeah. They're built right into its training. It makes sure that the AI's model of the building always sticks to physical reality, not just under the conditions it was trained on, but under all conditions.
That must give facility managers a huge amount of confidence.
It's a game changer for trust. And they tested this PCDL model in a real building, Carpenter Hall at Cornell University. It's a 2-floor office and teaching building.
And they put this physics-based model inside another system, right?
Yeah.
A model predictive control framework.
Yes, MPC. And the MPC is basically the brain that uses the prediction.
So it's the part that's always looking ahead.
Right. It's constantly looking, say, 24 hours into the future, and it's solving this really complex optimization problem. It balances the predictions, like weather, with the physical constraints from the PCDL model to find the absolute best set points for all the equipment.
It's the ultimate proactive strategy.
It is.
And grounding it in physics, that paid off. Not just in efficiency, but in, how it felt to be inside.
Precisely. They tested the PCDL system against 3 other controllers, a simple on-off, a state space model, and even another type of deep learning model that didn't have the physics baked in.
Yeah.
The PCDL model cut energy consumption by a solid range, between 4.5 and 8.9%.
Okay, that's a respectable saving, especially for a system built for reliability. But the comfort number, that's where it gets wild.
This is the real story here. Because the model was so stable and grounded in thermodynamics, it also improved indoor thermal comfort by a phenomenal amount, between 55 and 64%.
55 to 64% better comfort.
Yeah. And that just underscores this profound point. Efficiency and comfort are not enemies. They're actually intertwined when you build stable, reliable models. The AI doesn't have to constantly overcorrect and swing back and forth, which wastes energy and frustrates people.
The core of all these savings, whether it's 24% or 8%, seems to be the speed and accuracy of the prediction.
It is. Being able to forecast what you'll need in an hour or even a minute is what lets the system avoid that frantic, energy-guzzling ramp-up of the equipment.
And that takes special kinds of neural networks. We saw one study that used the transformer neural network model.
Right. And many people will have heard of transformer because it's the architecture behind things like GP2. But here, they applied it just to forecasting HVAC loads.
How good was that predictive power at actually saving energy?
The results were, frankly, staggering. This transformer model cut energy consumption by almost 50% compared to the conventional non-AI methods.
50%? Half.
Almost half. And that huge saving was most obvious at the really short-term forecasts, like 1 minute and 60 minutes out.
Wow. A 50% reduction is it's a testament to real-time prediction.
Absolutely. When you can accurately predict what you'll need 1 minute from now, your system is in a truly dynamic loop. It's responding to a cloud passing over the sun or a slight shift in the wind. That level of granular control is something a schedule-based system could never, ever do.
We also saw this being applied in places that are already supposed to be perfect, like the HR peeling in Texas.
A great example. This is a LEED Platinum facility. I mean, it's the poster child for efficiency. It has a perfect Energy Star rating of 100.
And even there, they found savings.
Even there, they used these convolution recurrent neural networks to analyze the data and found there was still room to improve. A potential for up to 8% in energy savings just by optimizing how the HVAC operated in different time slots.
If you can save 8% in a perfect building.
Imagine what you can do in an average commercial building from the 1980s.
Right.
It just shows you how much waste is hiding everywhere. And beyond just controlling the machines, these models are also helping with high-level financial strategy. They found that generalized additive models, or GAMs, were really effective at giving managers the confidence they needed to, say, shift electricity demand during peak periods.
Which connects right back to those demand response programs we talked about.
Exactly.
Where the utility actually pays you to use less power during a heat wave.
Right. And these GAMs give the facility manager the reliable prediction they need to participate confidently. They know they can shift some non-essential loads to off-peak hours without disrupting operations, and that means they can minimize those peak charges and maximize the financial incentives. The AI is literally becoming the building's financial advisor.
Okay, so section 1, it really proves that AI is brilliant at the physics, the thermodynamics, the complex financial math of energy.
It really is.
But the ultimate challenge is that the mechanical system, the chiller, it doesn't care if you're comfortable. Only the people inside do.
Right.
So now we have to tackle the messy, subjective part, the humans.
This is the crucial leap. I mean, if you just treat the building like an empty box, you're back to static control. To get both efficiency and personalized comfort, the AI needs incredibly accurate, real-time data. Not just about the weather, but about who's in the building, where they are, and critically, how they feel.
That data is what drives things like demand-controlled ventilation.
Exactly. And personalized heating and cooling, the human element is the ultimate wild card.
And the old way of sensing people, a simple motion detector, that's not going to cut it for this.
Not at all. You need granular data. Head counts, location, sometimes even identity.
Which is why we're seeing this push into computer vision. One study used a deep learning algorithm called YOLO.
You only look once.
Right. To detect people in an office with super high precision. And you use that to control something called stratum ventilation.
Which is basically just highly targeted air. It supplies the conditioned air directly to the people instead of wasting energy conditioning the entire empty room.
Vision systems are accurate, but they bring up immediate privacy questions, especially in an office.
They do.
So what are some of the less intrusive methods that are also working well?
We found this one study by Khalil and others from 2018 that was just fascinating. They proposed a non-visual system using ultrasonic sensors to identify people.
So using sound waves.
Yeah. The goal wasn't to recognize your face, but to identify you based on subtle physical features, your height, and, interestingly, your width.
That's almost like biometric profiling with sound. How well did that actually work, just using height and width?
In a lab setting designed to mimic a commercial building, they had 20 different occupants, and the system achieved a 95% accuracy rate in telling them apart.
95%. Just from sound.
Yeah. It suggests that even these simple physical dimensions, when you measure them precisely with AI, they're unique enough for reliable identification in an office.
Okay, but here's the detail that was so surprising, the one that sort of goes against your intuition.
I know which one you mean.
The study found that using the measurement of a person's girth, their width, was actually more successful at telling people apart than using their height.
It's a really powerful, unexpected result.
Girth was better than height. Why would that be?
Well, if you think about it, height is pretty stable, right? Especially for adults. But girth, or width, as the sensor measures it, that captures so much more.
Like your posture, or if you're carrying a bag.
Exactly. Or even just small changes in how you move. The AI found a feature girth that a human would totally overlook, but it turned out to be a richer, more unique identifier. It fundamentally changes what sensory data we think is valuable.
So if direct identification is too complex or intrusive, what about using indirect data? Can you reliably tell if someone's there without even looking at them?
This is often the way to go for facility managers. Researchers developed these occupancy estimation frameworks that used a whole suite of indirect data.
Like what?
Things like indoor temperature, light levels, CO2 density from people breathing, and the overall electricity use in a specific zone.
And they found that using just that environmental data, they could get, what, like 95% accuracy?
Around 95% accuracy in estimating occupancy.
Wait. That's just as good as the direct methods like the vision systems or the ultrasonic sensors.
It is. It's a profound finding. It means if the AI sees the lights are on, CO2 is rising, and the temperature is going up from body heat in one area, it can infer with near certainty that someone is there.
And you don't need a camera. You don't need a complex sensor.
Exactly. And it completely gets around problems like occlusion.
Where one person is standing in front of another and the camera can't see them.
Right. The indirect data just averages all that out.
Okay, so when an HVAC system is trying to keep a room cool, it's fighting against heat that's being generated inside the building.
Right. Internal heat gain, or IHG.
And that comes from people, lights, and all the electronics, computers, monitors, what they call miscellaneous electric loads, or MLs.
And accurately predicting that IHG is one of the most vital inputs for an efficient system, if the AI knows a heat spike is coming, it can prepare.
One study set out to figure out which of those internal factors was the best predictor of IHG.
Yeah, from Z-Wang and others.
And intuitively, you'd think it's the number of people, right? More people, more body heat.
That is the common assumption. But here's another one of those big counterintuitive findings from the research.
What did they find?
For predicting the total internal heat gain, the MLL load, the energy from the equipment, is actually a more important feature than the number of occupants.
That is genuinely surprising. It changes how you'd model a modern office. Why would the computers matter more than the people?
They gave two core reasons. First, in a modern tech-heavy office, the MLL load is just the biggest component. It pumps out more watts of heat than human bodies do.
Okay, that makes sense.
And second, and this is the really strategic part, the MLL data actually helps you predict the occupant count.
Because if a computer's running, someone's probably nearby.
Exactly. But the reverse isn't true. Knowing someone is there doesn't help you predict if they've turned on their high-powered workstation or not.
So monitoring the power draw from the outlets is a better proxy for the whole thermal environment than just counting heads.
That's it. It suggests that you get more bang for your buck, sensor-wise, by focusing on high correlation variables like ML load. It's a fundamental shift in where you'd focus your monitoring efforts.
Okay, this brings us to the ultimate battleground, thermal preference.
Right.
We've established comfort is totally subjective. What's perfect for me at my desk is freezing for the person right next to me.
And the standard models used in facility management, they fail because they just average everyone out. To get past that, the research is now focused on creating what they call personal comfort models, or PCMs.
And how personal can these really get? What kind of data are they using?
They're using biometric data, We saw research that looked at building these PCMs based on individual physiological signals.
Like from a wearable, a smart band.
Exactly. Specifically using the galvanic skin response, which is basically the electrical conductivity of your skin. It changes when you sweat or feel stress.
So it's monitoring your body's actual physical response to the temperature in real time.
That's right. And they found that while the general comfort model was useless for predicting how these people felt, the private models built from their own biometric data were extremely promising.
So comfort is so personal. You really need a model built just for you.
That was the clear conclusion. You need a personalized model based on unique biological data to get it right.
We also saw PCMs that used machine learning combined with observable human behavior.
Yes. Another study confirmed that PCMs based on how people act like when they adjust their personal comfort system chair.
So like turning on the seat heater or changing the little fan in the chair.
Exactly. That behavior gives a more accurate picture of what that person actually wants. Your office chair becomes this advanced personalized sensor. The AI learns, okay, when this person turns on their seat warmer, it means they're feeling about 2 degrees colder than the room air. I need to warm them up preemptively.
That's powerful for one person. But what about solving the group problem? The classic office thermostat war.
That's where you see some really clever innovation. One framework focused on guiding people to the right space in the building.
What do you mean?
It leverages the natural variations that already exist. You know, the area near the big sunny window is always going to be warmer than the interior core of the building.
So instead of trying to force the whole building to one unsatisfying temperature,
you let people find the microclimate that naturally works for them.
how did it work in practice?
People reported their preferences on an app. The AI fused that with real-time environmental data from all over the building, and then it would make a recommendation. Hey, try working in Zone D for a while. It's optimal for you right now.
And did it make a difference?
A remarkable one. This system increased people's self-reported thermal comfort by at least 18.8% compared to when they just picked a room at random.
18.8% better comfort, just from intelligent navigation.
Yeah. A huge improvement in well-being just from using data better.
Okay, so we've seen AI get really good at predicting thermal load, and we've seen it identify people and even learn their personal comfort needs.
Right.
Now let's look at the sophisticated control systems that take all that information and turn it into action, especially when you have to manage these really complex trade-offs.
Like maximizing comfort for a whole group versus minimizing the energy bill, or balancing health risks against cost.
This is where we get into reinforcement learning, or RL.
This is the domain of RL, yes. RL is a technique where the AI agent, it learns the best actions, like how high to set the fan speed through trial and error.
It gets a reward for doing something good, like saving energy, and a penalty for something bad.
Exactly. And it's perfect for a complex problem like HVAC because it can discover solutions that a human would never think of.
So how does RL handle that conflict of comfort in a room with 3 different people who all want different things?
That conflict is exactly what these systems are built to manage. We saw this great example of a multi-agent RL control system that used biosensing.
That physiological data we talked about.
Right, to optimize individual comfort within a group. You had multiple AIs, one for each person, all talking to a central negotiator AI.
And its job was to make the group as happy as possible first, and then worry about the energy second.
That was the goal, and the human results were incredible.
They were.
By dynamically navigating all those individual preferences, the system improved the group's thermal satisfaction by a massive 59% compared to the old static set point control.
59%. That just shows how much better RL is at managing these complex group dynamics than a simple schedule.
It does, but there was a really critical outcome related to the energy use.
And this is a huge consideration for anyone thinking about adopting this stuff. What was the trade-off?
It's a perfect example of the training problem. Initially, the system completely failed to reduce energy consumption. At all, because the researchers had programmed the reward to prioritize one thing above all else: maximizing thermal satisfaction. Energy saving was a distant second.
So the AI did exactly what it was told. It learned that making people that much happier was worth the energy cost.
Precisely. It was a ruthlessly logical optimizer. And it just highlights how carefully you have to calibrate and weight that reward function when you set these systems up in the real world. You have to tell the AI exactly what a comfortable person is worth in dollars versus what a kilowatt hour costs.
That challenge also brings up the issue of generalizability, right?
Mm-hmm.
If you train a system perfectly for one building, how well does it work in a different one?
That's a big problem. The research shows that these purely data-driven models often don't transfer well. A model trained in a mild, temperate climate might do horribly in a dry, desert climate.
So what's the solution?
The push is towards hybrid models. You combine the strengths of data-driven machine learning with the fundamental stability of a physics-based model. That hybrid approach gives you accuracy, generalizability, and stability.
Okay, let's shift to another trade-off. Health. The last few years really drove home that HVAC systems are public health infrastructure.
Absolutely. They're not just for comfort.
And keeping people safe from airborne risks usually means cranking up the ventilation, which uses a ton of energy. How is AI helping to balance IAQ and efficiency?
This is a really high-stakes calculation. One study developed a comprehensive framework for quantitatively controlling transmission risk.
And how do they do that?
They fused two critical data streams. First, the standard airflow data from the building's management system. And second, detailed, localized IAQ data from temporary sensors in the rooms.
So they were looking at CO2, but also things like volatile organic compounds and particulate matter.
Exactly. They're taking the big mechanical data and marrying it with the specific air chemistry in each room. They used all that to calibrate these physics-based models to simulate both infection risk and energy use at the same time.
And what was the key finding from that really complex analysis?
It was crucial for the whole industry. They found that these advanced control strategies could provide the same or even better expected transmission rates.
While what?
While also achieving a significant reduction in energy costs compared to the old way of just running the ventilation on high all the time.
So you don't have to choose between a healthy building and an affordable one.
You don't. Smart predictive ventilation can meet both demands. It targets the fresh air where and when it's actually needed based on real risk, instead of just flooding the whole building with it constantly.
We keep touching on this one limitation with all these personalized models. They need a lot of data.
They're data hungry.
Yeah.
If you want a personal comfort model for your office, you need months of data from your office.
Yeah.
And that's a huge barrier to getting started.
It is, and that's where this concept of transfer learning comes in to save the day.
Okay, so explain transfer learning.
Transfer learning, or TL, is basically the solution to that data scarcity problem. You reuse the knowledge that an AI has already learned from a huge, well-established data set.
So like data from thousands of other people in other buildings.
Exactly. And you use that foundational knowledge to dramatically improve the performance on your small, limited data set from your own building.
So you don't have to start from scratch every single time.
That's the key. And the evidence for it is really strong. A study by Park and Park used these ensemble TL methods to predict comfort, and they really put it to the test. The subjects were in completely different environments.
How different?
One was in a warm office that had active cooling, and two others were in slightly cool offices with no heating at all.
So totally different thermal conditions. Did the transferred knowledge still work?
It did. Despite the huge differences, the TL methods predicted one person's comfort with up to 95% accuracy.
Wow.
Yeah. It shows that the general principles of how humans respond to temperature are robust enough to be successfully transferred to a completely new environment, and quickly.
That potential for rapid deployment is huge for anyone managing a lot of buildings.
It solves two massive problems: not having enough data and having messy data. They found TL worked great even when the target data was small and imbalanced, which is the reality for most facilities.
And we saw another study that specifically applied this to buildings.
Right. Building-to-building TL. They used the advanced transformer model and showed it could solve that data-limited problem.
And how did it do compared to just trying to learn locally?
By leveraging the knowledge from other buildings, the TL model got better accuracy, 62.2%, and importantly, a better F1 score.
Okay, F1 score. Can you quickly break that down? It's a bit of a researcher's term.
Sure. Accuracy just tells you how often the model is right overall. But the F1 score is a balanced metric. It tells you the model isn't just guessing the easy answers, it's correctly balancing its positive predictions against false alarms.
Which is really important if you're controlling a physical piece of equipment.
It's essential. A higher F1 score means the system is reliable and trustworthy in the real world. And transfer learning clearly helps you get that robustness much, much faster.
So leveraging prior knowledge is the key to faster, better AI deployment.
It is.
Okay, that was a huge amount of data models, sensors, control loops, big savings. So in this last section, let's try to synthesize all of this and look at the big picture for facility management and building design.
Based on everything we reviewed, we can say there's a moderate confidence in this evidence base.
And that's important. This isn't just theory anymore.
Not at all. The studies are solid, they're relevant, and the core findings are consistent.
So what does this all mean for someone managing a building or even just working in one? Let's recap the big, high-confidence findings.
Okay, first, AI provides the kind of sophisticated data analysis and real-time prediction that's just beyond human capability.
Right.
Second, this better proactive decision-making directly and reliably leads to better energy management and serious cost savings.
And third.
And third, and this is just as important, AI drastically improves how we monitor and stabilize occupant comfort. We're moving from managing temperature to managing human well-being.
And those three outcomes just came up again and again in the research.
Consistently.
So if we want these AI models to get even better, we need to give them better data, better inputs.
That's right. And we've seen a lot of studies still focus on the easy-to-measure stuff, and they leave out these nuanced factors that really drive comfort and air quality.
Which brings us back to that comprehensive review that identified the gaps in what we're currently measuring.
Right. They synthesized all the inputs needed for these advanced models and pinpointed what's missing.
And they came up with a list of 18 critical variables. Beyond the obvious ones like air temperature and humidity, what are some of the subtle but really important factors that often get overlooked?
Well, the list included things that are rarely monitored dynamically right now. Things like the concentration of contaminants in the outdoor air you're bringing in,
Okay.
radiant temperature, the surface temperature of the walls and windows, air density, and even how long someone has been exposed to a certain thermal condition.
So if your AI is only looking at air temperature, it's working with a really oversimplified, maybe even misleading model of comfort.
Absolutely. The review pointed out this huge measurement gap in current practice. Almost everyone focuses on air temperature because it's so easy to measure.
But they miss that its effect is tied to other things.
Exactly, like air velocity, surface temperature, and what's called mean radiant temperature.
Can you just give us a quick example of why that mean radiant temperature is so critical?
Sure. Imagine you're sitting next to a big single-pane window on a really cold day. The thermostat on the wall might say the air is a perfect 72 degrees. But the surface of that glass is maybe 55 degrees, and it's radiating cold right onto your body.
So even though the air is warm, you feel cold because you're losing heat to the window.
Precisely. And the person sitting away from the window is perfectly fine. The AI needs that radiant temperature data to understand that localized discomfort and maybe adjust the airflow just for you instead of cranking up the heat for the whole room and wasting energy.
So even with all this tech, all these better sensors, what's the single biggest lever we have left to pull for both efficiency and comfort?
It still comes back to occupant behavior.
The people.
The people. Human actions, the simple choices people make every day, are still a massive influence on energy use. They're a crucial intervention point.
How big of an impact are we talking about?
Well, simulations showed that occupant behavior has a major impact on cooling energy. And the two most influential things people do:
What are they?
the cooling set point they choose on the thermostat, and surprisingly often, just opening or closing a window.
The simplest choices have the biggest effect.
They do. And this is something you can optimize without spending millions on new equipment. Real-time experiments showed that just by optimizing occupant behavior alone, you could get behavioral energy savings of between 11 and 22%.
11 to 22%.
And a significant improvement in their comfort at the same time. And this wasn't about scolding people. It was about using AI to nudge them toward the smartest decision for themselves and for the building.
That's a staggering amount of savings. Up to a fifth of the energy bill, just from influencing human habit.
Yeah, not from mechanical changes at all.
We should probably end by acknowledging a pretty big limitation here, one that's going to affect how fast this AI gets adopted everywhere.
And that's the current state of our large-scale data collection. We've shown how great AI can be in controlled experiments, but there's still a huge gap in standardized data across the whole industry.
You're talking about the analysis of the CBECS survey, right?
Yeah.
The big U.S. commercial building energy survey.
That's the one. It's the gold standard. Researchers analyzed this huge data set, and they found something really concerning.
That is it.
The variables that are currently reported and tracked in that massive survey, they have inadequate predictive power to actually map or forecast real-world energy consumption.
That's profound. The main data source we have for commercial buildings in the U.S. is missing the key ingredients for good AI prediction.
The implication is massive. It suggests we're not even measuring the right things yet. industry-wide. There are these huge information gaps.
And things like occupant behavior.
Right. Details about occupant behavior, power management strategies, building thermal performance metrics like that radiant temperature.
And how all those things interact.
And especially how they interact. So until we can standardize how we measure and collect all of this more nuanced dynamic data, broad-based AI prediction is going to be constrained. The systems will have to stay localized. So we've covered an enormous amount of ground today. We've seen that AI isn't just a fancy thermostat.
Not at all.
It's building these dynamic models that learn your personal preferences from your biometrics, that track airborne contaminants to keep you healthy, and that forecast energy needs minute by minute to cut costs by, almost a quarter in some cases.
The savings are real, and the improvements in comfort are measurable. Remember that 18.8% better comfort just by guiding you to the right spot in the building.
It's a really compelling look at how data fusion and deep learning can make these engineered environments finally work for us instead of against us.
The evidence shows, with moderate confidence, that this tech is already stabilizing comfort while driving down energy costs. The entire way we think about facility management is shifting.
The future of it is predictive, it's personalized, and it's proactive. The building is learning you.
Which brings us to our final, provocative thought for you, the listener. We've established that these AI systems can learn your thermal preferences using your biological responses, your wearable data, even just how often you fiddle with the thermostat. And they can do it better than any generalized model. So as these systems get more and more integrated into our buildings, consider this. Will the AI running your office eventually predict your comfort needs better than you can even articulate them yourself?
And what are the implications? Practical, psychological, when the building knows your thermal state, your needs, and your habits better than you do.
Something to think about the next time the office is a little too warm or a little too cool.
Indeed.
Thank you for joining us for this deep dive. We'll see you next time.